All right, we'll get started here. Welcome everyone to the ICRA 2021 workshop on learning for caregiving robots. It's a pleasure to have you here. We're very much excited for today and for the speakers and for open discussion. And this is very much an active research field with lots of questions open. So we're really looking forward to just kind of an open discussion on lots of things related to these kind of ideas. So if you haven't seen so already, the workshop webpage is linked here on this slide, as well as the Slack workspace. The webpage will have all the details about the speakers as well as the program. And then the Slack workspace is what we're using for introductions, discussion, both before and after the workshop. So feel free, if you haven't done so already, introduce yourself in the Slack workspace. This will allow other attendees to see you and see your work. Yeah, I think if you have any questions, also throughout this workshop, if you have any questions, feel free to use the chat system in Zoom. Let everyone see your question, including after speakers or after speakers finish presenting. There'll be a Q&A session. You're welcome to put your questions in the Zoom chat if you'd like, and we can read them out for you. Otherwise, you're also welcome to unmute yourself and ask the question as well. Let's see, anything else on that? I think we'll look at the next slide here. So the organizers, so there's 6 of us organizing this workshop. Myself, Zachary Erickson, I'm a PhD candidate in robotics at Georgia Tech, and in the fall, I'll be joining Carnegie Mellon as an assistant professor. Dr. Tapomayukh Bhattacharjee, and then so I'm the primary organizer, and we have several co-organizers as well. Dr. Tapomayukh Bhattacharjee is currently a postdoc at the University of Washington, and in this summer he'll be starting as an assistant professor at Cornell University. Professor Carmen Torres, she's joining us from CSIC UPC in Spain. Professor Tomohiro Shibata, he's a professor of Graduate School of Life Science and Systems Engineering in Kyushu Institute of Technology in Japan. Professor Yiannis Demiris in Human-Centered Robotics at Imperial College London, United Kingdom. And then Professor Charlie Kemp, an associate professor in the Department of Biomedical Engineering at Georgia Tech.
All right. So what is this workshop about? Well, the idea here through this workshop is we want to explore some questions, the open-ended questions. For example, how can learning enable robotic systems to achieve efficient and safe assistance across activities of daily living or instrumental activities of daily living? Or for example, or is learning the only solution? Like, what roles can learning play, or what roles learning should not play during robotic caregiving? And basically what we want to find out is what are the opportunities and challenges of learning in robotic caregiving. And when I talk about ADLs, basically on the left bottom side, you will see these different ADLs, 6 different ADLs: eating, bathing, dressing, transferring, toileting, or walking or moving around. But in addition to these activities of daily living, core activities of daily living, there are instrumental activities of daily living. And we want to see, well, robots have the potential to help people with these activities, but like, what is the role that learning can play, and how can learning enable robots to do these different tasks for people who cannot do these tasks for themselves? Now, to be able to do this discussion, we have a very exciting program ahead. Zach, yeah. So, well, the first thing that we'll do after this opening session is basically we'll have like a couple of us, like 3 co-organizers talking about different perspectives of learning for robotic caregivers from 3 different continents. And then the way we have divided up this workshop is we have divided this into 3 different components that we think are crucial for any kind of robotic system, especially systems that help in robotic caregiving. First, the robots need to be able to sense and act, right? And so there will be a set of invited talks on sensing and acting. And then we'll have some 2 excellent contributed talks at 1 p.m. Eastern time. All these times are in Eastern time. And then we'll have a panel on what role can learning play or autonomy play in robotic caregiving. Is full autonomy even the right way to go? After that, we'll have some lunch break. And then we'll go to the next theme of our workshop, which is like and where we'll have a set of invited talks on learning for robot caregivers. Plus, we'll have our presentation from our sponsors, Hello Robot. And then we'll have a break. In the break, we'll have a special chat session going on for informal discussions. We'll be there, so please join us there. And finally, this will be the last set of invited talks on modeling and benchmarking. As you know, for any kind of robotic caregiver systems or robotic systems in general, benchmarking is important. And so we would like to know what is the state of art there. Finally, we'll end with another panel on what do we think as researchers are the grand challenges in robotic caregiving. And we'll conclude the workshop with a Best Presentation Award. The award is sponsored by Hello Robot, our sponsor, and we'll close the workshop. As Zachary mentioned, during the invited talks, whenever you have questions, please feel free to use the Zoom chat. You can also use the Slack, and both Zachary and I will be continuously monitoring both these channels. And then we'll ask questions on your behalf, or at the end of the talks, we can even ask you to unmute yourself and ask the questions directly. Yeah, that's basically the program at a glance. If you want to know details about it, please visit our website. And we really look forward to an exciting day ahead. Thank you again for joining us.
Yeah, thank you all for joining us. So if you have any questions, now is a good time to shoot them out before we get started in the opening session. Otherwise, in just a few moments, we'll get started with some of the first few talks from some of our organizers, just giving some of their perspectives on what is learning for robotic caregiving and how do they view it, kind of what are their perspectives on it. And these speakers are coming from 3 different continents here. So
I was just going to say, I'm not going to be on, I'm just going to be in the Zoom chat because like 2 things going on. I mean, I'm going to go crazy. I'll be really happy if we just see a lot of activity in the Zoom chat. And I would encourage people to focus their stuff there so that everyone can participate. I'd love to see what you have to say. But if you want to keep things secret from me, go to Slack because I've never used it.
Yeah, but definitely during the Zoom calls, feel free to stick with chat. That'll be the primary mode of communication for us. And then Slack will be just something afterwards if you want to introduce yourself to some of the other attendees. Awesome. So I think we got Tom. Do I see you there? Yep.
Yes.
All right. So we have everyone here. Any questions before we get started with the first opening session here?
Do you plan on having any sort of after this you're planning to post everything, the videos? Do you plan to have any sort of write-up or other sorts of follow-ups?
There may be. It sounds like potentially a blog post that shows up, or a news article that shows up about this, kind of summarizing some of the key points and things that came out of the workshop. There might be other opportunities as well, but nothing's formalized yet as it stands. But definitely in terms of recordings and such, this workshop is obviously being recorded, and that will go up on the workshop webpage and on YouTube, at least as the first mode of presenting what happens in the workshop, and then hopefully there will be some follow-up points beyond that. But those are still in the works. A good question. All right, well, let's dive into the beginning session here. So it is my pleasure to introduce, so we have an opening session. For those who are just joining us, again, we have an opening session on learning for robotic caregivers, perspectives from 3 different continents. And during this, we're going to have 3 different speakers: Professor Tomohiro Shibata, Professor Yiannis Demiris and Dr. Tapomayukh Bhattacharjee, and presenting some of their perspectives on what does learning for robotic caregivers mean, and how do they view it from their perspective. And so we're going to dive into that here. I'm going to start off with Professor Tom Shibata, joining us from Kyushu Institute of Technology in Japan. If you'd like, let's.
So would you please let me share the slides? So I think it's inhibited.
There you go. You should be a co-host now.
I just made you a co-host. Yeah.
Okay, thank you. Okay. So can you see my slides?
Yes, we can.
Okay. Hello, everybody, and good night from Japan. And here it's 11:16, and so I think it's difficult to keep awake. I'm very excited to have this opportunity and this workshop, and thank you very much. So Zachary and Tapo, and thank you for your all efforts. Thank you very much. And I'm really excited, but I think I'm going to be sleeping, unfortunately, soon. And tomorrow morning, I need to work early again. So maybe if you have some questions, so please put it into Slack, and I will read it and answer questions later. So unfortunately, I was really excited to see some panel, some discussions, but later I will watch it. Okay, so due to the time limitation, my time is, I think, I have only 15 minutes plus something. So let me start. The title is Learning Schemes for Closing Assistance. And actually, so usually you say dressing, and historical reason I usually say, closing assistance, sorry, and yes. So just the background slide is only 1 or 2 slides, and this tells, so Japan has been always the top regarding the aging rates in the world, even in USA, Europe, and also Asia. Yeah, so that's only the message. And so different robots and different ICT or some other technologies are needed for different health conditions. Fortunately, so it's I need to shorten my explanation to explain this slide. But you see, according to this age and your physical abilities or cognitive abilities, there are different stages. If you're healthy, then you don't need a robot at all. But sometimes, so you are aging, you need to have to take care of preventive care. And also, if you are injured or if you have some disabilities, then you need to do rehab. Then maybe your ability can come up to the original level, close to the level. But again, so it's slowly going down, or sometimes suddenly going down to the the level where you need full support by the robots. Yeah. So of course, so we don't want to be that. So there are so many pictures here. And so interestingly, many of them actually, I have been working with many of these robots, but today I need to focus on my studies from the viewpoint of learning, on dressing assist. Yes. So need for closing assistance is quite clear in Japan. So Japan is facing a severe shortage of caregivers, and use of caregiver is predominant in dressing, right? So, this kind of a trend is also happening in other developed countries also. So it's worth working with this dressing assistance technologies. And actually, my mother has been Parkinsonian for more than 25 years. And if you get elder or so like my mom, you cannot raise your hand, higher. So if such a disability happens, slight disability happens, it gets difficult to dress by yourself. So that's why I mean, from such a personal perspective, I started working with closing assistance, robotics. Okay, so this is the total scenario of our robotic closing assistance, right? So, today I so emphasizes this part. So arm reaching and reaching and arm dressing and full body dressing part. But I really want to have full automatized, so dressing according to this arrow. So first it needs to find that clothes, and then it needs to initialize the closed state, and after that, so it address. So I have to say, so general image of the subject, I mean, we have assumption on the target elderly. So they have narrow range of motion of the shoulders, but they can, stably sit on the chair, and they have a stable upper body posture. So otherwise, it's too difficult for us to help. Okay, and the major challenges are some manipulation and control of non-rigid clothes, and description of human clothes relationship is another major challenges, and a change in environment. I mean, in this case, environment is mainly a caretaker. So what happens if caretaker changes the posture a little bit or something like that, and also they have individual difference in kinematics. And so actually dynamics, but I haven't worked in that direction yet, so only some kinematics. And safety is really important. Safe human-robot interaction is really important, because, so please watch this picture. So if you know my study, so you feel, oh, it's awful, it's quite dangerous. You might feel that, right? Yeah, so so we need to be very careful about implementing safe robot control. Okay, so this is my oldest study with the collaboration of Dr. Tamei, Dr. Matsubara, and Dr. Riek, and she got a PhD in CMU, and now she's working for Facebook AI. And at that time, we used Barrett WAM, right? And but already we implemented reinforcement learning with nice reduced. So the robot has high dimensions, and also clothes has a high dimensional state, but we have implemented some lower state representation and also policy representation, and some reinforcement learning worked nicely like this. So this is a reinforcement learning scheme. So this is not too much important slide, but just I need to tell, so our strategy is how to so initialize the model. So I mean, that was by direct teaching method, and after that, so we automatically extracted via points in this study. Yeah, so and the via points is well defined in the computational neuroscience, and it can generate very smooth motions like humans. And so you need to have trajectory representation in a low dimensional state space, and also you need to have a environment state representation. And in this study, we applied the topology coordinates to describe the human close relationship in a very low dimensional state space. And unfortunately, so we don't have time, I don't have time to explain this very carefully, but the point is reinforcement learning is a quite versatile method. But to use that, we need to have good representations in the environment and also control policy. Yeah, so that's the point. And also reward also. Okay, and yeah, so so we used Barrett WAM, and we succeeded in some press release in US and also in Japan. But unfortunately, so some of my colleagues gave me a phone call, Shibata-san, that is quite dangerous. So a safety issue is really important, but fortunately, Professor Brooks developed this Baxter, and this robot has a very essential safety. So I was energized and started working with this robot for closing assistance again. Okay, so this shows the latest our framework for imitation learning and safe control for closing assistance. And the latest publication was done by Dr. Joshi, and also, so Dr. Koganti, so we collaborated Dr. Koganti a lot. He was a nice student, and also Joshi, he was a QTech student. Okay, so anyway, let's focus on this part only. And this consists of two parts. One is arm dressing part, and the other is body dressing part. And for the arm dressing part, we applied dynamic movement primitives. Sorry if you don't know the dynamic movement primitives very much, but it also employs learning, right? And it utilizes a nonlinear attractor, and so it can be quite helpful for implementing a stable controller, and it can be adaptive to the change in the environment a little bit. Yes, okay. And using DMP for the arm dressing phase, please see this. In this case, we used actually a humanoid robot, pneumatically actuated humanoid robot. And actually during these, so on these movies, if you really focus on the motions of this humanoid, actually it moves the arms according to some rules. Okay, and unfortunately, sorry, the figures, graphs are difficult to watch, but the message here is, even if, during the arm dressing phase, even, so the humans, in this case, humanoid changes its arm posture, but DMP is actually nicely tracked the difference, change in the arm position, okay? And, oops, sorry. So didn't I show, sorry, I really want, I'm sorry, maybe yes, I want to show this. Sorry, I made some mistake. Okay, please watch. The arms are moving, right? And this shows, the target. The goal for the arm dressing is being changed in an online fashion to adapt to the changes so in the arms. Okay, so perform, yes. Okay, then how about body dressing part? We applied Bayesian Gaussian process latent variable model to find out, to capture the 2D latent space. So of the 14 degrees of freedom's dual arm space. Fortunately, we found that it was 2D, and now you see. Currently, I need to show it again. Yeah. So cursor in this demonstration, the cursor is moved by a user, right? And the blue line shows the thought trajectory, implemented, embedded in the 2D space. And now, so the user is exploring unseen, position, unseen in state. So on this latent space. But actually, so you see a quite, similar motion. So with the original motion. So this lower representation works out very well for closing assistance. And also this is safe actually. If you point out, so untaught position point on this space, but still it generates a quite similar motion to the original taught trajectory. So it's safe. Okay, and so I need to skip, maybe I consume too much time. So again, so using this robot, new robot, Baxter robot, we have applied a reinforcement learning method with the low dimensional representation acquired by applying BGP LVM like this. Okay. So it can be quite quick. So in this case, of course, so mannequin posture was changed after teaching the initial motion. Okay. So and actually that was the latent space for motor control. And we have also found out the latent space, very 2D latent space for describing human close relationships. And for this purpose, we applied manifold relevant determination, and where one latent space can represent two multimodal inputs. That is, in this case, that is ground truth acquired by the optical markers, and also 3D point clouds acquired by Kinect in this case. Yeah, so 2D space, and then now the dressing is running, and you see, so 1,000 point clouds are actually projected onto one point on this 2D space. Yeah, so like that. So applying, so Bayesian Gaussian plus latent variable models is quite efficient. Okay, so a summary, and I have one more slide. So a summary, manipulation and control of so these are major challenges, and we propose, to use a human demonstration and followed by trajectory modeling by DMPs and also BGP LVM, to acquire latent space. And description of human class relationship is also very important. So there are several ways. I mean, sorry, this is not via points. I'm sorry. This is topological coordinates. So one example was topological coordinates, and another one is multimodal latent space. And to deal with the change in the environment, and again, the DMP is helpful. And also reinforcement learning is quite versatile. And safe human-robot interaction, so DMPs and also latent space controller are quite, so can give the safe controller. And this is the final slide. So I really want to have fully automated robotic closing assistance. And so this is one example. So we have applied CNN and to find out the features, key features of the close like this, and it can pick up, it can detect, and it can pick up quite accurately. Sorry, this is quite noisy. And also try to apply CNN to find out grasping points for the initialization part of this our addressing. But it turned out it's quite really difficult. We need a lot of features on the close, but in this case, the feature close doesn't have any feature. So it turned out it was really difficult. But anyway, so that's why currently this is our latest result. We implemented a multi-robot collaboration system, and this Toyota's HSR can pick up a hanger, T-shirt on the hanger, and it can show it to the Baxter. And after that, the Baxter can start the body dressing part, arm dressing, and the body dressing part also. And this is another demonstration. Oops, this is very slow. Yeah, in this case, the user is changing its posture. I mean, changing the arm angular position according to the body, okay, artificially. And in this case, this is a case of multimodal robot collaboration. And this wheel, a very popular electric wheelchair, is trying to stabilize the arm position to the Baxter, okay? And after that, still, the body is skewed a little bit, but dressing, I mean, not so easy, looks not so easy, but actually this will be completed. Okay, yeah, like this. Okay, so thank you very much. Thank you for listening, and any questions, welcome, or comments are welcome. Thank you very much.
Thank you, Tom. So at this moment, there's a couple minutes for questions. If anyone has questions, feel free to put them in the chat, or you're welcome to open up your microphone and ask them directly.
Hello, I have a question.
Mm-hmm.
Thank you for the great talk. My question is, how is, like in the reinforcement learning case, how much data does it usually require to learn a good policy?
Yeah, so that's a good question, but unfortunately, we don't have a general answer, right? So it depends on the representation, how representation is compact or represented in the low dimensional state space efficiently, and also how your actual change, in the environment is not so harmful, right? If the change in the environment is under the assumption, and representations are, policy and the state representation are, compact, then it will be really quick. Actually, in our very simple-minded, reinforcement learning example, it requires only, around eight episodes at maximum. But you can say, it's too easy. Okay.
Okay. Thank you. So that's quite fast, actually. Okay.
Quite fast, yeah, quite fast.
Thank you.
You're welcome.
Any others?
Okay, let me, Charlie, go ahead.
Oh, I was going to follow up on that question. Also, yeah, excellent talk. It was really great to see, and I've very much enjoyed following your work over the years. I was just wondering, in those 8 episodes, would that be possible to have those episodes performed safely with a person with disabilities, or how do you close that gap given the potential risks?
That's also a very good question. So in the past, actually, we conducted our demonstration. I mean, some preliminary real-world evaluations in a nursing care home. And so participants are female and very elder, and usually they use a wheelchair. And actually, we were able to do it, and without any big difficulties. But of course, so we have some certain assumption on the target. So in general, their sitting position should be quite stable, and they can stand still on the chair, right? And also, so that's why. So if, for example, my mother has been, the symptoms are getting very bad, worse. So she's inclining a lot like this. So unfortunately, so far, our system cannot deal with her problem, right? Yeah, but in general, of course, so as you know, if their postures are changing a lot, still we need to improve our system, right? But from ethical, I mean, they didn't respond. I mean, they didn't tell us quite fearful or awful. They didn't tell us. That's good. So after this COVID-19 situation, after making fully automatized, dressing system, I really want to do real-world evaluations again in a nursing care home.
I think the point I was trying to emphasize was one of the challenges with using learning in the context of assistive robotics is if you're doing on-policy learning with people, then there are these, and people who are potentially vulnerable, these additional risks. And I was curious about how one might mitigate those risks if the goal is to do sort of on-policy learning with the people who are vulnerable.
Yeah, thank you very much. Yeah, so I think, so I mean, maybe we need to have a lot of actual, experiences, I mean, samples with many elderlies, and we need to develop some off policy and also maybe recommend the systems also with a lot of samples first, and then slight improvement or improvisation with the own policy.
Right. Yeah, it makes sense. Thank you very much.
Thank you for your question.
Thank you, Professor Shibata.
Thank you very much.
Okay. All right. So at this point, we'll move on to our next presenter, which is going to be Professor Yiannis Demiris, joining us from Imperial College London, United Kingdom. And at this point, I'll hand it over to him, and he can share some of his outstanding work.
Hello, everybody. I'm hoping that you can all see my full screen now.
You can.
Great. Okay, thank you. Hi, everybody. It's a pleasure to be here. It's nice to see so many people, friends in the audience. I'm one of the co-organizers of this workshop, but I should say that Zachary and Tapo did most of the work, so I should not take the credit. They are really the ones that did most of the work. I am very excited to give you an impression of what my work has been about the last few years now. I work quite a lot in personal assistive robots, and the words I have chosen for the title are important for me because, of course, for this workshop, assistive is important, but also personalization is what I see to be a very key opportunity for learning in this field. I think what I have been fascinated over the years is how different people are, right? Not only in ability, but also in disability. So, people look differently, they act differently, they have different problems, they have different skills. So one of the things that I have always been interested in to see, how can I make the assistance more personal for this person, right? For this user. So for the last more years that I want to remember, the work I've been doing is trying to see whether we can design and build architectures for robots that personalize this assistance. So from left to top to right, we have been doing this work with kids with disabilities. For example, here is some kids trying to learn how to control a wheelchair and move around the environment, explore the environment. Assistance, don't forget, is not required only for the elderly. Tom did a very nice introduction to the problem faced in Japan. We have very similar problems here in the UK, but also one of the things that we're quite interested in seeing whether we can help kids with disabilities to see whether they can achieve their full potential. On the top right, some of the other work we did, it was introducing some of the more interesting robots in terms of morphology. The now robot in an intensive care unit in a local hospital in Chelsea and Westminster Hospital, where we introduced it in the intensive care unit, and it was trying to help people, keep them a little bit of company, because it's not easy to actually visit in places where contamination or other visitations is not a good idea. So you could actually do more exercises and discuss and keep companionship in general. On the bottom left, the example here is of a clothing assistance. We very much, like Tom, interested in this quite challenging task of helping people to get dressed. On the bottom right, one of the aspects that I will explain a little bit is how can we explain the internal state of the robots to the users so they can understand more about what is the mental model that these robots have for the users. So in all these cases, what I'm interested in is, of course, is not only doing some assistance, but actually trying to see whether I can make this assistant better over time. And this is where learning comes in. So here's the kind of like the general structure of all these scenarios. Essentially, we have a perception, a sensing aspect, where we're trying to understand the user states and what are the users doing, usually through multimodal interfaces. It's not only vision that we try to use, but also haptics, wearable sensors, etc. Once we have a kind of a steady stream of user states, we're trying to see whether we can understand and predict the user needs and intentions by building user models. And I think that's where the personalization aspect comes in, and where my interest has been over the years. Once we have some sort of internal models of the users, we try to adapt the robot behavior to improve the interaction and the assistance effectiveness over time. And I think this extended period of interactions that I'm noticing on the bottom left is important, because with some of our users, the robot will be with them for the rest of their lives. So it's important for the robots to change over time to reflect the changing profile of the users. So to be a bit more technical and go a little bit more details and show the opportunities for learning, of course, we start by finding the users, tracking the users on the left. Yeah, and once we have the users, where are they and what are they in our video stream? One of the interesting things for us is to see how can we understand more about their body morphology, and we call this articulated structure learning. So the idea is that every person is different. They might have different disabilities. They might have missing limbs, and can we actually extract the morphology of their body by watching videos, right? So by watching them performing tasks, can we understand what are the different body parts they have and how well can they utilize it? And at the same time, we also do eye gaze tracking. So we're trying to learn more about their bodies and trying to learn more about where they're looking at and how they're engaging with the environment, to see whether we can understand something a bit more about the cognitive state. Now, one of the issues also that I'm quite interested and I think learning is important, is how can we go from these individual structures to understanding how does this structure match with other known structures we have seen before. So if this is a way, for example, to understand whether a person is of a certain type of disability or has a certain body morphology that can match against a database of different users we might have, and that database can allow us to understand a bit more about their morphology and about their capabilities. Once we have this kind of like, essentially a body model, we can try to understand and see how the people are moving. And here, I will show you a little bit in a minute how we can learn how this person is doing sequence of movements. How can they, for example, here put some jacket on or something like that. And usually we typically use things like neural networks or statistical representations for this. But for when we're trying to see how the person is behaving over long term, we using neural networks is not always an easy way for replicating patterns of activities over days, over different times of the day. So one of the things that we're trying to do is also trying to see, can we do symbolic actual representations, so we can actually try to learn, for example, grammars of behavior over time. And this will actually lead us eventually to essentially long-term user skills. And this loop, as you can imagine, has a lot of learning potential in every single aspect of this pipeline, personalization pipeline. Now, once we have this personal model, and let's say, for example, in the top left, you see a model of how a user is actually moving during dressing. If I have a model also how the person is changing over time, and I have an assistive robot, what can I actually do? When I say personalization of assistance, what are the different things we can actually personalize? So the three categories we are working in, one is modulation of the assistance. For example, when we have a kid with that's moving around the wheelchair, or whether we're having a person actually being dressed. Essentially, you have a shared autonomy situation where the user is doing something, and the robot will try to modulate the assistance to match the actions of the users. Another thing we are trying to do is trying to see whether can we modulate the training differently. So if we're trying to assist them, for example, trying to teach them to do something. In this particular case is, for example, a robot's trying to teach dancing to kids with diabetes. Can we actually modulate how difficult this training that we display to the user is? And finally, as I will show you a little bit later, we can also modulate the information we present about the task to the user here through augmented reality, because then we can try to stagger how difficult this presentation, how detailed this presentation can be based on the user skill model. Essentially, this is like the general overview of what I think in this field we can apply machine learning and use user modeling for effective assistance. What are the key challenges? I think that on the left panel, I have the challenges I think that are actually still unresolved. First of all, we don't know how and when to help always, right? So I think having one particular user, we need to understand the user intentions, we need to understand the capabilities. We have to determine whether we can help, because it's not always we will be able to help, and sometimes helping might not be a good idea. For example, if the help is not wanted or needed based on the developmental stage, we should consider whether we should do that assistance or not. And one particular way we've been working on in doing intention prediction and understanding human states is basically using simulation theory of mind approach in a generative manner. So we use internal models to predict what the user might do and see whether we can adapt the assistance for that. We've been working in developing a cognitive architecture that is similar in the different tasks. So I don't want to hack the system for each individual task. I would like to learn a generic one. And this architecture is using both inverse and forward models in different levels of abstraction in order to internally generate the observed actions for understanding the intention of the user. The diagram is a little bit complex, and I don't have time to go through all of it. The only thing I want you to take from this one is that we need, when we're trying to model a user and make a model for the long run in multiple tasks, we need to have hierarchical user modeling. So at the bottom level here, we are getting the visual data, acoustic data, haptic data, any kind of data we have about the user, and we pass it through usually some statistical models or neural network models to build models of the user and form predictions of what is going to happen next. But increasingly, this should be more and more abstracted. So for example, we use probabilistic activity grammars to represent things that are repeated over time, or have recursion, repetition, things that are a bit more difficult to represent using statistical models. For the lower level of abstraction, this is an example. So for example, here we use eco-state Gaussian processes for learning to model the movement of a user. How is the user moving? Even in the middle, you see corrupted data, for example, through wearable sensors. Because a lot of times, we don't have complete data about the user, we should be able to reconstruct some of the motion observed. And for things like this, sub-symbolic representations are quite nice. Another example is also in the dressing scenario, where we're trying to see whether we can use GP LVMs for learning different types of movements in latent spaces. For example, here we have we utilized arm harnesses for modeling different types of disabilities. For example, limitations of the shoulder, limitations of the elbows, etc. And we see that actually this kind of models can tell us more about the user, and we can actually see and understand the kind of disability the person has from observing the user's movement and mapping to latent space. But for higher level, so this for this kind of like low level movements, this is quite sufficient. But if we're trying to see whether we can do something in the more higher level, for example, how a user is actually doing a task, to see whether, for example, they have any cognitive issues or whether they don't understand how to do something, we use context-free grammars for doing learning a model of how the user behaves over time. And we put all of them together to form the user models I was telling you. An important aspect that we're also using is eye gaze. And in this particular case, on the left, we're using eye gaze, for example, to record where is the person is looking at while using a robotic wheelchair, to understand a bit more about the cognitive workload that the user is experiencing right now. Or on the right-hand side, we model the user's comfort levels in order to understand whether what the assistance we're providing is matching the user's desire and the user's desired comfort levels. Moving the last couple of slides I have, when I'm saying that I would like to adjust the assistance, the kind of the assistance we can do is can be either direct, and in the left side we have adjustment of the control signals to the user to make sure that they remain safe. So, for example, here the user, at this particular point was stopped from hitting himself on the wall. On the right-hand side, we can also have indirect assistance where the child here, for example, might be able to control the wheelchair, but we give it a bit of instructions and visualization of what they should do next, how to navigate this particular maze. So this either direct or indirect assistance is something that we can provide and adjust based on models of the user. One of the aspects that we are finding difficult about is that all these users, of course, are being helped by the robot, but sometimes I struggle to understand the internal state. Why is the robot helping me in this particular way? And one of the aspects that we are very much interested in is see whether we can visually explain this reasoning process. For example, here Mark in IROS a couple of years ago shown that you can use head-mounted augmented reality displays to visually explain the reasoning process that the robot is using now to assist the user. So, for example, here the augmented reality headset will actually show to the user a model of the environment and the intended assistance, so to explain more why is the user is being assisted in this particular way. Or on the right-hand side, we do this also with multi-robots, where you have a wheelchair and is being assisted by a user who is on a wheelchair and is being assisted both by the wheelchair, which will take him to the right place, but then at that point, the robot will also give him something that he can do, and we can do this using affordances, combined affordances from multiple robots to help the user do more complex tasks. I think that was a very quick introduction to our research. I think to summarize, personalization of robots' behavior is, I think, a major cause of concern and challenge. Because we like to maximize the user's outcomes, and this could be different based on both the cognitive and physical state of the user. We usually, in our lab, we do generative modeling of user skills, preference, and intention. And I think the remaining aspects that I think is quite challenging, I'm very happy to discuss with all of you later, is when and how to help is something that I think still remains a difficult challenge for all of us. And with that, I will stop here and stop sharing my screen. And thank you for your attention.
Thank you, Yiannis. So again, we'll open it up to questions. If any of the audience members have questions they'd like to ask Yiannis about his research or his perspectives. I'll open up one question for you, Yiannis.
Sure. There's a chat. There's something in the chat.
Oh, let's start with that.
I cannot monitor all I have the other one open as well, but.
Okay, so thank you for the chat. Gabriel says, concerning intent inference, how is the feedback from users in practice? I suppose that the cost of executing an unwanted action is much higher than the cost of inaction.
Sure. That's a great question. And actually, to give you an example from the work with the wheelchair with kids, we are very conservative in the beginning. So we assist quite a lot in the beginning to make sure that the child can do the task. And then over time, we actually remove some more and more of the assistance to make sure that over time, the user can do the task by themselves. So it depends quite a lot on the type of task we are doing. If the task is actually safer to let the user do it by themselves, maybe you can let the user do it first, and then you can learn to assist as time goes by. On the other side, if the user cannot do the task, maybe it's easier to start by helping all the time and then taking the assistance away. So I think basically the developmental aspect of what are you trying to achieve, what is the assistance required in the long run, right? Not just on that snapshot. I think that's basically our viewpoint. It depends very much on the task you're trying to do. I hope that makes sense.
Thank you for that question. So Yiannis,
Yep.
Can we bring personalized information? So if let's say we have a general model to start with, right? It's kind of, if the robot is interacting with the person for the first time, right? They haven't had any time to personalize. So you start with a general model, and then over time, that model becomes personalized. Mm-hmm. Can we bring some of that personalized knowledge or learned information back into the general model so that the general model is better for the next person?
Sure. No, you're absolutely right. And actually, that's what I was trying to allude in when I was discussing about keeping some sort of database of different types of users or different types of disabilities. So I think for sure you can start having variations of the initial model. So do some experiments, let's say, with some users, collect some of their models, and then bring it back to the general model and capture the variations between them. It's the cold start problem, right? How to bootstrap the assistance from other similar users who you have assisted in the past. Right? Yeah, I think that is possible for sure, and I think that's a very nice challenge.
Any last questions for Professor Demiris?
There is a hand raised, Zachary.
Oh yes, I see. Katao, would you like to?
Yeah, okay, I'm muting myself.
Okay.
Hi, Yiannis. Great talk. But I may ask a question is a little bit off the, what you talked about. I mean, for the current robot, because you have done a lot of work in this, like assistive robotics, and how much are the current robots, accepted by the, like what we call patients or who else need the care actually?
Sure. Mm-hmm. It varies a lot, right? It varies on their background. It varies how well you have explained it to them and to their caregivers. In the variation we've seen when we took the robots to the Chelsea and Westminster Hospital in the ICU, there was a lot of people that loved it. There were some people that just didn't want to have anything to do with it, right? And that's quite a lot of variations. I don't think you can know in advance, whether it will be accepted. I think there's a lot of potential there, and it's up to us to explain and educate people what can it actually do. One of the things we should be careful, of course, is also what it cannot do, right? Because sometimes we get excited about the potential and we are not very clear on what are the limitations. So, for example, the kind of dressing work we have, most of the research I know about been doing work on, we don't change clothes that require a lot of fine manipulation or are too close to the body, for example, underwear or something that is actually very difficult to actually put on, like I would have a lot of loops. So I think these are more difficult and require forces that I think is not safe yet we're not completely sure what we can do, right? I think that the big problem with assistive robotics in general is that if the robot is strong enough to help you, it's strong enough to kill you, right? So all of the robots we are using, exactly, in most of our cases, are not strong enough to do a lot of the tasks because we care about safety first, right? How could we, how can I lift somebody and put on some underwear for them, for example? A robot strong that's that strong will do a lot of damage to the person if we are not 150% certain that they're still safe, right? So I think that is one of the issues we have to be careful of about what the robots can do and what the robots cannot do.
Okay, great. Thank you very much.
Welcome, Miguel. Thanks for the question.
Thank you. So now we'll move on to our last presenter of this session, Dr. Tapomayukh Bhattacharjee, joining us from University of Washington and then soon Cornell. So Tapo, the floor is yours.
Thanks, Zachary. Can you say it in full screen mode, my slides? Awesome. Hello, everybody. As Zachary mentioned, so my full name is Tapomayukh Bhattacharjee, but I understand that it can be difficult to pronounce, so just call me Tapo. I am still I'm wrapping up my postdoc at University of Washington. In a month, I'm actually, though I'm physically in Ithaca in the East Coast, in a month, I'll be officially joining my position at the Department of Computer Science at Cornell. Here is my new lab. Preliminary attempt at building the website. Feel free to go there. But yeah, more exciting stuff to come there soon. So today I'm going to give my perspective on building caregiving robots. Basically, before I go into this, I would like to first show my lab, current lab, at University of Washington. In the middle, you see my postdoc advisor, Sid, who's also going to give a talk later in this workshop. And so some of the content will be overlapping, I guess. And then here is my PhD lab. So this, incidentally, was a lunch that we went to after my PhD defense. So on the bottom left corner, you see Charlie, who is also one of the co-organizers of this workshop. And just sitting opposite to me is Zachary, who is also another co-organizer. So my goal as a researcher is to enable robots to assist people with mobility limitations with tasks of daily living. Now, when we look at activities of daily living, right, given I am tasked with the with giving you a perspective from the from America continent, or according to a survey that was back in 2010, pretty old survey, around 12.3 million people in the United States needed assistance with different tasks of daily living. And as I had mentioned earlier in the opening session, there are various activities of daily living, right? Like core activities such as feeding, dressing, transferring, or instrumental activities of daily living that, like housework, laundry, meal preparation, and things like that. Now, robots have the potential to help people with these activities, but if you see just from this small sample of all these pictures, there's a wide variety of these tasks, right? So how can we even imagine a robot that can give these generalized assistance to all of these tasks? Well, if you look closely to each of these photos, one thing that's common is here the caregivers are physically interacting with their environment, whether it's an inanimate environment or the care recipients themselves, right? And the physical interactions happen not just over the hand or fingers, like in this, like feeding someone, but also over the entire arm or body, like when the person on the right is trying to transfer someone from bed to wheelchair. So the fundamental research question that I'm interested in is how can a robot leverage physical interactions in unstructured environments, such as homes, to assist with activities of daily living. Worked on various approaches of leveraging these physical interactions. So here are some snapshots, right? Like, for example, I've worked on developing whole arm sensing skin for robots so that we can use this so the robot can use this to physically interact with its environment unknown environments, and then reach into these cluttered spaces. And this is clutter is very common around people with mobility limitations, right? Now, I've also but also on the bottom, you see where I've worked on small area contact, where the robot is interacting with food of different properties, and then feeding someone. And then we have also evaluated this with people with spinal cord injuries ranging from C1 to C6. But when we think about physical interactions, we generally think about forces. But that's not it, right? Another thing that we have seen is that when I have tried to combine this with other modalities, such as like vision or thermal modalities, we have seen that we can actually collect more information. Machine learning, whenever we think about learning for caregiving robots, right? Learning depends on data, and the more information you get, really, the more you can use that information, you can leverage this information to decide the strategies that the robot would use. And so one fundamental key insight that I've learned from all of these different projects is, multimodal perception is important, because we need multimodal perception enables us to collect as much information as we can from these physical interactions that we can then leverage to do different tasks. Now, even though there are various projects, today for my talk, I'm going to focus primarily on one particular application, and this is the application of robot-assisted feeding. Now, why assisted feeding? Well, imagine yourself asking someone else to feed you every morsel of bite in your day-to-day life. It takes away the control, the feeling of control and independence, right? And when I visited these assisted care facilities and people's homes, people with mobility limitations, yes, caregivers are playing an amazing role. But even after that, care recipients may still feel embarrassed, rushed, or socially challenged. And these are not some words that I made up. When I talk to them, these are the words that they themselves mentioned. Now, assisted feeding is also unique because turns out feeding is one of the most time-consuming tasks for caregivers. And so it may increase caregiver burden. And so if a robot, which has the potential to help people with these tasks, if it can help with this task, it can also potentially free up some time for the caregiver to be able to focus on other activities. And also turns out this assisted feeding is also a very multifaceted and technically challenging problem, right? Let's think about this. If we try to divide up this task, the first is to be able to pick up the food, different kinds of food from different kinds of containers, right? And so we call this bite acquisition. Now here, even though we can have different machine learning algorithms to be able to pick up different objects, but there are so many objects, so many food items. If you go to a typical grocery store, there are 40,000 items. So it's almost impossible for your algorithm to learn from before all these different food items that exist in the world. And so adaptation to unseen food items is key. And so here, learning can play a role for caregiving. Let's look at the next step. Once you pick up the food, it needs to be transferred to a person's mouth. Here, this transfer is basically, it's like a robot to human handover. Unlike a normal handover, when we look at where you pick up an object with a hand and you give it to someone else, here the handover is from a robot to a person's mouth, and especially with mouth of people with limited degrees of freedom. And in addition to this, this is where, because it's such an intimate human-robot interaction problem, adaptation to user preferences is key, as was evident from the from Tom and Yiannis's presentations before. So here again, learning can play a key role to be able to help to do these tasks. However, as one of the speakers brought up, there is also this huge aspect of technology acceptance, right? What's the point of developing these robots and doing demonstrations in lab if people actually do not accept the technology? And that's where perception of safety, utility, enjoyment, all of these things are important. And there, the learning is not the entire story. You need to go much beyond that, right? So here is our first preliminary attempt at a robot-assisted feeding system. Here you see the robot autonomously going, picking up a fork. It can be another tool, but we have experimented with fork. It picks up the fork. It goes on top of a plate, it looks at different food items that there exist. It identifies the food items. Using the algorithms, learning algorithms, it figures out what is the best strategy to pick up a food item. It applies the right amount of force because food items can be hard, can be soft, can be slippery. Then once it picks up the food item, it goes in front of the person's face. It figures out what is the right way to transfer the food item. For example, for this long, slender carrot, the robot decided to tilt it so that it's easier for the person to take a bite. Now, the key insight from all of these things, and I'll go a little bit deeper into the algorithms that we have used for this, but the key insight here is, even though there could be multiple ways to pick up a food item, when we pick up a food item, we also need to be thinking about what is the ultimate goal. So the transfer depends on acquisition. And it's something very intuitive, right? For example, let's say you have a pen on your desk. If you want to pick up the pen, there are multiple ways of picking up the pen. But if you want to pick up the pen to write, versus you want to pick up the pen to hand it over to someone else, you will pick it up in different ways because you are optimizing that based on the task at hand. Here, we are using the same idea. So the algorithms that we use, it uses the transfer. It makes sure that when pick up, it's not only successful in picking up, it also can, it makes it easier for the person to take a bite later on. And that depends on different food items and things like that, the properties of food items. Now, but the question is, how did we do the bite acquisition? Well, so here is the algorithm, right? So look at the top picture. Like here, the first, when the robot goes on top of the food item, of the plate, we have an off-the-shelf retina net that we have fine-tuned for our food item data set. And what retina net does, it comes out with these bounding boxes around these food items. And then these bounding boxes, each of these bounding boxes goes an input to our skewering position action network that we developed. Now, one thing that we learned, and this is the key insight that from this slide, is basically the control policies that the robot needs to use. We originally thought coming into this problem that it depends on the physical properties of food. So, our algorithms will choose different strategies depending on whether a food is hard or soft or hard skin like grape, things like that. But turns out that's not the entire story. A policy depends on not only the physical properties of food, but also its immediate surroundings. For example, the most successful strategy that you pick up when you have a food isolated on a plate versus it's near other food items or near the edge of the plate versus it's like on top of a salad or something is different. And so we also had using classical computer vision, we had an environment classifier that we input on this network as a one-hot encoding vector just before the final layer. And then using all of this, the output was an action score map that tells for each food item, what is the most successful strategy to use and what is the probability of success. And we found that using this algorithm, it could generalize to some unseen food items as well. As you see in the bottom examples, where you see the identification is not about bell pepper versus strawberry. Algorithm only knows that it's food. And the way it was doing it, the insight was that it was generalizing based on shapes and size and color. So for example, if the robot knew how to pick up a spinach, it would know how to pick up a kale or a lettuce or things like that. But the problem is, as I had mentioned, there's so many food items, right? What if there is no way to generalize to, like for example, there are no the properties using visual modalities that we've used, it couldn't find any other match, right, to be able to do that, or it had never seen the action that it needs to use to generalize to. And that's where we moved. We adopted the idea of online learning. And as all of you know, again, that online learning, we need to have a state. Based on the state, we take an action and we get a reward. And so the top part is pretty much similar to what I had just shown you. We have the retina net that gives out these bounding boxes, and that gives as and we use our SPANet network as a featureizer that uses a linear map to select an action. And then our reward is the food item on the fork or not? So it's a binary reward, right? And based on that, we update our policy. And we model this as a contextual bandit. You can think of contextual bandit as basically, it's bandit because the robot is privy, it just knows the reward of the action that it took. It would know what happens if the robot takes another action. And so it's partial feedback, and it's contextual because it has the information of the context, in which is given by the featureizer here. And the idea here is to minimize cumulative regret. Now, to balance this exploration versus exploitation, we use this algorithm called linear upper confidence bound. And the idea here is it chooses the action with highest upper confidence bound. And now here is a result. So here you see a robot tries to pick up a slippery banana. It requires a very specific action that is given by that red bar on the right. So when it starts out, it has very low confidence on that. But by continuously trying, over trials, it explores different actions and it figures out that is the right stage to focus on. But once it learns, it does not forget everything else that it has learned. And next time you give it a slippery, soft banana slice, it immediately knows how to do it. So by sacrificing one banana, the robot learned how to use this. But again, a drawback. Did you see the number of trials we used? 25 trials. That's a lot if it happens when we feed someone, right? So we thought, what was one of the things that was missing, and this is an open-ended problem, we are still working on this, but one of the things we're missing is we were only using visual information. But remember the key insight we talked about earlier? Multimodal perception is key. And so we thought, well, the fork is actually physically interacting with the food. Let's use haptic data. And so, but the problem here is, even though the robot has access to the visual data before it takes the action, the haptic data only happens when the robot is actually taking the action. So it does not have access to that initially. It only has access to that in later trials. So we call this as post hoc context. And the idea here is that we assume that the visual context, here in this case, our loss, is a noisy linear function of not only the visual context given by C, but also the haptic post hoc context. And so we jointly optimize this with a hard constraint that the mapping is the same, whether it's from the context and the post hoc context. And using that, we collected again the data with banana as well. Remember, it was taking almost 25 trials. And now when we're using this concept of post hoc context with adding haptics to vision, we actually found that it was theoretically it could do it at half the number of trials, but it took even practically it took much less number of trials than when we're using a model with just context only. And you can see this by the blue graph over time. Now, this is a result that will be presented in this ICRA sometime, I think on Thursday or something by my student Ethan, or like say the student I was mentoring when I was a postdoc at UW. So, well, so far I've talked about how learning can help in different tasks, right? But then what about, let's bring it back to the assistive scenarios, like to actually feeding people with mobility limitations, right? So are we the first people to work on feeding? No. Well, I mean, like, for example, Charlie's group has worked on feeding for a long time. Zachary himself, I remember when he first joined our lab, his intern project was on feeding. There are many other groups who have worked on feeding. There are also commercial devices, feeding devices that are existing on feeding. So what we did was we tried to evaluate where we stand. Where does our robotic system stand when we compare with a commercial feeding device? One of the most widely used devices is Obi. It's not very widely used, but still it's out there. And I saw John in our participant list. So John is from Kinova, and so Kinova is also distributing these Obi devices. So what we did was we went to we basically spoke with the stakeholders. So in assistive robotics, this is one key takeaway that I want all of you to take out from. So one thing that we learned is stakeholder inclusion, stakeholders, including stakeholders in the entire part of the process is very, very, very important. And so we wanted to do, we wanted to ask our stakeholders, the caregivers, the care recipients, as well as experts, occupational therapists, therapeutic recreational specialists, and everybody. And we compared and we found that what are the things that are important for an assistive system. Doesn't have to be feeding. It could be anything else, any kind of assistive system. We found that in addition to technical function that I just focused on and technology robustness, where adaptiveness comes into play and where learning can play a key role, there are also various other factors about information gaps, usability, social acceptance, and system integration that are very important when we really want to translate these technologies from labs to real homes. And so learning is important, but it's not everything. And this is what this workshop is about, where we want to find out where can learning help, where learning cannot help. So when we compared this, we found that yes, because our system had more intelligence embedded in it, it could adapt to more, it had more robustness, as in it could adapt to more uncertain situations. But this robot was being used by people with mobility limitations, and we hadn't done that yet so far with this robot. So we evaluated this with people with spinal cord injuries from different like C1 to C6. And again, as Yiannis mentioned in the previous presentation, the idea of technology's acceptance is not that simple, right? It's very, very contextual. It depends on many different things. For example, one of the key things we learned was, for particular this robot, this particular task, people with high mobility limitations had low expectations from robots. What do I mean by this? Where the way we designed this experiment is we said, hey, with autonomy in unstructured environments, there are bound to be errors, right? There are bound to be errors. So if errors happen in the world while being safe, even if their errors happen due to perception or planning, how will people react to it? And what we found with people with C1, C2 spinal cord injury, they said, even if the robot fails 1 in every 2 or 3 trials to bring up the food to them, they will still prefer this because this gives them a lot of independence. But people with like C6, C7 who had some mobility in the arm, they said they would not accept this robot if it does not perform beyond a certain level of performance. So it's very contextual, and there is no clear answer, and it depends on many different factors. That's the key message here. So one of the things, like here are some of the things people enjoyed. Like, for example, the technology allows me to do more things on my own, of course, giving me more independence, making me feel more free, and gives me something to look forward to. So it's because of comments like these that continuously tells us, gives us motivation to keep working on this problem. Here are some open data sets that you can use, leverage learning algorithms to be able to do various things. And just to conclude again, there are so many activities of daily living. Feeding is just the beginning. And also in feeding, we are just barely scratching the surface. But there's a huge scope, and the potential impact is huge. So this motivates us to continue to work on this kind of problem. Our goal as a lab and my personally is to enable robots to assist people with mobility limitations with tasks of daily living. And thank you so much for listening to my talk.
Thank you, Tapo. So we've got just a few moments for questions, if there are any. I think I saw one in the chat.
Oh, Charlie, yes, that's a good point. I did not cover that. So basically, we wanted to, so we gave them different conditions. We gave them conditions where basically full autonomous, where we artificially introduced errors during different stages, like errors during byte acquisition, errors during byte transfer, and things like that. And also we introduced them to conditions where there was partial autonomy, where they could select what strategies the robot should use. And so when they selected, the errors did not happen in those trials. So that was the relative comparison that we did.
Well, as a follow-up to that, I'm curious, by the way, very, very nice. Thank you very much. The details there, I could imagine, would make a big difference in terms of like, what is it that the person wants control over? And yes. I could imagine that the strategy may be a bit esoteric for a user, and that they'd rather exert their control over other aspects of the system, such as, which food to eat and when and such.
Yes.
What are your thoughts on that? I'm curious.
Yeah, excellent question and point, very well taken. Yes, there are so many ways that a human can intervene with these robots. This particular experiment that we did, so this is how we designed it. There were 3 levels of intervention if they chose one of the partial autonomy ones. The first was, so basically we divided these feeding into three steps: byte acquisition, byte timing. So byte acquisition is the robot autonomously decides how to pick up a food item. Byte timing, which is the robot decides when to feed the person. Like once it picks up, it waits for the person to finish chewing or something, and then decide when to feed. And then byte transfer, which the robot decides how to transfer the food. So there were these 3 stages. Now, what we did was what we mean by autonomous was the robot, if in a fully autonomous condition, the robot was autonomously deciding all of this. In the partial autonomy ones, the robot, the person had control over choosing either the byte acquisition part, like deciding which actions to take. And when I mean by action is basically, they were shown different high-level strategies, like go down straight, go at a tilted angle, things like that, and they would choose one of those. So it's not like low-level control over how the robot actually moving the robot. So they chose these high-level actions. For byte timing, it was about feed me now or wait, just this binary decision making. And the byte transfer was, again, there were a couple of few actions, like high-level actions that we decided. How we chose those actions, this was based on another human study we did where we found out how people fed other people. And we came up with a taxonomy, and that's how we did it. Now, your initial question about choosing a like a food item, that was universal. So that part, the way we did this, we had multiple interfaces. So regardless of whether it was an autonomous condition or a partial autonomy condition, people chose the item that they want to be fed. So for example, in a voice interface one, a person would sit in a wheelchair and will say, hey robot, feed me a strawberry. Or hey robot, feed me a carrot. Or hey robot, feed me a celery. And then in autonomous condition, the robot will completely do everything autonomously. In partial autonomy situation, it will give control in one of those sections. Does that make clear? Does it make sense? Yeah. Cool. Awesome.
Thank you.
Hi, Tapo. So we have one question from Ellen, who asked a question first. And then for the remaining people who have asked questions, how about, if it's possible, can you post them on Slack, and then Tapo will follow up with you on some of those questions. But Ellen has asked, can the approach you discussed be used to feed people with a spoon, such as soup? And if not, then what would be some of the challenges of accomplishing this?
Excellent question, Ellen. I would say some of the things would generalize, but then some won't. So for example, think about spoon and like soup, right? One of the fundamental things, if you see when I skewer a food item, is during the byte transfer, when I pick it up, the only thing that I have to think about is what is the orientation in front of the food, in front of the mouth, so that it's easy for the person to take a bite. But with the spoon and soup, I have to make sure it's a constrained motion planning problem, right? Because I cannot just go in any way because the soup will fall off, right, from the spoon. So obviously there is an additional challenge here is when you decide the trajectories, there is an additional constraint is the food item should, because it's not rigidly attached to the utensil, it needs to be continuously on the utensil to be able to do that. There are many other challenges, and I will answer all of your questions, Ellen, Amir, and Henry, over the Zoom chat. But yeah, again, excellent question. Yeah.
Wonderful. Thank you again, Dr. Tapomayukh Bhattacharjee.
Thanks.
So at this stage, we will move over to, we have now finished the opening session, Perspectives from Three Continents. And we'll move over to our first invited speaker, which will be Professor Henny Admoni. So,
thanks, Zachary. Hello, everybody. It's my great pleasure to invite welcome Henny to this workshop. Dr. Henny Admoni is an assistant professor in the Robotics Institute at Carnegie Mellon University, where she leads the Human and Robot Partners, or HARP lab. Prior to joining CMU, Dr. Admoni earned her PhD in computer science from Yale University under Skaz, as we fondly call him. She also did a postdoc with my postdoc advisor, Sid, when Sid was at CMU there. And and Henny's research interests include human-robot interaction, assistive robotics, and nonverbal communication. She's an excellent speaker, and I look forward to her talk. Henny, over to you.
Thank you, Tapo. That was a really lovely introduction. And thank you all for being here and for the organizers for inviting me. As Tapo kind of pointed out, there's a lot of confluence and intersection in the community. So I'm really glad that we're all here today and we can discuss our work. And I think what you'll find is that my work echoes some of the themes we've already been hearing today, like the importance of involving stakeholders in the interaction and the challenge of building multimodal user models. So today I'm going to talk to you about how human behavior plays a role in assistive and caregiving robotics, and why your models and the learning that you do should involve learning on the behaviors of the human and not just learning on the behaviors of the robot. And I want to start actually with a terminology quibble. This is the Caregiving Robotics workshop, but really when I think about the kinds of robots that I'm trying to build, I don't think about them as caregiving robots, because I think about the fact that these robots are actually designed to empower the individuals who are using them. So they're really built to let the users do more of what they want to do, rather than providing sort of top-down care. And for that reason, typically the robots are very tightly linked to the behavior of the user. So they are shared autonomy robots where their user maintains some teleoperation control, or they're otherwise tightly linked to the needs and interests of the user. And in particular, what my robots do, what I try to do with my robot algorithms is figure out what, when, and how people need assistance. And so the work that I'm going to talk to you about today is focused around these questions, not just building robots that provide assistance, but then also figuring out the right type of assistance at the right time in the right method to empower people to do what they want to do. And my argument for you is that in order to build these kinds of robots, we need to understand the human part of human-robot interaction pretty intimately. And so a lot of my work focuses on how do we understand humans in this human-robot system. Now, the type of assistance that robots can provide is really dependent on people's internal mental states. So people have beliefs, they have desires, goals they want to achieve in the world, they have intentions, they might have biases or preferences or confusion. All of these mental states exist invisibly inside people's heads, and those are what robots need to understand in order to provide assistance. And the challenge is that these are impossible to directly access. What we have access to as roboticists, as observers, are the resulting human behaviors that are controlled by the underlying mental states and are exhibited and are observable outside. So a lot of my work looks at how we can take observable human behaviors and use that to build models that interpret the intentions or other mental states that people have so that robots can act on them. That's half of the work, is figuring out how we can build user models based on observable human behaviors. The other half of the work, of course, is closing this loop to produce responsive robot actions. So it's not just enough for the robots to know when help is needed. We also need the robots to then provide the right kind of assistance. When I talk about human behaviors, I mostly talk about nonverbal behaviors, not because speech is not important. Speech is very important, but there's a lot of richness to the nonverbal communication that people provide implicitly when they're doing tasks. And so today I'm going to talk to you about eye gaze in particular, but also other kinds of nonverbal behaviors in general and their role in human-robot interaction. And when I think about responsive robot actions, today I'll talk to you about two different kinds of applications. One is assistive food retrieval. So again, some overlap with Tapo's work, and you'll see why in a minute. And the other is social conversational support. This is the outline of the talk. My work spans a number of different kinds of interactions. I don't only work in the assistive space. I also work on collaborative robots, robots that are fully autonomous, and so on. But for the sake of this talk, I'm going to focus on two specific areas. So the first is using eye gaze for assistive manipulation. And the second is how we build assistive sidekicks for users of AAC devices. So let me dive right into the first half of the talk, which is about eye gaze for assistive manipulation. This is work that I started as a postdoc with Sid Srinivasa, and his work that Sid has continued, and Tapo has continued, and it has branched in a lot of different directions. And so you'll see some overlap here with that work, but I've taken it in kind of a nonverbal interaction direction, which I think is complementary to the really excellent byte acquisition work that Tapo has done. So to give you a little bit of background on this challenge, assistive manipulation is the challenge of helping a user teleoperate a robot arm to perform manipulation activities, typically activities of daily living, like taking a drink of water. There are robots that are particularly designed to help with manipulation. This is an example of one. It is a Canova Jayco arm. I think I saw someone from Canova in the participant list. So here's the shout out. Canova makes a bunch of different kinds of robots that are commercially available, FDA approved in the US for assistive manipulation. And the way this robot typically works, for those of you who don't know, is it is attached typically to a powered wheelchair, it plugs into the battery of the wheelchair, and it's controlled by the user using whatever interface they have access to based on their ability. So this could be a 2 degree of freedom joystick. This could be a sip and puff, which is a straw that sits by your mouth and you either blow out or suck in, and that's your entire control signal. This could be a head array with buttons that you toggle with your head to switch modes, to switch access. Now, you can see very quickly that this is a really challenging control problem for this robot. The robot itself, if you think about controlling the end effector of the robot hand, you have a 6 degree of freedom control problem, because you have 3 degrees of orientation, pitch, yaw, roll, and 3 degrees of Cartesian space, X, Y, Z. And the input devices themselves have very few degrees of freedom accessible at a time. So the way this is typically solved is through modal control, where each mode takes the accessible degrees of freedom of the input device and maps them to output degrees of freedom. So for example, in mode 1, a user might control X and Y on the robot, and in mode 2, they might control the Z dimension and pitch and so forth, and they explicitly toggle between modes. Now, this is a really challenging way of controlling a robot. It's a great way. It gives people access to the robot, but it also can take a lot of time and a lot of expertise. What I'm showing you is a video from Laura Hertland's work in Sid's lab. And this is admittedly a novice able-bodied user, so not our target population, trying to pour a pitcher of water. So you can see that the challenge, mode switching is a challenging method of controlling this robot. And so the insight in shared autonomy is, instead of forcing the human operator to fully teleoperate the robot, what if we put an intelligent system in the middle? And that intelligent system could predict what the user was trying to do with the robot, and then take some action autonomously on the robot to achieve that goal while maintaining the user control through teleoperation. Now, Sid and his student in 2015 proposed this very nice shared autonomy framework based on a partially observable Markov decision process. I'm not going to go into the details of the system, but the system takes in continuous observations from the user input from the joystick, and then the POMDP is nice because it maps the user input in as observations. It allows you to represent uncertainty about the user's goal. So every single potential goal the robot has, or the potential goal the user has some probability associated with it of being the goal, being the correct goal that the user is actually trying to manipulate with the robot. And the system maintains a belief distribution over those goals, and then selects an assistive action that maximizes the movement towards as many goals as possible. And this system works nicely. So part of my postdoc was helping empirically verify that the system led to shorter task completion times, less user effort, in terms of how much people had to move the joystick, how much they had to switch modes, and increased subjective satisfaction with the system. So of course, on the left here, you see a video of a user selecting a marshmallow off of a plate using the shared autonomy system. And on the right, the user is using teleoperation, and he does eventually get to eat the marshmallow, but it takes a much longer time. Now, the shared autonomy framework is really valuable, but the one that I just told you about only takes user input in the form of joystick control. And the observation is that we're leaving a lot on the table if we're only looking at a robot in terms of how the user directly interacts with that robot. Instead, I want to expand the model of the user, that intent inference model, to include other elements of human behavior. And let me show you why. So here is an example video of a user from this empirical study that we ran, who is teleoperating the robot in shared autonomy mode to pick up a marshmallow. And now you can see on this user's face that there's a lot going on, right? So you can see where she's looking. You can tell that she's engaged with the system. You can tell if she's pleased or if she's frustrated. You can see when she has achieved her goal based on her body posture. She'll relax in a second. Well, she laughs first. There's a lot of information that we can capture, and actually, you can see that this user is wearing an eye tracker because we did record people's eye gaze as they were doing this. We started with eye gaze because gaze is known to be tightly linked to people's manipulation actions. So this is research that's now more than 20 years old that showed that if you track people's eyes as they're moving objects with their own hands, you see that their eyes will skip ahead to the next target of their manipulation before their hand reaches that object. And eyes will also linger on obstacles in a way that reveals what the challenging parts of the manipulation scene are. So here the white cross, or in the line drawing the little eye, represents where people are looking while they're doing this task. And you can see that the eye gaze kind of skips ahead to the different locations that are relevant to this task of picking up a block and touching it to the target. So we thought, okay, in our teleoperated system, perhaps we can do the same thing. If we track people's eyes, maybe we can use that eye gaze to predict the intent more easily, and therefore have a better intent prediction for our shared autonomy system. So we track people's eyes, as I showed you, and on the right, you can see the view of what it looks like from the eye tracker. The pink dot represents the focus of people's eye gaze, and this is kind of what the scene looked like when people were teleoperating our robot. What we expected to find was that people's eye gaze would precede the end effector position on the target, and that we would be able to use that eye gaze to predict people's goal. It's not surprising for anybody who's done a human study that we didn't exactly get what we thought we were going to. This is the way science works. Instead, mostly we saw that people's eye gaze fixated on the end effector of the robot. So people did occasionally glance down at their target, but because they don't have proprioception, and because they don't have spatial awareness, haptic sense with the robot, they were actually spending a lot more time looking at the robot end effector when they were teleoperating it than they were at their target. In retrospect, makes a lot of sense, but not what we predicted, which was a little disappointing. We were able to extract eventually their targets from those initial glances, but it turned out that the data was very thin for that. On the other hand, we did see something that we didn't expect to find, but that I found very interesting. So here again is a video of someone teleoperating the robot to spear a morsel of food on a plate. And in a minute, this person is going to make a mistake, which is that the robot's elbow is going to drop down below the level of the end effector, and it's going to be impossible for them to do the spearing action. Now, it's not their fault, actually. This is the internal kinematics of the robot have decided that the elbow needs to go here because they're only controlling the end effector. But you can see that their eye gaze changes when they realize they have a problem. And now, instead of looking at between the end effector and their target, they're looking at other parts of the robot that weren't involved in this task previously. And this change in the pattern of eye gaze can actually cue us to the fact that people are having trouble with the robot. So this is something we didn't expect to see, that instead of just telling us what the target of manipulation is, eye gaze can actually tell us when people are having trouble. So when they need the robot to pitch in assistance or not. We saw this in a number of different cases. So there are other types of kinematic failures that we observed. And there's also other types of end effector occlusions. And eye gaze can be used to reveal all of these problematic situations that robots can assist in managing that are outside of the specific task of acquiring a particular target. So that was pretty cool because it showed us not only that we can use shared autonomy to determine what goal people have, but also when the system should be helping people out. This is very relevant if you have dynamic autonomy, for example, where you want to increase the assistance in some cases and decrease in others. So I can't yet talk about our newest results. They're currently under review. So hopefully in a month, I'll be able to share them with you. But we do have a system that does use eye gaze to predict the next target. And we show that when eye gaze is present, it can actually be used to predict the target of manipulation much earlier if we use a model like a Hiddenberg model that takes into account the temporal sequence of eye gaze. When we don't account for the temporal sequence, when we just try to like count the number of fixations on a target, our model actually performs really poorly because people don't just look at their target, they also look at obstacles and distractors in the scene. So we do have some success in integrating eye gaze into the system for providing assistance in shared autonomy. If you are interested in this kind of data set, we've also open sourced the data set, which you can access at the link on the slide. So we definitely encourage people to download the data. It's about 5 hours of videos from different perspectives, egocentric and third person. We have all the robot information and videos of close-up videos of people's eyes. And if you do something cool with it, let us know, because I think it's a really interesting pile of data to work with. Okay, so that was some discussion about how we can use one particular nonverbal behavior, which is eye gaze, to build better user models for assistive robots. So that was kind of the top of the arc that I mentioned before. And now I want to talk about the bottom of the arc. How do we make robots behave in ways that are meaningful to people and assistive to people using what we know about nonverbal behavior? This work focuses on AAC, which are methods of alternative and augmentative communication. And in particular, we're looking at high-tech AACs, so AAC devices, computer devices. One of the most famous AAC device users was Stephen Hawking, who used a thumb switch and a blink switch in order to control his AAC device, type words out on a computer that would then speak out for him. Now, AAC, this is kind of what it looks like if you look over the shoulder of someone who uses an AAC device. The interfaces vary wildly by device and by user, but generally there's some way to type words. There's usually some kind of shortcut to particular pre-made phrases or pre-made words. And in this case, we have the augmented communicator, who I'm going to call the AC from now on, the augmented communicator, who uses, in this case, a joystick and a button in order to select words on her device to speak. Now, the challenge with AAC is that it can take a long time to type these words. And oftentimes people who use AAC will end up not being able to contribute to a conversation just because when people are speaking, multiple people are speaking, typically the rate at which the AAC user can contribute is slower and the conversation moves on sometimes, or it's hard for the AAC user to get a speaking turn. And so we wondered, how do we use technology to mitigate this? So let me show you an example of what it looks like for an AAC user to use her device to respond to a question. So here, the user is responding to an interview question.
She does
and
everything.
Her father is sitting next to her.
But she only uses it like a typewriter. And it's Bluetooth connected to the computer.
So you can watch the screen if she
this
starts typing.
She could use like that.
Mm-hmm.
But when your communication device.
And we're going to speed up the video. So she's still typing the answer to the question. And the father is kind of filling time, because we do that socially. We fill a conversational time. And eventually she gets to the point where she can contribute.
I can, but I haven't explored the internet.
She can use this. And we do go on the internet for all her updates.
Right. So as you can see, it's very common for augmented communicators not to get the chance to share what they want to say. Our insight is that we can mitigate this by viewing the interaction as a social interaction. So instead of trying to increase the throughput of the device itself, which a lot of people have done and is a really important aspect of the research. We instead view this as a three-way social interaction where we have an augmented communicator who is the speaker. We have a close conversational partner who knows the AC well and is doing things to try to maintain the AC's agency in conversation. And then we have some kind of third party who might not know the AC well, or who might not know how to interact with somebody who uses an AAC device. This is where the possibility for a social robot comes in. If we can understand the things that the close conversational partner does to increase agency, then we can build a social robot that can mimic those kinds of behaviors. And that social robot belongs to the AC, so it kind of gives them back some of the agency in the conversation. They don't have to rely on somebody else to provide them cues for agency. So if you think about agency as being affected by a variety of constraints, like how quickly people use their device, or the complexity of the task that they're trying to do, one of the big constraints is the relationship between the speaker and the listener. And so we investigated these relationship constraints to try to pinpoint where social robots might play a role in maintaining AAC agency. This is a two-part study. So the first part was a formative study that invited ACs and their close collaboration partners, or close conversational partners, to investigate how CCPs supported AC agency. And the second part was a co-design workshop where we invited ACs and their partners, and then movement experts who are puppeteers, to help us design social robots that would achieve the kinds of tasks that ACs actually wanted done with robots. So in the first part, the formative study, we invited 4 different pairs of people. There was a lot of diversity in terms of people's age, the kinds of input they used on their device, and their words per minute, most critically. So people's abilities ranged in words per minute ranged from about 3 words per minute to 22 words per minute. So a huge variability. Our question, we invited people in and we had them do a series of tasks, interviews, and activities with our researcher. And our question was really, how does the CCP in this process do things that support the augmented communicator? So I'll skip to the findings because those are the most interesting ones. One thing we found is that when asked a direct question, ACs tended to answer first, and then if the CCP was going to contribute, they would expand second. So in this graph, you can see the proportion of turns taken by whether that turn is first immediately after a question is asked, or subsequent after that first turn, by the different participant pairs. And for the first 2 pairs, you can see this mismatch. So as soon as a question was asked, the AC typically responded first, and then the second turn was typically taken by the CCP. So for example, if the third party asked the AC, do you use your device for social media? The AC would respond directly with a short answer, and then the CCP would kind of elaborate on that answer. And we saw this pattern appear a lot when the CCP contributed. Now you can see in the participant 3 and 4 that the CCP actually did not contribute very much at all. These were the 2 users who had very high throughput on their devices. And also they were the 2 users whose CCPs were paid aides rather than family. Now I'm not saying there's a causality here. I'm saying there's a correlation, right? They might be paid aides because of the high throughput. They might, I'm not claiming that, but we did notice that when the CCP was a paid aide, people tended to contribute more. The ACs contributed more than the CCPs, but also the ACs tended to contribute in a single modality, which was speech. Whereas when the CCP was a parent who ostensibly is closer and knows the individual better, the CCPs actually did a lot of interpretation of gesture and vocalization. So the AC didn't just use their device to speak, but they also used things like eye blinks, or like non-verbal vocalizations, like grunts, to communicate information that the CCP could then interpret. So this is another area potentially where a robot would be helpful, is to do that kind of social interpretation and let the AC communicate in the way that works best for them. One thing we did find is that when the CCPs were involved, sometimes their involvement led to missed opportunities for the AC. So here's an example script from our study. So the third party, the interviewer asks, for how long have you been using the Series 5? and the CCP kind of reiterates the question, yeah, how long do you know? The AC starts typing. So the AC first blinks, uses a nonverbal mechanism of communication, and then starts typing. And the CCP, because we're human and we're trying to fill conversational space, starts to speak. And it kind of goes on for a while as the AC is typing, reaches a point where the answer has been given, like the conversation has reached its sort of conclusion to that question. And so the third party interviewer asks another question, but the AC hasn't yet given their answer. And so they end up erasing their previous message, right? Which is awful. Yeah, I see you, Charlie. It's awful. It's so frustrating, and having to provide a new answer, right? And that's what we want to avoid. We want to avoid a situation where not only has the AC put in the effort to construct a sentence, but now they don't even get to share it. So our insight is we know that social robots can perform social conversational functions, right? We've seen research where robots can use eye gaze to hold the conversational floor for themselves. We've also seen research where robots can redirect the attention of someone using gestures or head movements. And so our interest is in how do we design a social robot that can use these kinds of social functions to reorient the conversation back to the AC, to indicate that they want to speak, and other things like that. Now, to do so, we developed participatory design, as I mentioned, with ACs and their partners, and puppeteers, because puppeteers are experts in movement and communicating through movement, which is what we wanted our social robot to do. So these folks spent a day together sharing the lived experiences of the ACs, talking about what would be most useful to have in terms of a robot assistant. And then the puppeteers came up with some idea movements based on the input from the ACs. So let's take a look at that. This is just the last part of the workshop where the puppeteers are presenting their kind of creative brainstorm ideas about how a social robot could be involved in AC communication.
Co-designing socially assistive sidekicks for motion-based AAC. In the third enacting part of our workshop, puppeteers improvised possible nonverbal behaviors for assistive robotic sidekicks. Behaviors in the workshop were a combination of motions that addressed attention, precision, and timing needs. Example, behaviors to invite the conversation partner to look at the AAC device. Behavior 1, imitate me. The puppeteers used Tammy's prototype to look at another puppeteer and then establish joint attention with the AAC device screen. Behavior 2, swirly look. Tammy's prototype is used to swirl around to call for attention and then point to the AAC device screen. Behavior 3, inviting arm. A puppeteer uses her arm to lure in another participant to look at the AAC device screen.
All right, so the ACs identified a number of different tasks that they wanted their robots to help them with. You saw in the video, invite partner to look at screen, which is the last task. They also said filling the silence gap, like I talked about, is really important. Letting the AC take a turn when conversation is streaming, and softening a message. So sometimes the mechanical voice coming out of the device can seem very flat and maybe a little harsh, so softening a message. As I mentioned, we had this two-part study, and actually we're currently, it's again under review, but hopefully soon, we're going to publish a paper with a case study where we developed a particular robot for a particular user and sent it home with him during the pandemic. He used it over Zoom, and with other people that he saw, like friends he saw outdoors, which was really interesting, and his family members. And we showed that that the device helped him, particularly with people who didn't know him well, to regain the turn taking. So to indicate that he wanted to take a turn. Okay, so that is, I think, all my time, and also what I wanted to share with you, this notion, again, going up a level, that in order for robots to be assistive, they need to understand the person, and in particular, they need to understand what, when, and how the individual that they're helping needs assistance. And in general, I look at how nonverbal behaviors do this, because the implicit signals that we get from nonverbal behaviors provide a really clear vision, really clear view of how robots should be assisting individuals. So obviously, none of this work is possible without a lot of collaborators, some of whom are in this Zoom room, and the funding agencies that make it possible. And I'll leave you with this one idea, that in order for robots to help people and empower individuals, they need to use nonverbal behavior to understand the what, when, and how of when people need help. Thank you.
Thanks, Henny. As usual, amazing talk, and let me clap on behalf of everybody. Any questions? Either put in chat or feel free to unmute yourself. So while people think about questions, one thing I was wondering, Henny, very inspiring work again, and I have been also becoming very interested on this, on the idea of using gaze as a way to communicate intent. And one thing I found when I was talking to people like with spinal cord injuries, like my group of users, that some people were not very willing to wear another extra device, don another extra device. While if we have a gaze interface that's on the table or something that's far enough, it's not that robust enough. Do you have any thoughts on how we can, what we can do about this?
Yeah, that's a great question. So in general, with all humans, but especially with people with disabilities, the idea of sensorizing them further can be really challenging. And it might be because they don't want to wear a device. It could be because, we had a user, I encountered someone with cerebral palsy once whose head movements made it really hard to do tracking on the device. Or maybe they don't have the head strength to hold up their head with a device on it. So there are lots of reasons why we don't want to do that. And I think that's a really interesting challenge of assistive robotics, that we don't get a lot of these signals for free. Now, particularly with eye tracking, it is getting better. We're actually having some success now with just an off-board Tobii eye tracker that we can put, just close to the user and calibrating it carefully. And we also end up, we're running a study right now, and we end up recalibrating occasionally. So we can monitor the quality of calibration and recalibrate on the fly if we need to. And I guess maybe that's where learning comes in as well, these personalized models for individuals. But yeah, good sensor data is hard to come by. This is also true if you go to speech, right? People with physical disabilities often have speech impairments. So our natural language models don't work well. It goes when you talk about gesture, right? People who are using these robots to eat are not gesturing because if they could gesture, they wouldn't need the robot to eat. So I think a lot of the work that we do in human-robot interaction more broadly is facing really interesting constraints in the assistive case. And I think that's what makes this area so challenging and so interesting to work in.
Thanks, Henny. I do see a raised hand. I think Shen, do you want to unmute yourself? Yeah.
Hi, Henny. Thank you for the great talk. I really enjoyed it. So my question is in the first half where you say you use eye gaze for the teleoperation task. I'm just wondering your thoughts on using eye gaze in tasks where human is not really controlling the robot, where, for example, in the assistive dressing task, where human is not controlling the robot. So how, or whether it's useful to use eye gaze in those scenarios?
Yeah, absolutely. Yeah, that's a great question. Thank you. And I'll point back to some of Yiannis's research that he presented earlier today, where I think you mentioned using eye gaze to measure people's cognitive load, or what people were distracted by or paying attention to in a scene, maybe for the autonomous navigating wheelchair. So I think eye gaze is very rich, is the point, and it provides us information not just about what people are trying to manipulate, which it does, but also about what they're worried about. So we have this notion. I have a student. This is the next thing he's going to do after he finishes his card user study, is try to understand how eye gaze reveals what objects in the scene people are most worried about manipulating around. So if you have fragile objects and non-fragile objects, can you tell which one is fragile by where people are looking. Similarly, can you tell what's distracting somebody? If you're going through a doorway, can you tell what part of the doorway they're most worried about hitting by looking at, so it's not where they want to go, it's where they don't want to go. Eye gaze also, like other parts of eye gaze, like pupil size, has been used to link to cognitive load. That's really hard to measure sometimes because it's also very affected by lighting changes. But as a gross measure, it can be useful to tell, how like stimulated people are. So yeah, I think there's a lot of different ways of using eye gaze that go beyond simply the point to the target method that we started with.
Thank you.
Awesome. So in the interest of time, let's keep all the other questions either in the Zoom chat or in Slack. And thanks again, Henny. Let's thank the speaker again.
Thank you for the questions.
So yeah, over to you, Zachary, for hosting the next speaker.
Mike, that probably helps. Hello. All right. Hello, everyone. So our next speaker is going to be Dr. Laurel Riek. She's a professor in the computer science and engineering at the University of California, San Diego, where she directs the healthcare robotics lab. So this is a really special lab. I've been watching it for many, many years, pretty much throughout my entire PhD. She's got some amazing research that she's been doing. And a lot of her research has been looking at human-robot teaming, human engineering, and assistive robotics. So Dr. Riek received a PhD in computer science from the University of Cambridge. And she's also received the NSF Career Award, the AFOSR Young Investigator Award, and the Qualcomm Research Award. And so with that, I'd like to hand it over to you, Laurel.
Great, thanks so much. Can people see my slides? I'm going to try to play them, and can you see the correct screen, which is just the slides and nothing else? You don't see the notes or anything?
Yes.
Like no notes? All right, cool. Great, well, thank you so much for the introduction. I'm a roboticist and computer scientist here at UCSD. I have appointments in the Department of Computer Science and Engineering, as well as the School of Medicine. And I direct the Healthcare Robotics Lab. And we build autonomous robots that are able to sense, understand, and learn from real people in the real world. And I'm really interested in both the fundamental and the applied problems to enable real-world autonomy for robots, including perception, coordination, and long-term learning. We situate our work within healthcare, and we solve real-world problems that arise in community health, home health, and clinical settings. So over 20% of the world's population has a physical, cognitive, or sensory impairment. This means that 1 in 5 people have difficulty doing many activities of daily living, as well as independent activities of daily living, which include planning for future tasks and managing medication or finances. Here's the big thing about disabilities, though. As a lot of people in the disability studies community will say, we are all only temporarily able-bodied. So becoming older, getting into an accident, getting COVID-19, a lot of these things can cause you to develop a temporary or chronic disability or health condition, which can affect your life. So thus, there's a lot more people that need help than there are people to provide it, and these numbers only continue to grow. Unfortunately, we live in a very ableist society, which places an inordinate amount of burden on people with disabilities and their families. It's immensely stressful and causes burnout. In a lot of countries in the United States, including the United States, a large majority of people with disabilities live in poverty, which adds to the stress. And professional caregivers, including clinicians, are also overburdened. And this has become even more apparent during COVID-19. So robots themselves are not going to fix all of these structural and societal problems. But what we ask is, can we use technology to lessen the burdens of systemic ableism, help fill care gaps, and reduce caregiver burnout? The answer is a resounding yes. There's hardly a greater application area for robotics than healthcare. So that sounds great, but how do you successfully design a robot-based health intervention? Anybody can build a robot, but the question is it going to actually be useful? Does it address a true need in the community? Is it a good fit for what they want? Is it accessible and usable by non-roboticists? And is it affordable? And finally, is this a Frankenstein robot, right? Is this something that people are actually going to be okay having around with them in their hour of need? As roboticists, it's really important to think through these topics. We're building systems that may be supporting people experiencing hardship. So you have to be really mindful of the larger context of care and what effects our robots might have. So taking a community health perspective to designing robots can really help to address these concerns and can help sharpen one's framing a bit. So there's kind of a few parts to this. The first question is, where is care happening? So in my work, we look at pre-acute care contexts. So these could include homes and community centers, as well as in acute care, such as in the emergency department. These are all very different contexts, and stakeholders are going to have very different goals and concerns. So the second thing we think about is what kinds of problems are we trying to solve here? And what are the types of ways our robots can provide support? So in homes, we focus on providing cognitive support for people with disabilities. And we also focus on providing respite support to family caregivers. In clinical settings, we focus on supporting clinical workers. So here we ask about how robots can help to offload low-level tasks such as material delivery or help provide support for telemedicine. We work very closely with stakeholders to ensure that our systems are well aligned with what they actually need and have that be the driver of our research efforts rather than being very technocentric in our approach. So what I'm going to do today is describe several efforts along these lines, which are aligned with our current and planned robot-supported interventions. So the first is looking at robots that can provide cognitive neurorehabilitative treatment for mild cognitive impairments. The second are robots that are co-designed with dementia caregivers and dementia community healthcare workers, focused on supporting people with late-stage dementia at mealtimes, as well as to support caregiver wellness. And finally, I'll briefly discuss some work we're doing on deploying robots to support clinicians who work in emergency medicine who are at a very, very high risk of burnout. This is actually going to be presented tomorrow in session T15, so a little plug there. So I'm only going to briefly talk about that one. So this first bit of work is led by my PhD student, Alyssa Kubota, who has a really nice review paper all about robots for cognitive neurorehabilitation in the annual review of control robotics and autonomous systems, which I encourage you to check out. So dementia affects approximately 50 million people worldwide. It can dramatically affect a person's cognitive abilities with symptoms ranging across the spectrum from reduced concentration in the early stages to inability to recognize friends or family in the late stages. People with dementia require highly personalized and unique interventions to support their health and independence. Mild cognitive impairment, or MCI, affects about 16 million people and can also cause many of these symptoms. And it's a prodromal condition that sits between regular aging and dementia. There are no pharmacological treatments for dementia, but there are behavioral and lifestyle interventions that can be effective. So one of the things that, one such intervention is developed by my colleague, Dr. Elizabeth Twomley in psychiatry, is called compensatory cognitive training, or CCT. CCT teaches people metacognitive strategies so they can learn to bypass impaired function and minimize the impact of the impairment on their daily lives. So for example, we might encourage someone to make a habit of placing their keys next to the door when they return home, or using strategies such as visual imagery or acronyms to compensate for memory difficulties. Traditionally, a human neuropsychologist or cognitive therapist will work closely with a person with MCI to determine their needs and goals and tailor the intervention to the individual. What we're doing is we're looking at how to adapt the CCT intervention to be delivered via robots. So the inspiration here is that robots can extend the reach of an intervention. And this is a theme across a lot of our projects. A robot is helping with the homework between sessions with a clinician. We also hope that we can one day extend this work to the point where the robot solely delivers the intervention to also help expand its reach. Right now, as I mentioned, there's 16 million people with MCI who could benefit from this treatment, but not nearly enough clinicians available to provide it. So these are a couple examples of me CCT delivered on one of our robots. This is a very, very early version, but I just wanted to give you a sense of what this looks like.
Hi there. It's great to see you. Here are today's activities. Please choose one to start. Let's start the color game. Let's get through 3 rounds. Here is round number 1. Now, select the colors in the order that they appear.
Okay, I'll just skip to. This is just another example of teaching lifestyle
Today we are
strategies.
going to practice a mindful breathing exercise. If you find yourself having trouble focusing today, try to match your breathing with the light on my chest.
Oh, did that stop? What happened there? Oops.
On my chest. If you feel comfortable, you can gently close your eyes, or you can keep them open if that is better for you. Do only what feels comfortable and safe for you today. I will also close my eyes along with you.
Okay, so that was, yeah, and so that was just like an initial prototype that we developed, and we're actually looking at using different platforms for this, but I just wanted to give you a sense of what the manual looks like and what some of the therapies might involve. So here, one of the most important features is that the robot-delivered health intervention is personalized and tailored to the individual and is well suited to their environmental context, otherwise it won't be adopted. So for a robot to do this, it has to be able to perceive the person's actions and behaviors, understand those in context, and adapt its behavior accordingly. So we ground this problem within 2 key contexts. The first is leveraging domain knowledge to enable clinicians to program and reprogram robot-based interventions. And the second is engaging in longitudinal preference learning so systems can change how they provide support to continually align with the users and the clinician's goals. So for the first effort, we created Jessie, which is a robotic system that enables novice programmers to express high-level specifications, to program robots using high-level specifications. And we employed control synthesis with a tangible front end to allow users to define complex behaviors for which we automatically generate control code. And again, the idea here is that you have a clinician who has a particular therapy in mind that they want the robot to do, like some of the examples you just saw. And without knowing anything about robots or programming, they're able to use this really straightforward, tangible interface, and that can turn into a whole program that can run on the robot. So we demonstrated this within the context of enabling and creating these personalized treatments. And what was really nice about this is that it's an open source way of accessing control synthesis. And we've demonstrated this on multiple robots now, and we're looking at scaling it to other platforms as well. So this really helps to support reproducibility and scalability and accessibility of building personalized robots for HRI. And you can actually check out the whole thing on our lab GitHub. So one of the things we need to be able to do, though, is to automatically tailor interventions and adapt them to people long-term, they need to engage in preference learning. So in recent work, we modeled this as a multi-agent, multi-armed bandit problem and designed a new method for preference learning across multiple users. So here you have multiple online agents deployed to perform similar tasks and receive similar feedback. And the analog could be, although we haven't quite reached this point yet in our research, but the idea is you could imagine having a system, one of these robots in multiple homes. And in a way, each night, perhaps you could share data across these, right? And figure out a way to learn across these different agents and look at how agents can improve their collective performance. And one of the things that was exciting about this was we looked at new ways to consider reward distributions by having multiple arms in the bandits play concurrently and adaptively aggregate rewards collected by different players. So to our knowledge, we're the first to develop such a scheme in a multiplayer bandit learning setting, which is exciting. So currently what we're looking at is extending our system to expand the ways it can be personalized to users and keep them engaged. So during this process, we're iterating on how it can be integrated into the lives of people with MCI, how they would interact with it, as well as designs for the tablet interface and different parts of the robot and so on. So maybe the robot could give somebody a high five when it touches its head, or maybe there's new ways to play games that are contextualized and localized within their homes that better connect with the therapy. So moving forward, we're going to continue to work closely with neuropsychologists and people with mild cognitive impairments and their caregivers to investigate appropriate features for modeling user preferences and abilities, particularly those that might differ from people without dementia. In our discussions with stakeholders, we're going to look really carefully at what appropriate behaviors are going to be for robots to exhibit in response to a user, as well as we're also exploring ethical and design considerations for designing for people with dementia. Just a brief note here, and we actually have a paper at We Robot this year where we're looking specifically at what does it mean to have a robot that's personalized, right? And what are those implications for people with cognitive impairments? We're also developing additional methods for adapting robot behavior to people with dementia longitudinally. And we're exploring methods that are suitable for a variety of preferences and abilities for these users, while also exploring how we can leverage expert knowledge, such as inverse reinforcement learning. Finally, we're going to implement these algorithms on physical robot systems to conduct longitudinal studies with people with MCI in their homes. We're currently planning an 8-week-long pilot deployment sometime this summer, and we will evaluate the efficacy, usability, and acceptance of the robot-based cognitive neurorehabilitation intervention. So I want to shift gears a little bit to looking at work that's a little bit more exploratory. So we're starting with the community first and then building the technology outward. So unlike the prior project that was a little bit more clinician driven, where clinicians had an intervention, they wanted to test it out and see how this would go, we don't really have an intervention yet. So what we're doing here is we're engaging in exploratory design work with the community so we can start to understand the shape of what future robotic technology in this space might look like. And this is specifically for people with late stage dementia, which is very, very different from people with mild cognitive impairment. So this is work led by my student Connie Guan, and she recently presented this at CHI. So people with dementia, particularly more in the late stage dementia, really struggle with isolation and loss of agency as their disease progresses. And similarly, informal caregivers are really overburdened, also can experience loneliness. They have a lack of social and financial support. And this is true worldwide. It's very, very hard to be a caregiver. So across a number of different disciplines, people are looking at ways to support both populations. And a number of researchers in this space adopt what's known as a critical dementia lens. And that examines dementia's social construction to understand embodied expressions of personhood via art, music, and other embodied experiences. Meanwhile, in public health, researchers are exploring how social determinants of health, such as racism, classism, sexism, and ableism, can impact health equity for both caregivers and people with dementia, and explore methods to address them. So our question then is, what lies at the intersection of these two approaches to dementia care, and how can we explore it within the context of technology development? So with this framing, our first question is, how can we design sensory and embodied technologies to promote agency in people with dementia and alleviate caregiver burden? And the second is, how can we incorporate community health care practices into dementia technology design to advance health equity? So we engaged in a 1.5 long research process, and this was in collaboration with a number of professional caregivers, dementia community healthcare workers, and dementia community educators. And ideally, we were going to include people with dementia in this particular project, but COVID made it a little bit more challenging, but we have in prior work. But one of the things we learned in our prior work was that meal times are very, very difficult. People with dementia often need repeated reminders or assistance to eat. And by the way, since there's a lot of people that work on feeding in this talk, these individuals do not need physical help with eating. It's more that they need cognitive assistance with regards to eating. So with this as our initial problem space, we did a lot of iteration on designs, and we wanted to really capitalize on the notion of familiarity, because that's very important for robot design. So it was important that the technology was something that was a familiar object, but had a little bit of, was like a roboticized object in some way. So we thought about a lot of things. We thought about kitchen types of items. We ultimately ended up with an old style radio that was intended to help during meals. So this radio will play music, and it has a robotic arm that can mimic eating motions. And this is an early prototype you can see here. And what we did was we used this probe in our later stages of research to get our participants to reflect upon their care practices, again, within dementia community healthcare settings, and then use this to help to envision future technology that individuals could have in their homes. So we conducted a thematic analysis of all of our data, which yielded 4 themes. So the first is affirming agency. So this is something that professional caregivers do to structure interactions to affirm the self-agency of the person with dementia. So for example, they might say, how do you feel about breakfast? Rather than what did you eat for breakfast? To let someone with dementia express themselves without having to rely on their memory. So there's a really interesting opportunity here to design interactions that are similarly tailored to reinforce the agency of people with dementia. The second theme was that emotional well-being and task assistance are interdependent concepts. One of the hardest aspects of dementia care is supporting the emotional well-being of the person with dementia during care. So a person with dementia might get frustrated at being told what to do, which frustrates the caregiver. And now you have 2 frustrated and stressed people. The care task is only all that much harder to accomplish. So here, a robot could use a sensory experience like music to keep the person with dementia calm during tasks and relieve some of that burden from the caregiver. Alternatively, it could provide prompts to the caregiver to help them reorient themselves and the person with dementia back to the care task in ways that are more effective. The third theme is the importance of using nonverbal embodied cues to communicate with people with dementia. So educators teach caregivers to use action mimicry cues instead of verbal explanations, as these are much better understood in late-stage dementia. So for example, seeing a caregiver eating can often jumpstart their actions and help them to follow along in ways that verbal prompts cannot. So robot designs that employ nonverbal cues to help communicate actions with people with dementia. Finally, our participants envision a number of roles that the robots could serve to support the dynamics between the caregiver and the person with dementia. So for example, mediating interactions as a motivator to promote positive interactions, or as a respite provider to give caregivers a break. Technology could also support conducting specific tasks, such as a facilitator that helps people with dementia perform tasks themselves, or as an educator for caregivers to model useful caregiving practices. So there's 2 key takeaways from this work. The first is the importance of designing robots for nonverbal embodied communication. This allows robots to adapt to changes in the brain, as language can be difficult in later stages of dementia, but sensory and embodied experiences are retained for much longer. Building this kind of community care practice into technology is one way designers can align the use of technology sort of with the work that's being done in community health. The other key takeaway is the opportunity to address health equity by designing for the community health system. So we've designed 3 areas where technology can support the ecosystem of health workers. The first is access, which we view in terms of how technology can help individuals access community resources. So here we envision how technology can make community resources like art therapy or support groups available to people in their homes. The second is education and supporting caregiver educators. So perhaps educators can provide caregivers technologies to help guide them during their care tasks and help reduce their cognitive load. And finally, the third area is expanding the reach of the community system, where technology can expand the ability of community workers to scale their existing support programs. Ultimately, we hope this work can provide one of many starting points for future design research to draw on community health frameworks to tackle complex social issues like health equity. Okay, so really briefly, I want to talk about a third area, which is in the acute care context, which is ways that robots can support the clinical workforce. So this is work led by my PhD student, Angelique Taylor, who will only be my PhD student for about 5 days because she's defending on Friday. And she's going to present this tomorrow in session T15, so please do check it out. I'm not going to steal her thunder, but I want to just briefly describe the work. So this is the emergency department. It is a high-stress, fast-paced, safety-critical environment. It is understaffed, underfunded. All of this has become worse during the COVID-19 pandemic. We've been working with local emergency departments on several projects over the course of many years. And one of the things we've learned is that they really want robots that can do things like deliver equipment to them. So, material delivery, in a lot of literature, we know this is a non-value added task, right? So this is a task that takes clinicians away from their job duty of treating patients. One other thing I want to mention is that in these spaces, emergency medicine workers get interrupted every 6 minutes. So anything that could even take away one interruption, to go get something could be huge, right? And so this is a great opportunity and interesting problem domain for robots to support work. So as you saw in this video, right, this is a non-trivial problem for robots. EDs are always changing. The hallways are crowded. There's patients being treated in hallways. There's just so many different people. There's noise, there's occlusion. There's just a lot happening, right? And this is a safety concern, because even something you might think, oh, it's a delivery robot, it just has to go from point A to point B. It's actually not, right? It's actually very complex, because your robot could in fact be a disruptor, right? It could potentially interrupt the delivery of care. So robots need to understand the context of care delivery, which includes the severity of a patient's condition, in order to make intelligent navigation decisions. So of course, if you see that if you see that a person is having a stroke or a heart attack, you shouldn't go that way, right? When you're doing your task. So, this were considered the following scenario. You have a healthcare worker, they want some supplies delivered by the robot. The robot wants to respond to this request and deliver supplies to the user as quickly and safely as possible. So to do this, we developed a social navigation system called the Safety Critical Deep Queue Network, or SafetyQN. And this is a very high-level overview of the system. And what it does is it detects patient acuity in video using inspiration from our collaborators with ED staff, as well as the literature. It was trained on thousands of videos from emergency medicine documentaries, because obviously we can't put cameras into the ED, but ABC can, right, for their documentaries. And these reflect the dynamic, chaotic, crowded nature of the ED. And it used these to estimate patient acuity score. Then it encoded patient acuity in the map state space, which uses a neural network to predict a path to avoid high acuity patients as much as possible. So spoiler alert, overall, SafetyQN achieved a path length and a high acuity penalty, significantly lower than comparative methods. And this was an exciting result, because it shows that SafetyQN generates the most efficient safety compliant path. So in the future, we plan to deploy SafetyQN on a physical robot in a medical simulation and training center to evaluate its effectiveness, the effectiveness of our system in close to real world settings. So here we can really explore how robots can help out professional caregivers in these challenging clinical settings. Unrelated to this, but another clinical application, sneak peek. What we've been looking at is exploring the deployment of these systems within the context of telemanipulation for telehealth. And I'm going to save that for another talk. Some of you might recognize that robot arm, but this is something we're really excited about, and I hope to have results to present to you at the next caregiving workshop that I hope you run again. Okay, so to wrap up, what I discuss are a few of our projects in pre-acute care, specifically within the realm of supporting people with mild cognitive impairment and dementia, as well as their caregivers in home settings. In clinical settings, I briefly discussed how we're supporting clinical workers via offloading low-level tasks such as material delivery, as well as to provide support for telemedicine. I will stop at this point, but I want to thank my amazing students who have done all of this great work that you've seen, as well as our sponsors, and I'm happy to take any questions that you have.
Thank you, Laurel. I'll clap for, again, all of the participants that are listening. So we have I believe about time for one question. If anyone from the audience would like to ask a question, either in the chat or unmic yourself. And then we will move over to the next speaker for time constraints. But we have room for one question if anyone would like. All right, so I'll shoot one, Laurel. So how do you perceive the affect or of robots impacting some of the results that you've shown here? So like the feelings that you get, that people get from like the visual appearance of a robot or its actions, how do you see that really playing a role in some of these results?
Sorry, was your question about the affect that humans are experiencing from the robots, or the robots displaying affect? Oh, okay.
Yes.
Yeah, I mean, I think that's a really good question. I think one of the reasons we use robots in these settings and not just tablets, right, is that the physical embodiment is very powerful. And so there's been some nice work showing this effect in a lot of different health scenarios. So this act of something physical that's in your space, you're much more likely to adhere. You know, one of the big problems with longitudinal health interventions, is that people don't continue to use them, right? They tend to be abandoned. And a lot of that is, we think one of the reasons for that is that they don't keep you engaged. And so there's some really nice work thinking about like how to maintain that engagement over time. And certainly if it's something that you enjoy, you're more likely to use it, right? And another thing we talk about in the health space is lowering barriers, right? So, so one example is that if you're a runner and, you have to go to all these efforts, to change into running clothes and find your sneakers and get your sweat, all this kind of stuff. It adds barriers. But if you lower those barriers, right, all you have to do is you wake up and you can just go out the door and go running. You're more likely to do it. And so in some ways, a robot that you enjoy interacting with is probably lowering a barrier to doing some of these tasks that can be somewhat arduous, right? I mean, doing that cognitive training, I showed you the color game, which was one of the easier ones. I mean, there's some tough stuff in there, right, that you have to do because you're really trying to teach yourself a lot of new strategies. And if you feel positive affect about it, that can be helpful. The other thing that we're looking at is, as we've talked about, there's a lot of differences between individuals, and some people respond really well to different kinds of feedback. And so I have a project in collaboration with Will Joyner and Carolyn Patton at UC Davis, where we're looking at robots for stroke therapy. And there, we're actually exploring different types of feedback, where sometimes the robot, completely different type of robot, but there we're looking at ways a robot can give negative feedback. So, but like, how do you give negative feedback, right? And what are the ways in which you can provide that? And that's another aspect, because there are people that will respond well to that, and that's another thing one can consider.
Well, thank you so much, Laurel. If anyone has any other questions, feel free to throw them out in the chat or ask in the Slack channel. We'll try to get them directed to Laurel as well. So thank you so much again.
Thank you.
It was wonderful.
Thanks.
Final round of applause.
Thank you.
Next one is yours.
Thanks, Zachary. Excellent talk, Laurel. So it's my great pleasure to introduce Brenna. Dr. Brenna Argall is an associate professor of electrical engineering and computer science, mechanical engineering, and physical medicine and rehabilitation at Northwestern University. She is founder and director of the Assistive and Rehabilitation Robotics Laboratory called the Argall Lab at the Shirley Ryan Ability Lab. She earned her PhD in robotics at the Robotics Institute at Carnegie Mellon University. Brenna is a 2016 recipient of the NSF Career Award and was named one of the 40 under 40 by Crain's Chicago Business. I personally have been following Brenna's work since my PhD, even my PhD. So I mean, it's a great pleasure to have her here. Brenna, over to you.
Thank you so much for the kind invitation, Tapo, and also for Tapo and Zachary and all the other organizers for the invitation to actually speak at this workshop, which is quite interesting. All right, let me go ahead and share my screen. All right, can everyone see that fine?
Yeah.
Yeah, okay, great. So as Tapo mentioned, I am a professor at Northwestern, but I also run a robotics lab at the Shirley Ryan Ability Lab, which is formerly known as the Rehabilitation Institute of Chicago, which is a rehabilitation hospital located here in Chicago. So the focus of my talk and the focus of my lab's work is on functionally assisted machines. So these are machines that have been designed to be operated by humans. They're not designed to be robots. And they were designed to be operated by humans in order to fill some sort of gap in function that is left as a result of a motor impairment. And we see a persistent challenge within this field of how to capture control signals from the human body in order to control these machines. These machines ubiquitously are more capable mechatronically than they are in terms of actually getting control signals to operate them well. So a classic example is myoelectric prosthesis, upper limb prosthesis in particular, where you are capturing control signals from residual muscles on an amputated limb, and you are recording muscle activity through EMG sensors, and you're interpreting this array of sensors in order to control an arm. But the upper limit on the number of channels you can usually, or not channels, but the number of classes you can normally predict is like 12 to 14, where each operates a half of degree of motion. So there's one prediction for arm extension, one prediction for arm flexion, for example, or elbow flexion and elbow extension. If we take the powered wheelchair, on the right, we have a diagram of level of spinal cord injury and how that maps to the amount of paralysis left on the human body. And this is sort of roughly mapped over to interfaces. These are control interfaces that are commercially available to operate powered wheelchairs, and which would be available with that level of motor function. So we see with a low level spinal cord injury, joysticks, 3-axis joysticks, 2-axis joysticks are available, and operating a powered wheelchair is a 2D control problem. You control speed and you control heading. So that's fine. You very easily can have the wheelchair become an extension of your own body if you can use one of those interfaces. As we travel up the spine, we see a switch-based head array, and we see a sip and puff, which is operated through respiration. Now, these are 1D control interfaces nominally. Sometimes they can be operated as 2D, but these are nominally 1D control interfaces, and they are what are called non-proportional. So if you blow harder into a sip and puff, you don't go faster, versus with a joystick, if you deflect it further, you do go faster. So that it becomes more challenging, but still feasible to operate a wheelchair with these sorts of interfaces. Here's an example of some video taken from my lab, and I apologize that the video seems to be flashing a bit. I also seem to be sometimes sort of frozen. Are you guys seeing that as well?
It's working.
Okay. Okay, and this perhaps with the quality of the video right now, this is perhaps not going to be so illustrative, but the takeaway here is that on the left, a joystick is being used. On the right, a head array is being used. And so you can see that the motions on the right are quite a bit more choppy and segmented. But that even with the joystick, the higher resolution and higher dimensional interface on the left, it's still a difficult task. Getting through a doorway, typically an ADA doorway with typical powered wheelchairs, you have about 10 centimeters of clearance. So this still requires a lot of dexterity in order to get through. And this participant had been driving a wheelchair for 25 years. So he was an expert, not necessarily an expert in our chair specifically, but he is a wheelchair driving expert. All right, so now as we consider something like an assistive robotic arm, someone who requires the use of an assistive robotic arm probably has a higher level of injury. Maybe they don't have full paralysis of their arms and hands, but some sort of impairment that would probably impede their ability to operate a hand-operated interface. And yet we see that the robotic arm is actually a higher dimensional control problem, right? So just to position the end effector of a robotic arm, not even to operate the hand or the gripper, is a 6D control problem. And so none of these interfaces actually can map to a 6D control space without partitioning that space and operating a subset of the control at a given time. And this is sort of typical within robotics as well. We don't have standard interfaces that are good at capturing 6+ degree control signals simultaneously. And this is sort of a persistent challenge that often the more severe someone's motor impairment, the more complex assistance they actually require. And that requires a more complex motions or more complex robot, which requires capturing more complex signal from their body. And yet their body presumably has fewer ways in which to issue that signal as a result of their motor impairment. And here's an example of operating a robotic arm in our lab using a 2-axis joystick. So this is a 2-axis joystick, which means we've partitioned this control space in this 6-dimensional control space in order to operate, be able to be operated with the 2-axis joystick. I paused it right here because now he's going to switch control modes, and you'll notice that he's wearing a utility cuff with a pen in his hand or a pen in the cuff, because he doesn't have the finger function to actually push that button. So he pushes the button, it changes the control mode of the robot. He starts to operate it, realizes it's not the control mode that he thought it was, has to push the button again, and then he continues forward. So functionally assisted machines have this sort of persistent challenge. In particular, we have the challenge of human impairment, that their impairment is actually masking and filtering the information that they need to give to the machine in order to control it. We have limitations of the control interface, where the dimensionality of the control interface to issue a simultaneous control signal in all of the dimensions is lower than that of the machine being controlled, and also continuity, whether or not it's a proportional control signal or not. And then we have this catch-22 of machine complexity that I mentioned, where oftentimes greater machine complexity is paired with greater motor impairment. And so capturing control signals for those to operate those machines is all the more challenging. So of course, a solution to this problem that we've been researching with it for decades, we the field as a whole, is to introduce robotics autonomy in order to help alleviate these control challenges. Now with these sorts of machines, we're usually talking about partial autonomy. So these end users typically want to remain in the control loop. They don't want 100% assistance. They want to remain a part of the control loop and controlling the device as much as possible. So I'm going to pause just for a moment here because this is a workshop on robotic caregiving. I want to make the case for partial autonomy as a caregiver. And the reason why is that we have people, for example, who can't be prescribed powered wheelchairs because they can't issue control signals with enough regularity in order and safety in order to keep themselves safe and the people and environment around them safe. We have other people, for example, children with CP who actually can be issued a powered wheelchair, but they're not allowed to bring it into their schools because there are concerns about their safety or the safety of the children around them. We have potential end users of robotic arms that can't operate the arms because of the complexity required of controlling the arm. And so for tasks like feeding or hygiene, personal hygiene, the arm is actually not accessible to them. So my argument is that when we have partial autonomy, that it empowers users to now perform tasks of mobility and manipulation independently that caregivers would otherwise provide, that partial autonomy is stepping in to a role that a caregiver otherwise would have been filling. And that when we do this, we reduce caregiver burden. Okay, so assistive partial autonomy. There's a lot of things to talk about, a lot of opportunities for machine learning within this space, and I'm just going to focus on two. So first is judicious control sharing. So we do not want to step in when the human doesn't want us there. We don't want to step in ways that they don't want. And so it's very important that we get this right, because if we do it at the wrong time or in the wrong way, we actually take away the human's autonomy. It's the opposite of what we're trying to do. It's worse than doing nothing at all. So one algorithm that we developed in my lab a couple of years ago, and this is in collaboration with Todd Murphy, who's also at Northwestern, and my previous graduated PhD student, Alex Broad, was a paradigm for safety-aware shared control. So the autonomous controller in this system only knows about system safety, doesn't know anything about the task the human's trying to achieve, and therefore it's applicable to sort of any task the human would be trying to achieve. Doesn't require being trained on task-specific approaches. It only knows about the robot system and what it takes to keep that robot system safe. So the first thing this algorithm asks is whether or not the system as a whole is currently safe. If it's not, we just issue the autonomy control signal that will put the system into a safe state. If, however, the system is currently safe, then we look at the control signal that the human issued, and we evaluate that for future safety. So is this, even if the system is currently safe, is this control signal from the human about to run the robot into a wall? If it will, we just reject the human's control signal, and otherwise we accept it. So there are a lot of details about how we are actually doing all of these different, the different boxes in this flow diagram. And I'm not going to take the time to go into the details of all these, but I would refer you to our wafer paper for those details. But a key point of this is that we're adding information. So we're replacing the human's control signal with the autonomy control signal only to ensure safety. That's the only time the autonomy is stepping in. And so we evaluated this first just within a simulation environment, a lunar lander, which is a very dynamic system. It's difficult to operate under 100% human control. And for all of these environments, we saw that task success dramatically improved when we had this safety-aware controller running. Sort of the result I want to spend a little bit more time on actually was that we took then these trajectories. So we had trajectories that were generated with only human teleoperation, and we had trajectories that were generated with human teleoperation, but with this safety-aware controller running. And so first is that this is 20 participants, and we see that with the user only, so no safety awareness, These are the yellow trajectories, and actually we're never able to complete the task, which is going down this narrow corridor in order to cross over the green line on the right. However, under shared control, just for safety, we actually are. We are able to complete the task, and that is the blue trajectories. Now, and so in this case, we actually saw that assistance was enabling demonstrations. So we were actually getting end users to be able to do something that they couldn't do without any sort of assistance running, but the assistance that we provided was task agnostic. It didn't know what the user was trying to do. Now, we also then tried to, we ran behavior cloning over these two sets of demonstrations, so the yellow demonstrations and the blue demonstrations, to see what would happen. And what we see for the blue demonstrations are these purple trajectories. And what we see for the shared control demonstrations or the assistance demonstrations is the pink trajectories. And so what, the pink trajectories achieve the goal. That's not particularly surprising because the demonstrations achieved the goal. But what was interesting was that we actually saw that the behavior cloning was able to keep its reproduction in the part of the state space that actually where the demonstrations happened with much more regularity. And so it actually was helping with covariate shift that we often see within learning, and it was improving shared control reproduction. And this is an approach that we are planning to implement on assistive robots sometime soon. Okay, the second project I'm going to talk about with judicious control was one where we actually let the end users themselves define how the control sharing was happening. So this is just an exploratory study with 4 spinal cord injured subjects and 13 uninjured subjects operating our robotic arm. And we were using this sort of classic control blending function, which is a piecewise linear function defined by these 3 parameters, where theta 1 indicates at what point assistance kicks in, autonomy kicks in, where the ratio between, I guess, all of the parameters would define how steep the slope is, and so how quickly or aggressively assistance takes hold. And then theta 3 is defining at what point when the autonomy is fully engaged, how much control does the human have left? Is it any control? Is it partial control? And we let the users sort of, it was again an exploratory study, so we let the users just give us verbal cues that would map to these parameters. So if they said something like, I wish the robot had stepped in earlier, we would modify theta 1. If they said, I wish the robot had stepped in faster, we would modify the slope. So here's a video, the same video on top that you saw before. And now the video on the bottom is with operating with the end user specified shared control function and with autonomy engaged. Now you'll notice that the autonomy is helping out in all 6 dimensions. So there's no reason to perform a mode switch. And there's actually, I won't get into that. I'm about to get into it. And so one of the interesting takeaways that I'd like to mention for this talk was, one is that we saw statistically significant differences between our spinal cord injured and uninjured subjects. And we saw these diminish as the autonomy was sort of more present. So we had a sort of minimal amount of autonomy and maximal amount of autonomy. And we saw that the differences became less marked, but they actually were still significantly there. And it was only with the end user customized autonomy or control sharing that there was no longer a statistically significant difference. Now, that's not the same as statistical equivalence, but it still is noteworthy. And the reason why I found this interesting was because the minimum and maximum actually represented the min and the max. So the customized control functions or shared control functions were somewhere in between there. So if you had asked me which paradigm I thought would actually eliminate differences between the 2 groups the most, I would have said max, because that's when the autonomy was maximally engaged, and the autonomy was the only thing that was the same across all of the subjects, but that was not the case. Second is that when we looked at the sort of user-directed optimization, we saw that they were considering something more than our standard cost functions. So one was that about 20% of the time, they actually had greater task completion time, so they were not minimizing for time. And about 40% of the time, they actually had more mode switches, so they were not minimizing for effort. And so, as a next step, thinking about how we could actually automatically extract this, whether or not we could, if this is something that we could actually learn from people, that's what we would like. That we could learn this without needing to query the person all the time. But whether or not we could, or what it would take to be able to do that is an open question. All right, The second topic that I'd like to talk about is the fact that we have masked and filtered information coming from the human. So these are the control signals coming from the human. It's masked and filtered both by their motor impairment and also by the control interface that is available for them to use. Now I put in this little teaser about can the autonomy trust the human? Normally in human robot interaction, we're talking about the inverse, whether or not humans trust autonomy. But I argue that for shared control systems, it's equally important whether or not the autonomy can trust the human, especially when the human has motor impairments. And the purpose of the autonomy is to keep them safe. We've done a bit of work in this area on the autonomy trusting the human. I'm not going to go into it here, but if you're interested, these are some papers to look into. Okay, so this idea, I'm talking about intent inference, but a little bit different, I'd say, than in two projects that had a little bit of a different take on intent inference. So the first is one where we are actually looking at control mode selection in order to maximize intent disambiguation. So in this case, it's that we're trying to figure out which goal the human is going for. And you can see in this example, I've got the red goal and the blue goal. And if the robot is to move along the x-axis between the two of them, that is much more intent expressive than if it was to move along the y-axis. And so this idea that control modes encode different amounts of information, or they are unequally informative with respect to revealing the human's intent, is something we wanted to explore in this project. So we added into our general sort of control sharing paradigm this intent disambiguation algorithm, where instead of pressing a button to switch control modes, the user could press a button in order to request the system put them into the control mode that will help maximally disambiguate intent. So it's sort of this idea of help me help you, that if you're willing to operate in the control mode that will help the autonomy figure out what you're trying to do the most, then the autonomy will be able to step in sooner and help you with greater efficiency. So we did a study with 8 uninjured subjects and 2 tasks, where one was a multi-step task with operating our robotic arm with 2 different interfaces. And you can see the interface mappings on the right here. So we have the head array where we had to have 6 different control modes. And then we had a joystick where we only had to have 4 control modes. And the head array was non-proportional, the joystick was proportional. And what we saw was that with the joystick, we saw fewer button presses for mode switches, but actually if we look at now the button presses that were out requesting the disambiguation, our number of button presses was about the same. But once we moved over to the head array, to the more limited interface, we saw a significant difference between the number of button presses that needed to occur. And we also saw a similar sort of difference when we considered just the one-step reaching tasks versus the multi-step reaching tasks. So the takeaway being that as control interfaces become more limited and tasks become more complex, this idea of intent disambiguation becomes more valuable. All right, the last bit that I'm going to talk about with interface awareness, or with extending the idea of intent inference, is the idea of interface awareness. So at the top here, we have sort of what teleoperation typically looks like. So you have some sort of task level action, like I'd like the robot to move forward. And then you issue a control signal through an interface that issues a control command, like to move a robot joint or a motor. And this typically is user interface agnostic. So at the time on the side of the robot control, if the velocity command was issued by a joystick versus a head array, we don't treat that velocity command any differently. That's what I mean by user interface agnostic. So here we were trying to really emphasize user interface awareness. And the reason why is because interfaces require physical activation. Even if it's a brain-computer interface, you're actually issuing electrical signals that are being picked up by this interface. If it's a sip and puff, you're issuing respiration. If it's a joystick, you're actually physically interacting with the interface. And so there can be a mismatch between the actual intended interface level command, like I intended to blow out, versus the measured interface level command. And so we explicitly modeled this in this work. So first is that we modeled stochastic deviations in user input. So the difference between these intended versus measured commands. And we did this by running people through this paradigm you see in the video and recording all this. So the models we built were user specific in this regard. And so what this would look like was that, for example, if I was currently in state X and I wanted to issue a hard puff on the sip and puff in order to transition to state Y. So it actually wanted to perform a mode switch. but it was detected by the interface as a soft buff, then what would happen is I would move forward an X instead. So this is what the ramifications of incorrect interface level actions can have. So we first modeled stochastic deviations of user input, then we did model-based inference of the intended input. And then within this, we came up with a customized sort of assistance that if we had a mismatch between the intended and measured signals, we would either filter the command or correct it. And I'm not going to present any of these results because I'm instead going to direct you towards my students' talk that's happening this Thursday, which is when this piece of work is actually being presented. But this idea of interface awareness is something we're starting to pursue quite heavily within my group. Okay, so that is about it. I will just, here I talked about judicious control sharing and also masked and filtered information. And I just wanted to present these bullets. I didn't have time to actually go through all of them, but last summer I actually gave one of the plenary talks at ICML, and this was sort of the takeaway from that talk, which was exactly looking at this question of how do you perform machine learning, or what's the role of machine learning within these partial autonomy assisted robotic systems. So one big challenge I'd say is, what feedback signal do you use for learning? Is it a reward? Is it a supervised label, a correction, a demonstration? Is it explicit? Is the person explicitly telling you how they would like the system to change? Is it implicit? Are you just inferring it from a mismatch of control commands, for example? And we do have work, we do have work in my lab going on in all of these areas. I just didn't have time to go into all of it here. Another is this idea of masked and filtered information. So we did talk about that some within this talk. There's also temporal considerations. There's the person's physiology. So are you seeing a difference because they're tired or because they're in pain? Or is it something that actually changed in how they're operating the machine and you want to adapt to it long term? There's a question of familiarization. All humans change in response to how we operate technology. And now we actually have the fact that people are there's a high probability that people are physically changing as a result of a degenerative disease, hopefully not, but it of course does happen, or as a result of rehabilitation, that they're regaining ability, and we need to be responsive to that. And then there's a question of the rate of adaptation. Is this a day-to-day or hour-to-hour change, or is this a change that's happening over time? And your response probably needs to be different depending on those two things. And of course, if you have an autonomy system that's adapting to a human, and then the human is adapting to the autonomy, you have actually human autonomy co-adaptation. And it's this moving target, and actually trying to perform adaptation appropriately within such a system or within such a paradigm is of course a challenge. With that, I will thank my current PhD students in my lab on the left, prior people in my group whose work was featured in this talk is on the right, and my funding institutions. And I'm also happy to take questions if of course there's time.
Thank you, Brenna. Excellent talk. Very educational personally for me as well. Let me applaud on behalf of everybody here. So time for questions, maybe a couple. You can either unmute yourself or put it in chat, and I'll be happy to say this to Brenna. Well, while people think about the questions, Brenna, one thing I was wondering, for the work on the end user customization, you had mentioned that some of the conditions, like you could not find any statistical differences in different levels of autonomy. And I was wondering, can you tell me some details about what was actually automated in the maximum autonomy condition versus what was automated in the minimum autonomy condition?
Yeah, so the only difference between the two was actually that control sharing function. So, so the idea is that with the minimal assistance, it would have been, the autonomy would have been stepping in the latest with and the least aggressively in terms of its slope, and the end amount of autonomy that was present would have, the human still would have been in control the most. And the maximal would be, the opposite of all those statements. But the actual autonomy controller was the same actual path planner and autonomy controller running. It was only the way in which the human and autonomy signals were blended and what was dictating that.
Got it. Thank you.
I had a question about the same study. I was just curious, they weren't minimizing for time. They weren't minimizing for mode switching. Did you have an intuition for what was driving the customization and their preferences? It's really interesting.
I agree. And, you know, we've actually been meaning to do a more thorough follow-up to this work, which, you know, this now was published, I think 4 years ago. So we obviously are behind on that, but I don't. It's not something that was clear from the, it's not something that was clear from the questionnaires that we gave. And, you know, it wasn't something that occurred a majority of the time, right? I think it was only 80% of the time they were optimizing for speed, and, you know, 60% of the time they were optimizing for mode switching or for minimizing effort. And so it's something that looking into that, actually, I did have a student who built up these sort of like physical interfaces, like sliders for people to be able to sort of on the fly modulate how much assistance they were getting. And we always planned to run that study, and other studies took priority, and now he graduated. And so it didn't end up happening. But that's a question that we are interested in as well. And, you know, to be fair, I think also it's, you know, I've been someone who's been advocating for longitudinal studies for quite some time. I'm always a little bit hesitant to say how much we can actually glean or infer or state as truth from a one-session study where there's this huge novelty factor. And so whether or not these results would hold or persist or still show up after in a longitudinal study is something that we would need to run that study to learn.
Great, thanks. It makes a lot of sense.
Thank you. So in the interest of time, let's, if you have any questions, feel free to use the chat, but let's thank the speaker again. I think—
Alrighty, well, we are back. So welcome everyone again back to the ICRA 2021 workshop on learning for caregiving robots. We're about halfway, a third of the way done for today. And up next, we've got two contributor presentations. The first one, which I'm happy to introduce, is by Antonio. Let me pull it up here. So Antonio is a PhD candidate at ICRA in Spain in the Perception and Manipulation Group, advised by Dr. Guillem Alenya and Professor Carme Torres. And his research interests are in the area of human-bot interaction and human-centered design for older adults with cognitive impairments. So with that, I'm happy to hand it over to you, Antonio.
Hi, everyone. Thank you for the nice presentation. So today I'm going to talk to you about framework, Cursor, for learning in situ personalized robot assistance from therapist demonstration and knowledge. So the incidence of cognitive disability has soared in the last decades, and it is projected to rise even further in the next 20 years. So as the older adults population increase, the number of healthcare professionals is decreasing. So social robots are promising to bridge this gap and be employed to augment the effectiveness of the therapist and reduce their workload. This particularly applies to repetitive tasks, for example, cognitive and physical therapies. However, how to replicate therapist expertise in terms of social interaction and intelligence in a robot in a fully autonomous fashion is still an open research question. So in order to address it, we envisage that a robot needs to have the following key features. So it must learn quickly, as the number of interactions are usually very limited. It needs to balance assistance in order to keep the user engaged over time. And it needs to lessen therapist workload. So in this work, we propose an approach that focuses on addressing the three key features mentioned before. So to do that, we introduce active learning agent assisted behavior, Cursor. So this is an interactive framework which enables the robot to actively learn in a fully autonomous manner, personalized patient-specific policy. So to design, as well as to evaluate Cursor, we collaborate with Fundación ACE, that's a research center in Barcelona, specialized in the treatment of patients with dementia and Alzheimer's. So what we did is basically start observing how therapists administer cognitive training therapy to patients with mild dementia and Alzheimer's. And what we want to do is to model the therapist behavior on the robot, and then I will show you during the presentation how we did that. So the framework consists of two main phases. The first step of the online learning phase is to gather data. So we use an hybrid approach in which we combine the therapist's prior knowledge of patients' cognitive ability on the given task by getting this information through questionnaires and gathering data from the interaction between the therapist and the patient during daily therapies on that task. Then we encode this information in the form of probability, and we build what we call generative Bayesian model of the patient and the therapist. So in this way, having the model of the patient and the therapist, we can basically simulate interaction and generate episodes. So we already introduced this idea of using a simulator for generating data in HRI in our previous work at Roman in 2019. And here we extend our work using Bayesian network to build this kind of models. So as soon as we generate the episodes with the simulator, we compute the reward function by means of max causal entropy inversion for learning, and therefore we learn the policy using the value iteration. So after that, we embed the policy on the robot. In this way, we have an initial robot policy for the specific patient. So at that point, we complete what we call the offline learning, and we start the online learning phase. So where basically we start, the robot starts providing assistance to the patient, and after each session, the generative models are updated with the new data. So this is the stage where the framework basically decides if to stick with the current model or to reshape the policy in order to challenge or help a bit more the patient. And it does and this is done by checking the user average performance during the session with the human therapist and comparing it with the current performance. According to that, we generate new episodes, and then new reward functions learn and policy as well, and then we plug that in the robot, and it's going to employ in the next session. So in this work, we aim to address the following research questions. So the first one is, would the social assistance offered by the robot match the therapist's preferences? So here we want to evaluate the relevance of the assistance provided by the robot. Then the second research question aimed to evaluate how the user performance change when the assistance is provided by the therapist or the robot. And the third research questions aim at to evaluate the ability of the robot to adapt and personalize the assistance to the patient over the sessions. So to do that and to evaluate our research question, we first carried out an observation study in which we assessed using a user-centered design approach, the robot's behaviors in terms of interaction modality, and so voice, gesture, and facial expressions, and levels of assistance. And as you can see in the table, we defined seven increasing levels of assistance, and these are the levels that basically the robot is going to learn during the sessions. I'll show you in the next slides some of them. Then we conducted two user studies in a healthcare facility where patients were used to have their cognitive therapies. The study involved 22 patients, and each patient played 6 sessions with the assistance of the human therapist and 6 sessions with the assistance of the robot therapist. In the study with the therapist, the objective was to gather data that would later on be used to initialize the model of the patient and the therapist. And after a few weeks, then we conducted the study with the robot, in which we aimed to at evaluating our research questions. So I will present here the kind of robot of assisted behavior, as well as the interaction the robot was capable of providing to the patient. So the robot was just, for example, saying to the patient that it's his turn to move a token. Then it was reminding the rule of the exercise. That is very important because usually patients with at least mild dementia, they forgot the rule very often. Then the robot can encourage the patient. And then we have additional levels that are more supporting, that involve also gestures. For example, here the robot is pointing the line where the correct token is, for example. Then we have an additional level of assistance where the robot is pointing a subset of the solution. And here, for example, the robot, this is an additional level of assistance when the robot is basically pointing to the right token to move. And finally, the last level of assistance is basically where the robot picked the correct token and offered to the patient. So besides of that, the robot was also capable of providing some kind of back-channel cues, as you see here. So as soon as the user picked the token, then the robot provide a kind of feedback, combining head nodding, verbal, very short sentences, and changing its facial expression. And finally, in order to avoid that the user just gets stuck and after he makes several mistakes, the robot can pick the correct token and move in the correct location. So with respect to our first question, we requested the therapist to level each robot action with a score between 1 and 5, where 1 is I completely disagree with the robot, and 5 I completely agree with the action of the robot. So as you can see from the figure, the therapist score in some way improve over time. And basically after the fourth session, the robot's behavior almost converged to the expected behavior of the therapist. So in some way, the robot was able to meet the therapist's expectation. So with respect to our second research question, we aim at comparing the average participant performance during the six sessions, whether the assistance was provided by the human therapist or the robot therapist. And we found that the patient were actually, when interacted with the robot therapist, they were performing better. And if you look at the figure on the right, they were also required less assistance. Finally, in order to assess whether the robot was capable of keeping the patient performance constant, we compute for each patient the standard deviation of their performance over the 6 sessions. And we did in both the cases where they were assisted by the human therapist and from the robot therapist. And you can see from the plot that the robot managed to keep the patient performance constant during these sessions, and even more so than the therapist. Additionally, in order to evaluate further how the framework accomplished the task of tailoring the assistance over the session, inspired by the work of Park, we computed the correlation between the policy in terms of state action pair, where the idea is basically to assess to what extent the robot policy for what patient is unique with respect to all the others. And in this case, low correlation means higher personalization. And you can see that the therapist really strive to adapt the system to a given patient and eventually ended up to adopt the same strategy for different patients. So despite our results are very interesting, we would like to point out some limitation and that can motivate future work. So we classify them in methodological limitation, but also on developmental limitation. In the methodology, we mentioned the sample size. I think the study is more or less like most of the other study on the field. The number of participants is, let's say, sufficient, but we would like to validate that on a larger population. Also, we believe that this study might suffer from the novelty effect. So maybe a longer study should explore the patient engagement and their acceptance over time. And also the other limitation that we want to point out is that we only rely on a single therapist. So we should try to concentrate or replicating in this study with different therapists. And regarding the developmental limitation, so we were using just contextual information, so not affecting state of the user was included. We didn't include any speech recognition and dialogue management. The task was designed in a way that was kind of low-dimensional task. And the robot was, let's say, mastering to who and what action of assistance provide, but we didn't learn when actually to provide the assistance. And just as a recap, so what I presented here is a framework that enables robots of in situ learning in a fully autonomous fashion of personalized patient-specific policy using a user-centered design. And with that, I want to conclude with a special thanks to the therapists, nurses, and patients from the SENACE, because this study was carried out during the pandemic. And so we made a lot of effort, but they really help on making it possible. So I'm glad to take some questions here on Slack or on the chat. Thank you.
Thank you, Antonio. Wonderful, wonderful presentation. Thank you for sharing that with us. So there is definitely time for questions. I think I see a couple in the chat, but others are welcome to ask other questions verbally or in the chat as well. So Michelle has asked, how do you control for ordering effects in your study? That's the first question. How do you control for ordering effects?
Okay, I guess the order effect means, if I understand the question, it's mainly about, because we started with the user study involving the human therapist, and then we went to the robot therapist. So I guess this is the order that
kind of like mentioned. Has the participant learned more about the task by working with?
Yeah, so I would say that there was sufficient time for them to not learn the task, even because we have to think that these people are older adults with mild dementia, so they were even forgot the instructions and what to do after like 5 or 10 minutes. So I don't think. Hi.
I was just going to ask you, how are you? What evaluation did you do for in terms of cognition? Because not everyone with mild dementia does forget, and there is some learning that they do have the ability to do. So did you evaluate their cognitive working memory ability? So you had a definitive number so that you could compare?
So I'm not sure if I can completely answer to your question, but the cognitive evaluation was up to the hospital or the care facility, and they provided us with the patients. I know that they were so they did a pre-assessment of their cognitive, let's say, their cognitive status, and they decided to include that. So we have, I think there were like several tests. I'm not really an expert on that, but they assessed that with several tests, standard tests, and they decided to include that in the experiment.
So what
sorry.
I'm going to interrupt for a second. What I would suggest is that, because I'm a little suspicious of the result from this perspective, is that if you don't have a way of measuring the impairment of the persons, so you measured it, but you didn't consider that in your interpretation of the results, to either control for the level of impairment of the group and also the amount of memory that they already had intact. So you can't for sure say that the no learning occurred, because I don't know what the amount of mild disability or mild cognitive issues they had. So I would just, I really love what you guys did. I totally think it's awesome. I just would suggest that that you actually really pay attention to the information given from the therapist in terms of the level of working memory function that each patient had, and use that maybe as a covariant in analyzing your data, because it will make a difference, period. And there's no if, ands, or buts. So if they weren't uniform, say everyone was on the same level, then I'm now even more suspicious of the results. So just to throw that back at you guys, that you really need to pay attention to that and use it as a covariant in your analysis.
Thank you. Thank you for your feedback.
Thank you, Michelle. If you couldn't tell, Michelle is an expert in this area, and so she has wonderful feedback to provide on how to improve many human studies. Great questions, and thank you again for the talk, Antonio. Is there any other questions that others have? Otherwise, we'll move over to the second presenter we have.
If there's time, I'm just curious qualitatively how people with MCI responded to this type of robot and these kinds of interactions.
Yeah, it's actually, it's very interesting because they were, so let's say the average, I think I had the slide, but I think the average age was around 75, 76. And the oldest one was a lady of, she was 89. So she would not even imagine what a robot was. So they had like 15, 20 minutes of interaction with the robot. So they were asking questions. So we had this warm-up section in order for them to familiarize with the robot. Even because we were like worried about because there is kind of physical interaction. So the robot was also moving. So we want to be sure that they were understanding why the robot was moving and why the robot was going in that direction. But I have to be honest, they were very, very excited about the interaction with the robot. That's why I mentioned the novelty effect, because I don't know if then like employing the robot for a few months doing the same repetitive task, maybe it's going to be a bit boring for them.
Thank you.
Thank you. Very interesting.
Welcome.
The final round of applause for Antonio, Andriella, and we will move over to the next speaker.
So it's my, thanks, Zachary. It's my great pleasure to introduce Paola for the next contributed talk. Paola is a PhD student at the Edinburgh Center for Robotics. She works in the Robust Autonomy and Decisions group at the University of Edinburgh and Social Robotics group at Heriot-Watt University. The group is also known as RAD group. I love the name. Her work focuses on incorporating the concept of grasp affordances to improve autonomous robot manipulation. So with that, it's over to you, Paola.
Great. Thank you very much for the introduction. Let me see if I can successfully share my screen. I think you see it now, right?
Yes.
Cool. So as Tapo kindly introduced me, I'm Paola. I'm a PhD student at the Edinburgh Center for Robotics, and what I'm going to present to you now it's better. It's our latest piece of work, which was in collaboration with the University of Washington with Maya Kakmak in her lab. And we worked on a piece for affordance-aware handovers with human arm mobility constraints. So the way that we've motivated our work is that in those assistive scenarios where you have a carer helping a receiver and they are giving them out objects, it's very important for the carer to actually analyze how to grasp the object correctly so that the receiver can perform a task successfully afterwards. So in the example that we are seeing here, for example, the lady wants to drink from the glass of water. And as we can see from the carer, he is carefully pouring the water in the glass and making sure that she has enough room to grasp the glass of water. So how can we actually transfer this to robotics so that we can actually have an assistive robot in these type of scenarios? What we propose is to create an optimized model that considers robot grasps along with object poses that later on we can put inside a user study so we can grasp the preferences actually from the humans that are actually going to use this proposal, and then encapsulate these preferences in a statistical relational model. This with the purpose that we actually learn and generalize these different handover configurations, and so that the user in the future can actually just input their arm mobility level and what is the task that they want to perform afterwards. So we are going to start by explaining how we are actually modeling. I'm not sure if you are seeing all of the pop-ups. I'm guessing you are. So I'm going to start by explaining how we are actually modeling this cost model. So we have started by discretizing the space of the hand, where we have different, we're going to call them variables, and we're going to call them as well constants. So the constants are going to be those things that we can actually not control, such as the human hand pose, the human face pose in the space, or the grasp that the human is going to choose in order to grasp the object. And the variables are going to be those things that we can actually optimize, such as the robot grasp and the object pose that it's going to hand over the object. In that regard, our hierarchical cost model is then going to be formed of an appropriateness cost, which is going to consider how the robot is going to grasp the object so that the human has enough room to grasp the object in the area where it's going to perform the upcoming task. And for this, we are going to consider the affordances. For the affordances, we use our previous work, which was published in 2019. In which we analyze the semantics of the object to discretize what are the affordances that this object has. The second cost is going to be safety. And safety, what considers is that the robot needs to be far away from the human so that it doesn't hit it. But also we need to consider reachability. So it's a trade-off that the robot needs to be far away, but the object also needs to be reachable to the human. In this sense, since our final goal is to actually ask people if they will prefer or if they will feel comfortable using our method, given that they have an arm mobility limitation, we want to compare our proposal with proposals that are out there. So in the first scenario, we have those proposals that consider that the object has to be as safe as possible, so far away from the human. That means that the human needs to extend the arm to reach the object, and it doesn't really consider the appropriateness of the object, since this wasn't the goal of this set of the literature. And for resembling this part of the state of the art, we consider the 25 diameters from the human. The second set of methodologies are those that are kind of in the middle. They consider already the affordance because they have been already some human-robot studies that, some human-human studies that consider that when the giver is actually thinking about the upcoming task of the receiver feels more comfortable in the interaction. And this one, since it is in the middle, we put it to be at 50 centimeters from the human. And method C, it's going to be our proposal, which goes as close as possible to the human hand, given that it has a mobility limitation, and it also considers the affordance of the object so that it can perform, the human can perform the upcoming task. In this sense, we created an online user study in which we put 5 different objects, these 5 different objects with their most common affordance. And here we hypothesized on the human grasp, and we also detected prior to the rollout of the experiment, the robot grasp. So at this point of the presentation, it's worth mentioning that actually we couldn't do the experiments face-to-face because at the time it was at the beginning of last year, the pandemic, and to assure the safety of the participants, we decided to go online with this. So we created animations with as many textual descriptions as possible. Here are some examples of the different objects and the different animations and how they looked in the user story, of course, with the descriptions that I was showing before. In this regard, now it's interesting to think, how would we know actually what is the arm mobility limitation of the human that is actually looking at the screen, and how do we calculate this? So we started by hypothesizing, okay, if somebody has an arm mobility limitation, probably what they want to do is to perform the fewest of the motion as possible and to feel the more comfortable. This means that they have to perform the minimum, or they have to do a minimum effort to actually go and grasp the object. So theoretically, out there in nature, in different type of literature, it says different type of formulas on how you can calculate the effort on the joints of the arm and what are the joints that are supposedly to be most useful by the arm when you are reaching out for an object. With this data, we actually calculated that with our method in comparison with the state-of-the-art ones. The human mannequin that we had in our animations actually performed less effort. However, we want to ask the people how they did this or how they perceived our method in comparison to the other ones. For this, we created the online study in which we kindly asked the Chest, Heart, and Stroke Scotland organization here to help us with some volunteers so that they will have some assistance looking at the animations and somebody else to be replying at the questionnaire. And also we recruited 250 unique participants from Amazon Mechanical Turk, for which the specifications were more like if you know somebody or if you are a carer and you can help us out. And we actually wrap different participants from different ranges, which was actually really useful, so we could actually compare between different levels of arm mobility. And in this regard, we showed different animations at the beginning of the questionnaire where the participant could actually see what is the motion that they could perform, and they could identify with one of these motions and then say like, I think I move like level 1, or like, I think I move like level 4 of the animations. And those are the ones that we are putting it at the beginning of the questionnaire. For the actual questionnaire, we started with the first section where what we want to know first is to know what is actually influencing the perception of the different handover methods. Is there arm mobility in relation with the handover method, or is the method itself? So here we perform a two-way repeated ANOVA, in which first for the arm mobility, we saw that specifically for people that classify themselves to be between higher mobility level and lower mobility level, that responses were significantly different. Whereas when it comes to the method itself, this difference was not so much across all the perceived options that we offer them, which was safety, comfort, and appropriateness, but it was more about the different methods. So, for example, for the perceived appropriateness, all of the participants saw that the appropriateness was different between the first methodology that we showed, which was method A, and the last methodology that we showed, which was method C. At this point, it's also worth mentioning that these methods were shuffled across the different animations, so they were not in the same order, so that we wouldn't hint the participants what was going on in the study in this regard. Another thing is that we wanted to know what was more important than in this sense for the participants. Most of the participants, even if they were in high levels of arm mobility, they thought that it was more useful to have a method that actually considered the appropriateness of the handover, in which case they actually prefer method B. But for people with lower arm mobility, they prefer our method, which will come close to the hand. So it's actually very curious to see that for participants with higher mobility level, the most important thing might actually be safety rather than being the shared effort, where the shared effort is that the robot actually moves more towards the human. And for low arm mobility, it's almost the opposite. It's more important for them that the robot tries to do most of the motion, no matter if it takes forever for the robot to reach to the position, for example, than being natural or appropriate. We also asked them an open answer question where we just ask their opinion on their handovers and if they will feel comfortable with an assistive robot being there, helping them by handing them objects over. And it's also very curious that for people that was in levels of high mobility of their arm, they said yes, that it will be okay for them and that it will be useful, but we found many constants or many as long as or if these many conditionals before they actually say it will be useful. However, for people with lower mobility levels, we almost didn't have these conditionals, and their opinions were more like it was very helpful, it will be very useful, and I would totally feel comfortable with it. Ones that we have what we want to know and what we want to do at the end is to see if the assistive agent can actually generalize different handover configurations depending on the input that you put in the system of your arm mobility level and your upcoming test. So for this, we expanded our previous work published in 2019 of our statistical relational learner, and we input the features of the robot grasp and the object pose that we learned from the handover configurations extracted from the online study. In this regard, for the real execution of the robot, our vision will be to have actually the real robot there, have external cameras that actually detect the hand pose, the human face, and then the robot to perform the handover object. But as I mentioned before, given that we started these experiments early last year, we actually were not able to perform them face-to-face. So what we did was a couple of animations just to make sure that it was actually affordance aware of the handover configuration, different objects, and different inputs of human arm mobility. And we tried ourselves in the lab with different inputs as well, and different objects. Also, I believe there is another one with some more examples of also objects that we were using in the online study with the animations. And of course, we would like to thank the co-authors for their amazing help on this work, which got into RAL, and it's going to be presented a bit more extensive tomorrow. You are more than welcome to assist to, and here you can find more information about our work so far, and I'm guessing that it's time for questions.
Thank you, Paola. Great talk. It's time for questions. Do you have any questions? Let's see the chat. Well, while people are thinking about questions, I do have something, Paola. Yeah. So I was wondering the way you had, so if I understand correctly, you had the human grasping regions, and then you took the complementary regions as your robot grasping regions, right?
Yeah.
But like if I think about human handover or something, not all complementary regions could be viable options for the robot to grasp.
Yeah.
And so I was wondering, have you thought of, actually using human handover data to figure out where the robot should grasp for these handovers, instead of just taking the complementary regions?
Yeah, actually, that's very good, and it's part of our future work. Unfortunately, we didn't have enough time to collect all the data, but the initial thought was to actually do human studies with those, extract the grasping regions of the object, and then relate them with our previous work so that we can segment those objects with their affordances and relate this mapping, and then proceed with the different robot grasping. And it is true, not all of the options for the robot were viable. So actually it took a couple of trials before we managed to put the robot into action.
Thanks. We have a question from Michelle in the chat. So what about, Michelle, feel free to unmute yourself if you want to ask the question directly.
Sometimes my dog is in the background.
Oh, okay. Okay, no problem.
So I keep it low, but really interesting work. And it was curious what you observed about the folks that were high functioning and those that were low. And I definitely would agree with the observation, and it jives with what I've seen. The one question I had was, and I think this is interesting, is how would you kind of adapt what you're doing to those with mobility issues? Because you're really looking at reaching, but grasping is about gross and fine motor dexterity when it comes to the hands. And while, and that's usually the last part that people recover. So, the reaching part is the easier part. And the dexterity in the hands is the part that, especially if you're thinking about the population that you were just describing, arthritis, rheumatoid, all kinds of things will end up impairing dexterity. So how are you thinking about that? I mean, it seems like the assumption is that people had good grasp. And
yeah.
But with the population that you're targeting, I'm concerned that the good grasp assumption will not necessarily be true.
Yeah, that is true. And that is something that we thought whenever we were actually thinking about doing the face-to-face experiments. And we were thinking on actually including this type of grasp test that there are out there for different testings on not only the robots, but the human, when you can do either the pinch grasp, the power grasp, and what type of grasp can actually be related to the person. However, we didn't make it to that point, but it's a very good point. Not everybody will have the same option of grasping, not the same force in their fingers to grasp. For example, if I offer them this object and the area that it's this, which will be a very bad actually offer. But what if I did this? Not all the receivers would actually be able to do this. And it's something that we thought about. Unfortunately, yes, we didn't have time, but it is for sure in our future work considerations.
Great. So I guess in the interest of time, again, let's cut short the question session. But if you have any questions, feel free to put it in the chat, and I'm sure Paola will be here to answer your questions.
Yeah. Thank you.
Thank you again, Paola, and let's again give a round of applause for Paola. Great talk. I guess the next session is our panel discussion, first panel discussion of the day. So Zachary, you take it from here.
Absolutely. So we have a great group, a very exciting group of panelists here to discuss the roles of learning and autonomy in robotic caregiving. Right? It's kind of, it sometimes can be considered an idea that's kind of out there, right? It's not hugely mainstream yet. And so I think it's a great time to start investigating what are the right roles for machine learning to play in these types of physical or social assistive contexts, right? So in terms of panelists, we've got 4 different panelists here. Professor Henny Admoni, Professor Laurel Riek, Professor Dongheui Lee, and Professor Yiannis Demiris. We'll be our 4 panelists and kind of talking about some of these ideas of where should learning play a role in caregiving. And so to start off here, of course, For audience members, feel free if you have questions just about this idea, this notion, feel free to put them in the chat and we'll read them to the panelists. Or feel free to unmute yourself and you can ask the panelists yourselves. But just to get started, I'll pitch a question, which might actually be kind of two questions here, which is, I think the primary question, which is, what problems in robotic caregiving and assistive robotics are well suited for machine learning to solve? And kind of the opposite of that is, are there aspects of caregiving that data-driven methods are not appropriate for? Anyone like to start us off?
Okay, I'll jump in and you know, please you know, correct me if I'm wrong in any way. I think that that's a great and really difficult question, Zachary. I think that in a way, almost all problems in assistive robotics are great for machine learning, right? We have people are different, so actually we couldn't possibly not have learning in our systems in order to do intelligent caregiving or empowering the humans. So I think that the fact that the system cannot come out of the factory helping everybody, you know, directly, and you have to have some sort of learning in order to customize to the particular person, I think that makes it a good target for machine learning. At the same time, that actually makes everything in caregiving robots to be a tough problem for machine learning, right? The fact that we have such a variation between different people, everybody's different in terms of preferences, skills, disabilities they might have, what do they want to get out of the interaction? I think that makes also learning to be a really tough thing. We don't have enough, in a way, learning data, or we couldn't afford to take the humans and impose on them this learning system that will take a very long time to learn, right? So there must be ways that we can leverage statistics among many different people in order to learn more efficiently. But I think that's pretty tough, and we need much more longitudinal studies to achieve this. I don't know whether that answered your question, or was just a long way of saying we don't really know.
Yeah, no, this is good. I also, let me just make a quick break because I realized I missed something. For any attendees that just joined us recently, I just want to quick point out who actually the panelists are here. So there's a couple of faces. So you just heard from Professor Yiannis Demiris. He's from the Imperial College London. Just give a wave when I call your name out. Professor Dongheui Lee, she's joining us from TUM in Germany, so the Technical University of Munich. She's an associate professor there. Professor Henny Admoni, she's joining us from Carnegie Mellon University. And Professor Laurel Riek, she's joining us from UCSD. Awesome, that was it. Continue. I just wanted to point that out for everyone in the audience. So it was definitely a good start. Yeah, it's kind of essentially we don't really know, but I think there are probably aspects that we kind of know, right? Like sensing does play a pretty big role in where machine learning comes into play, right?
So if I may say a word here, I think in general, intention recognition is a really great topic in this domain. In general, intention recognition of user is also very important for other domain like collaborative robots. Whatsoever human-robot interaction domain is important, but especially for the caregiving robots, maybe the difficulty adds on more because of the sensor data we usually deal with is not going to be that great. It's kind of very noisy in some sense, or there might be containing a lot of some signals which we usually do not want to have it as well because of some characteristic of some kind of disease as well. So certain things would make it even harder to make this intention recognition there. And then I think, so this a lot of individual preference, the personalization items, I think also Yiannis mentioned. So these things will be very great topic for the machine learning to apply in the caregiving robots. One thing I think what would be what human, what people should be the concern should be, not to think always machine learning will be the best tool ever, especially because we were dealing with a lot of tight interaction between human and robots. And we have to ensure the safety always. So not always a data-driven approach would be great, actually, because then you're not gonna have any great policy to robot to perform or something for the unobserved space, like a state-spaced area. So I think people should a bit take care of this very much underlying safe controller together with some kind of data-driven approaches. Yeah.
I think that's a really great point, that in any human-robot interaction, getting data from humans includes a safety risk that other kinds of learning don't. When you think about robot learning, often you think about systems that are working in isolation that can, pick up an object 1,000 times and or try to pick up an object 1,000 times, and if they fail, that's fine. But when you work with humans, suddenly safety becomes important. And then building on that point that Dongheui made, like with people who have disabilities, the inputs become very heterogeneous. So you lose a lot of the consistency that you see sometimes in like typical populations, and that means that it's an even harder problem. One thing I do wonder is if we want to separate out learning about people, which is like personalization, like what Yiannis was talking about, and learning about robots, which is like the classical robot learning, a robot training its own algorithm. And if they seem like different things to me, and I haven't yet worked through why, but it seems like those are two distinct kinds of learning that we do in this field.
I also want to just plus one Dr. Lee's comment. I don't think machine learning is always the answer, right? And I know that everyone's really excited about machine learning, and that's wonderful. I think it's a fantastic tool for a lot of problems. I don't think it's the only problem, and it's helpful to think a lot about what it is we're trying to learn and how we're trying to do that learning. The other thing I want to suggest, this workshop is on learning for care, it's framing it around caregiver robots to support, presumably to support people with disabilities and to provide caregiving support to people with disabilities. But I'd like to suggest an alternative framing, which is that I think it's helpful to think about caregiver robots for caregivers. So we work a lot with caregivers, and they are really, really, really overburdened. And particularly considering, like I said, I work with people who have advanced stage dementia, right? And so the level of caregiving is quite high, particularly when those individuals are being fully cared for at home, and there isn't always other alternative support. It might just be like a partner or a child. And, when we talk to them, like sometimes they want things like robots to help with housework, like doing the dishes and taking out the trash and cleaning and cooking and shopping, and like, those I think those are plenty fun robotics problems to do. And indeed, those are caregiving tasks, right? Like those really help aid the caregiver. The caregivers don't mind, the person with disabilities might mind, but the caregivers don't mind doing ADL support tasks. They don't mind cooking and bathing and supporting the caregiver. Like that's okay. Like they're okay with that. What's hard for them is to support the person with disabilities while also kind of managing their household, managing their own health, which is also often problematic. And so I feel like that could be kind of a nice way to think as well about ways that we can, other types of ways we can support caregiving in general in other kinds of ways. So.
Yeah, I think this is excellent point. So related to this, like we have, like this has come up in each and every one of your comments. What I'm wondering is like, well, yeah, like there are some areas where machine learning can help, whether it's helping care recipients or caregivers, like helping to reduce caregiver burden and everything. But at least from my own experience, what I've found, well, machine learning depends on data, right? And it's just extremely difficult to collect data, especially in these kind of scenarios. Like people, like if I have to do an experiment with people with mobility limitations, it's just very difficult to collect the relevant data, the data with end users or intended care recipients and caregivers. And I was wondering, what are your thoughts on how we can help, how should we obtain data for these kind of scenarios? Or are there any ways where maybe we do not need or maybe we should select our algorithms such a way that they are not very data hungry? Like, what are your thoughts on these things? Any of you, really?
I think data from real people is always best, because as anybody who has ever put a robot in front of a person knows, as soon as you do that, you suddenly discover things you had no idea to expect. That said, simulation has given us a lot of opportunities to kind of bootstrap some of our algorithms initially, and people have made really good use of simulation, especially in the last year during the pandemic. But I do think that we need to be very careful about the unbridled enthusiasm about data hungry algorithms. I think it's very, very easy to see a lot of success in other domains like natural language and computer vision and want to apply those algorithms in our space. And sometimes they work really well, but the data issue is a big problem.
Can I say something?
Yeah.
No, not on the panel, but I've been thinking about this a lot since I sit in a PM&R Department of Physical Medicine Rehab Department. And one of the things that I think we may need to do as engineers kind of is to partner with the clinicians, because they collect tons of data. Now, there's always a HIPAA and the IRB rule, but one of the things we recently have been doing for like a different study that we're doing, some study with infants, is the clinicians are collecting this as a part of their natural process, and oftentimes they have secure database where all this data is sitting. And I think what we might need to do is to consider going to them and creating like a retrospective, analysis. Can we retrospectively, create an IRB where we analyze your data sets? These actually exist, and they're actually also data sets of peds and adults and people with disability that folks have been collecting for a long time. We just need to find out where they are, and then maybe instead of necessarily trying to create our own. I know there are two parts that I'm answering. One is the human data sets are kind of there in terms of understanding people's interaction with people with disability. And then maybe from there, we could infer how to then to learn a lot about how to then put a robot in front of the same person with disability. So I throw that out as an option or something for us to consider, is that we can actually, the data set is there. We just need to partner with the clinicians to access the data set in a way that secures the data and the privacy.
And I think, especially when I totally agree with those comments. And then I think also one thing that we do a lot of, because we're putting robots in people's homes for long periods of time, and these are people with cognitive impairments. And as much as we've tried to not put anything on the internet and not use any kind of speech recognition, for example, that's farmed out, we think a lot about like, how can we design for privacy from the get-go? So for example, rather than putting cameras, which nobody likes, nobody wants, we think, okay, can we do stuff with wearable sensors, or do we even need a camera, right? Can we, like, we're trying to infer cognitive states, for example, can we do that with just their interaction with the robot or with like a wearable, watch or things like this, right? We think about doing, if we're going to do speech, recognition, which a lot of people really want because they don't like to touch tablets. Can we do all that locally, right? Do we have to be sending it all out to a web service, or can we do it locally? We think a lot about how to keep our data safe. I can tell you for this project, the MCI project, where we're trying to learn across participants, we're still finishing the completion of the database, right? Like we spent a really long time thinking about how do we collect the data? How do we store the data? How do we transmit the data from the various robots to the database? How do we keep the database secure? You know, like we walk through all of this. We walk through a lot of the red teaming, like what happens if this data is, you know, if someone breaks into this data, if this data is shared, you know, and so and we think, okay, if the database is compromised, there's no personal information that's stored in the database. So that's okay, right? Like, so we kind of like walk through a lot of those types of scenarios to try to consider ways, you know, really thinking about data minimization, like only collect what you actually need, right? Like I can tell you for one of our projects, like there's like billions of parts of like the ankle of like how it moves that we could collect, right? But like, do we really need that for the task, right? Like, so sort of thinking about like, what's the bare minimum of data we can collect to still solve the learning problem? And that's another way you can help to get around some of those challenges as well.
We also, I was just going to also suggest, as we as a group thought about consolidating and grouping our data, you know, so that we form group databases that then people don't have to kind of build their own every time they want to do something, that we maybe join together and share data and put it into a group, a natural depository, you know, for adult, you know, stuff with kids, stuff with infants, stuff with whatever, so that we're building our own kind of data sets that I know we have to deal with HIPAA and all that stuff. So, but if we de-identify them, they may then be able to be used across, you know, different universities by actually, you know, writing kind of a universal IRB or something like that. But that's something that maybe we could consider, because I definitely think that there's a need.
So excellent points. Yeah, I completely agree that with everything that has been said here, like including, I think this would be a nice initiative to think about in terms of like having a common repository where we can use each other's data to be able like to access it. I think that's excellent. Yeah.
One question I think about when with like a shared repository is would we need a shared problem that we're also looking at, right? A shared context in order for the data to be accessible or usable across different organizations?
Good question. One of the things I think is there are shared contexts, for example, already existing. You know, several people mentioned dementia. You know, just, you know, if you had databases on people with dementia, different levels of cognitive information, where you also collect the motor, I mean, the cognitive scales as well, so you could figure out who you could search the data and say, I'm looking only for mild, I'm looking for severe, blah, blah, blah. A lot of people do a lot of work with stroke. So you can, you know, do work around stroke. A lot of people do work with cerebral palsy. So I think an organizing process would need to happen, but it's almost self-organizing, because there are some groups that are similar issues. You know, are you doing work with multiple sclerosis? And so you could argue for that type of organization, that then within it, we can search for the type of specific person that you might be, or the specific group of data that you might need. Just a thought there.
This is very, very, yeah, I mean, this is, I do like this idea, kind of a shared database of data that can be accessible across groups. And then this kind of brings up another question, which I have, which is kind of related to this, which is if you have this shared database, or even if you want to build a shared database, or in general collecting data, what are the right approaches to collect this kind of data, given the fact that safety is really paramount for these kind of assistive robotic systems? It's kind of like a chicken or egg problem, which is where we want a system to be safe, but that system may not be safe yet if it doesn't have the data that it needs to collect, right? And so how do we just kind of in general, what are your thoughts on how do we provide safety guarantees for these types of systems that rely or leverage learning? Can they do part of their job without learning, and then learning helps fill in the gaps or improve later on? Any ideas on this? How do we ensure these kind of systems or thoughts, or are there, when is the right time to apply learning to ensure the system is safe?
Yeah, I think that's an important question. Laurel and I are actually on a paper, co-authors on a paper, I think, that came out in the Communications of ACM, came out. It's in, I don't know, it's somewhere in the printing process. That basically emerged out of a workshop on formal methods and HRI. And can we use formal methods to support the development of HRI algorithms? And essentially the crux of that workshop, what I took home from it was formal methods are wonderful. Like you can use verification techniques to ensure the performance of your algorithm under certain constraints, as long as you can model your human. And it turns out that's really hard. But if you can model your human, if you can describe the human in the correct way, then absolutely you can guarantee safety of these algorithms. And then the challenge then becomes, how do you model the human sufficiently so that you can ensure safety of the algorithm while also letting it explore enough to get the training data?
Yeah, and actually it was kind of funny because it was this workshop that the Tadas Kreskazit and Guy Hoffman and others organized. And so you had these like formal methods people who were asking us, okay, like all I need is a model of humans, like give me a model of the humans and then I can make the robots safe. And we're like, well, yeah, humans are complicated. Yeah, so we spent a lot of time talking about that. But you know, one of the other things you can do that we thought of, so for example, for our deployments in the home for people with dementia, we thought a lot about like, what kind of robot is this going to be? And originally we, a lot of different ideas. And one of the first things we thought about was not making it mobile, right? It didn't have to be mobile for the tasks we want to do. It's providing cognitive assistance. It's okay for it to be on a desk somewhere. And, because tripping hazards are a real thing, right? Especially when you're working with older adults. And, we all know as mobile robots are not very safe in general. So this seemed like it didn't need a manipulator. It didn't have to pick anything up, right? It was talking to people. So it was fine for this to be a tabletop robot. And again, it depends on the task, right? So for the robots we're doing for, that we're putting into hospitals that are providing, telehealth, for example, we need a manipulator, right? We need a mobile manipulator for that problem. It's really dependent a lot on the context. And then the other thing is to think about the materials that you're making the robot out of, right? So one of the things we've learned from some of the people with advanced dementia is that they really hate technology and they tend to smash it and break it. So we're thinking for those populations, like I showed you that Spoonbot robot, that's laser cut out of wood. It's got like a cheap Arduino in it. Someone smashes it, and we're also playing deployments of that robot over the summer. Someone smashes it and breaks the robot, no big deal. It's like $30, no problem, right? So I think, thinking really thoughtfully about, and yes, that robot isn't particularly capable. It's not doing anything super sophisticated, but it is serving the need that's for that population, right? For that intervention. So kind of thinking through, like, are there ways you can design the technology such that it inherently is safe for the person? And yes, that may limit its capabilities in terms of mobility or manipulation, but you may not need mobility and manipulation depending on the task that you're trying to solve.
I think, oh yeah, Dongheui, sorry.
Yeah, so if I add here about how to ensure the safety guarantee for the learning, this is a very difficult task actually, and then some of you already mentioned, if we have the model, yes, the problem can be solved. There are a lot of techniques, so you can show the, passivity or convergence whatsoever. But of course, usually we do not have it. But we usually have also approximate model. So what is a good approach, at least the current time at the current stage is like you use approximate model for the underlying control or the robot's behavior, and then do the learning on the residual dynamics. And that can be, you can do a lot of data-driven approaches, or you can do the data-driven simulation in the simulator, and very few rollouts in the real world. That allows very efficient learning, and also it allows robot to explore the new policy in a very safer way. So this is the some new trends going on in the learning domain, also in the reinforcement learning domain. So I think this would be very good also to apply. Yeah.
I think these are great points, and this actually segues perfectly to one of the audience questions by Shen, where he mentioned basically, like, especially when we don't have a model for the human, and you learn a human model, how do you validate that learned human model is actually correct? And Shen, feel free to unmute yourself if you want to ask the question directly.
I think if I just maybe answer to here, of course, it's really about how to make this to human model. It is a very complicated issues, and depending on what your task is about. If task is about something like a balancing, then typical approach is you just model inverted pendulum and then adding on the nonlinearity on top of it. It's really depending on what kind of level we want to model. And then there are tons of tools there. And how do we validate our learned model is correct or not is again depending on your task problems, right? You want to see that you put inputs, right? For example, your current state and your some control actions whatsoever to your model, which can be the human model now, and predict what is gonna be output. And then you compare that with the real data. And then your predicted data outcome matches well to your real observed data. Then this is a way to validate the model is, learned okay or not, right? This is the typical, yeah.
Makes sense, Dongheui. So, sorry.
Actually,
yeah.
I wanna augment that. Yeah, because I think that's right. And yet I want to suggest that correctness is the wrong target. I guess. Like, I think correctness doesn't mean anything in this case, because what we see over and over again, and what a couple of people mentioned in their talks, is that people change over time, right? The reason we need long-term studies with robots is that the way people use their robots will change as they gain expertise, as they gain function or lose function, as the robot abilities and assistance changes. And so I think a lot of learning presupposes this notion that we're learning something that exists that doesn't change, this kind of ground truth. And the reality is that people change. And so correctness might not be the right goal to chase. You might want a different metric, which is just like effectiveness or something like that. I also want to highlight something that Brenna pointed out, which I thought was so fascinating, that shared autonomy in her system actually gave people the capability of providing good demonstrations to the system that they couldn't do on their, like, without assistance, which is so interesting because it's the opposite of what we found, which is that when we add shared autonomy to the system, people stop giving us inputs because they let the system take over a lot of the effort. And now we actually get less human input than we expected, than we were kind of like building our systems to accept. So there seems to be both directions, this duality of the kinds of information, the kind of data that you're going to get from people as they use the systems.
So interesting, really. It's multifaceted for sure. So I mean, it's almost 2:20 in the Eastern time, and we are running late for lunch. So let's conclude the panel discussion here. I would like to again thank the panelists and the audience, like the people who spoke up for this excellent discussion. I myself learned a lot. To conclude, basically, what I feel like takeaways are that yes, machine learning can be useful for robotic caregiving. First of all, we have to define what we mean by robotic caregiving, and then machine learning can be useful in various different aspects, especially whenever there is adaptation involved or intent recognition is involved and things like that. But there are also issues with getting data, and as well as providing, and safety. And for getting data, at least there could be ways of brainstorming about coming up with shared repositories where we can use each other's data, but we need to be careful about using the right amount of data needed for our learning systems while also respecting privacy. It seems like we are just beginning to work on these open-ended problems, but there is so much things to work on together. So thanks again, everybody, for this wonderful panel discussion, and let's meet again after lunch, which is probably at 3 p.m. Right, Zachary?
Yes. I'm going to share a slide. It's got the actual time on it. Do you see this now? Yeah, so it's going to be in Eastern time. It would be 3:15. So
awesome.
And yes, again, thank you everyone a huge thank you to the panelists. It was wonderful to get your feedback on these ideas and sharing your insight and knowledge. As Tapo had already discussed, he gave a wonderful overview of all the main points brought up. And thank you again to everyone in attendance. It's great having you here and having you ask questions and feedback. So at this point, we'll take a short lunch break, and we'll be back in a little under an hour. So about 50 minutes from now, we'll be back. All right, take care, everyone. See you soon.
Yeah, hello, everybody. It's my absolute pleasure to introduce my postdoc advisor, Sid. Dr. Siddhartha Srinivasa is the Boeing Endowed Professor at the School of Computer Science and Engineering at the University of Washington, where he leads the Personal Robotics Lab. Sid has worked on so many different things, robotics, that the best way to probably describe his work is like he's a full stack roboticist, where he has worked on motion planning, human-robot interaction, like robotic manipulation. But his goal generally is to enable robots to perform complex manipulation tasks under uncertainty and clutter with and around people. Sid has also led several large initiatives, including the Quality of Life Technologies, NSF ERC, DARPA RMS, and the CMU CHIMP team on the DARPA DRC. So it's again, it's my absolute pleasure to welcome Sid. Sid, over to you.
Thank you, Tapo. Can everyone hear me and see my screen clearly?
Yep.
Thumbs up.
Yes.
Excellent. Thanks. Well, thank you so much for having me. It's such a pleasure to be here, speaking to such a distinguished audience. It's been years since I've seen some of you, so hello to all those I haven't seen in a while. You look exactly the same. So today, and thank you, Tapo, for the kind words. Today, I want to talk a little bit about robot-assisted feeding. I know Tapo talked a little bit about this earlier today as well, so I'll give you my perspective on it. And it's been a problem that I've been incredibly passionate about for the past almost 10 years. And I wanted to share more than solutions, actually, some of the problems so that I can get you all excited about working on this problem. So this is more of an interesting problem summary rather than an interesting answer summary. And I'll try to provide some of the discoveries that we've had along the way. We're still far away from being able to address this problem completely. Of course, I want to acknowledge the work by my really wonderful team. There's Tapo out in the back. This picture was taken a few years ago. Really, honestly, it's their work. I'm merely a vehicle for the transmittance of their work. And they've been doing really fantastic work at the University of Washington. It's also been a real pleasure working at the University of Washington very closely with physical therapists, doctors, as well as the users of our work. So super excited about everything that we're doing at UW. Today is also a rare sunny day in Seattle. So my white balance is all messed up because I'm used to the rather less light. So feeding is something that's rather interesting and personal. So I wanted to share a video from a while back. It's actually right about when I started working on this project. Oh, I didn't know there was sound. I don't know if you can hear my son speaking. So this is a video from right about when we started working on this program in 2014. And even in this really small video snippet, you can see a lot of very interesting interaction. There's my daughter, Samira, being fed by my wife, Supriya. And if you notice, Samira is actually tracking the spoon with her eyes. And there's a lot of signaling even going on. Of course, the type of food that she's being fed and how she's eating, obviously with 0 teeth. And if you watch this video, obviously as a dad, I've watched this video thousands and thousands of times. There's a little bit of sort of spittle coming out of her mouth, and Supriya sort of very deftly cleans it out. And then the camera pans to Kabir, who at that time was probably 3.5 years old, and he's eating by himself. So he's also learning to eat, as you can probably see from the video. He's eating granola with some milk. And again, if you watch the video, he tries to pick up a spoonful of food and fails pretty miserably at it, and then realizes that and instantaneously, or at least I'm speaking as a proud dad, instantaneously fixes that problem by picking up the granola and putting it in his mouth. And then subsequently, he wipes his face with a little paper towel on the side. So there's a lot of, and obviously the other thing that you notice immediately is that eating is such an incredibly social interaction. There's 3 people there, they're all participant in this social dance of eating, whether it's feeding, whether it's eating by themselves, or whether it's watching someone else eat. And so I think this video really exemplifies a lot of the challenges that we all see and feel when we're eating. Of course, the kids are much older now. So Kabir's almost 10, Samira is 6. So it's been a while since that video. But there's still the same social dance and the same social interactions. Actually, we had lunch just a little while ago together. And I can't help but notice, as a roboticist and someone working on feeding, just how many of these patterns repeat and how many new patterns emerge because they're older, they eat different food. So I think in addition to the fact that this interaction is complicated, it is also changing spatiotemporally, like where we eat and when we eat. And it's a gift that sort of keeps on giving. And I think many of the sort of parents will agree that, should I admit somebody into the waiting room, or will you take care? Oh, you got it. Okay.
Oh, we are taking care of it, Sid. Sorry.
Okay, cool. No worries. These days it's very rare that my kids want me to feed them, but I grab every single one of those opportunities because I never know when it will be the last one for me. So it's still a pleasure feeding the kids. They have big teeth now, so my feeding strategy has also changed significantly since when they were kids, and their patience has also gone up or down significantly. They're far more resistant to eating their broccoli now than they were before. So again, that's another point, which is that feeding is not just an act of giving somebody food, but it's often an act of coercion, like convincing people that they really ought to eat their broccoli, not just all the cool stuff on their plate. And of course, this is the motivation for our work, right? There are over 12 million people in the United States alone for whom this is not a luxury, right? They have to be fed by their caregivers. These are actually some of the users that we work with, and they've given us permission to share this video. Tapo may have also shown you this video earlier today. But just like watching my own kids eat and sitting around my own kids eating, watching the users that we work with be fed by caregivers is also inspiring and fascinating simultaneously, particularly because a lot of these people are now our friends, not just people who are our subjects or our users. And it's been a prolonged space and time of interaction with them over the past 4 or 5 years. And we've learned a lot from them also. But I think this is what excites me the most about feeding, is that it's simultaneously incredibly familiar to us. We all eat all the time. We've all fed probably, or will feed somebody in our lifetimes. But also there are millions of people whose lives that we can actually positively affect by the work that we could be doing in assistive feeding. So that really is the motivation for at least some of this work, which is how do we build AI that can empower those who are in need of care. Right? And I think I chose all of these words very carefully. We're certainly not replacing one caregiver with another, or taking away the freedom that somebody has. I actually just remembered an interesting conversation I had with somebody at the Rehab Institute of Chicago. And I told them, like, oh, okay, I'll build you a robot that can feed you food. Like, isn't that awesome? And she said something that I remember even today. She said, well, now there's going to be another thing that's going to tell me what to do. I don't want that. Right? Like, no, I want to be empowered. I want the ability to really be free in what I'm doing, and I don't want one more thing telling me what to do. I think feeding is, again, one of those interesting acts where we really don't want to be fed if we can feed by ourselves. I'm sure Tapo has talked about this to you too, which is that it is often a case where people are embarrassed to be seen being fed when in the past they were able to eat by themselves. So again, I really want to focus on building AI that can empower, and I think we should all think about this as a means to empower those in need of care, rather than replace something that had control over them with some other thing that had control over them. So this is a video of our current system in action. All of what you see here is completely autonomous. We have, and I'll walk you through some of the algorithms that go in here. We have algorithms that are perceiving what's on the plate, classifying what it is, using learning to close the loop on haptic feedback, planning such that they can actually go close to the face and feed somebody, visual surveying and face tracking, so we can track facial features, including things like, is the mouth open or not? That's actually rather important sometimes. Or are they talking or not? Are they looking at us or not? This is a system, this is a snapshot of the system right now. You know, if you go to our website, you'll have videos of the system over the past several years. And this is by no ways a completed problem, right? Like, we're still working our way towards addressing this problem. I think this is, again, some work that, and I want to give 1,000% of this credit to Tapo for championing it. One of the biggest pleasures for us has been in trialing and testing our work with the user population that really wants this, right? One thing you'll notice here immediately is the variety of interfaces that these people use to control the robot, to control their systems, as well as the variety of their abilities and disabilities. So we have patients with high spinal cord injuries all the way from C1 to C6. So really limited mobility to a little bit more mobility. And I think that's another piece that's really exciting and interesting about this problem. Just like you saw that the way Samira ate was very different from the way Kabir ate, I think that our physical abilities and disabilities, not just our interests, really shape the way we eat. And that, again, is a moving target. It changes really spatiotemporally as we get used to the system. So building caregiving systems that can actually very deliberately think about this moving target is very important. You notice this even with caregivers, right? Like, certainly you notice this with as parents, but you notice this with caregivers, that they're changing their interaction modality spatiotemporally based on the situation, based on time. And they're able to mine a rich set of features, historical features also. They're running, you know, long range prediction as well as closing the loop on that, such that they can really truly meaningfully interact with their users in the social dance that exists. So why feeding? And I'm sure, like, Tapo has given you his reasons for why he wanted to work on feeding, but I wanted to give you mine. It's actually, you know, obviously there are so many activities of daily living and instrumented activities of daily living. I personally chose to work on feeding on an impulse. It was just, I was talking to some users at the Rehab Institute of Chicago. This is almost 8 or 9 years ago. And pretty much every single one of them said, I want a robot. I want to be able to feed myself. Obviously, I didn't do any long study of, like, you know, what is the fraction of the population that wants feeding or not. I looked at the problem and said, yeah, if I think about it as a roboticist, the problem really sort of very nicely breaks down into two large subproblems, right? The first one is what we call byte acquisition. Being able to pull out 1 byte, not 0 bytes, not 2 bytes of food from a plate. And the second is of byte transfer. And it turns out that byte transfer, if you think a little bit more about it, is really a handover. This is something that I'd worked on many, many years ago on how can robots hand over things to humans. And this is exactly the same thing. It's the handover of a piece of food from a fork to a human being. It's a robot to human handover process. And it inherits a lot of the same challenges as handing over a coffee mug to somebody else, in that there is the signaling of intent, there is the agreement as to the exact time at which we will close the handover process, as well as there is a lot of error correction and feedback that goes into that, right? And of course, it ratchets up the complexity of that even more quite significantly, because you're literally putting a piece of food in somebody's mouth, right? So the things that can go wrong can be potentially even more challenging. But I think as a roboticist, I felt like, well, at least I believe that at some level, I might be able to build a system that might be able to perform some of these tasks by breaking it down like this. Of course, again, like I said, we're very far away from a system that works for reals, but at least we've been able to use these same principles to be able to break the problem down into acquisition and transfer and make some progress along that way. The other question that one might ask is, so why a robot arm, right? Why not build a special purpose robot that feeds somebody? And of course, history is replete with special purpose robots that do various things. For us, the reason for using the Kinova Jeiko arm that's mounted on a powered wheelchair was rather very simple, which is that these systems already existed in the real world, right? So there were several hundred users of these Kinova robot arms that were already using the robot for several different purposes. And we knew that that user population was only going to grow up. And so we wanted to bootstrap our AI off of that existing user base and provide a means by which we could quickly build our software such that it would, I can't pause this video, it is very distracting. Such that we could actually piggyback off of the work that they did. Actually, one of the, and I'll just mention it right now, there's one problem that's actually very unique about having a robot arm that does many things, including feed you food, is the context, right? This robot arm may have been used to hold on to an object while you were drilling, and now suddenly it's feeding you food. So I think there's an interesting open question about, like, how do you tell the user that you've actually switched context from a robot that is just holding on to something for you to a robot that is actually feeding you some food? And again, there's another interesting question around, do you want this feeding robot to function like a third hand, or should it function like a caregiver? Or, obviously I'm not talking about Booleans, but really about an entire spectrum. So there's an entire sort of interaction design question around, like, how do you want this robot to actually work with you? And we've barely scratched the surface of that problem too. So I want to, again, like I told you, this is more a problem than an answer. But one of the things that's really exciting about robot-assisted feeding is that it really lies at the intersection of robotics and human-robot interaction, right? We need both of these to be able to succeed. And certainly this is our current view, right? I'm sure that this is just a projection onto a two-dimensional space of an incredibly multi-dimensional space. I'm sure there's many other fields that are equally critical. So for example, some of the work that we've been doing, and this was one of the things that initially fascinated me about the manipulation problem, was about representation. How do you represent? What is the state space that you use to represent a plate full of food? Is it the same as the state space that you represent a bowl full of spaghetti? Is it the same that you use to represent alphabet soup? Is it the same that you use to represent sort of cut vegetables? So really thinking about representations and state estimation, given a stateful representation, was something that it's still an interesting and open problem. And it's challenged me particularly because I'm very, very much traditionally a model-based person. Like I like to build models, I like to plan with those models, I like to close the planning loop with those models. But this field challenges me because like, what is the model of like picking up a banana and eating it? What happens when you bite into the banana? How does that state space change? There are actually no answers yet. I don't know, but it certainly was quite fascinating for me to think about these problems. Of course, the next one is deformation and haptics. You're dealing fundamentally with deformable objects. Right? Most of the things that you eat that are on your plate are going to change their shape, potentially their appearance as you're eating them. And that change of shape and change of appearance is actually important. Right? It's not a nuisance, but it's actually important. The texture, the mouthfeel of food is an equally important pleasure of eating the food as the as the physical appearances. Like for any of us who like eating sushi, like just the feel of the sushi entering my mouth is just almost as pleasurable as the taste of the sushi as I'm eating it. And of course you want to make sure that like the robot that is picking up your food doesn't mess up that mouthfeel, right? Which is again interesting and important. And of course it is a haptic problem, very much a haptic problem. And I can talk about some of the interesting consequences of that. And of course there's some very interesting motion planning problems that we've had to address as well. One of them is actually goes back to the days of sort of Lozano Perez, which is called goal backchaining. The idea being that if you just pick up a celery stick right in the middle and you've grasped it, and now you need to feed it into somebody's mouth, like how are you going to actually present it such that the person can take a bite out of it? Because re-grasping that celery stick is quite challenging, right? You've already stabbed it in the middle. So what pre-image backchaining around goals says is that, like, think about the goal that you want, which is, I want to have exposed a piece of celery that the person can actually bite with their mouth, and backchain that to your starting conditions such that you're picking up the celery knowing fully well what you want to do with it, right? This is particularly relevant in cases where reconfiguring, in-hand reconfiguration is very challenging. You as a human don't pick up the keys knowing fully well that you need to like insert it into the lock, but that's because you can in-hand reconfigure it. That's much, much harder for robots. And of course, the questions around legibility, like what does it mean for this robot to signal its intent that it is actually giving you food rather than sort of waving its hands around with your food? Because even though humans, the users might know that this is a robot that is trying to feed them, the details are actually important, right? The amount of trust and confidence that they have in the system will vary greatly depending on how intentful they think it is, right? And I think as users, as designers of robots, we sometimes confuse safety with comfort. Just because a robot is safe doesn't mean that it's comfortable. Like you can have a robot that stops a millimeter away from your face. You can declare that it's incredibly safe, but it's not comfortable at all. Nobody would want one. So I think thinking very carefully about the comfort of the robot interacting with you is incredibly important. And then of course, intent inference. So we've been doing a whole bunch of work on being able to do face tracking, also track salient features on people's faces, including their gaze and potentially the movement of their mouth and lips, to understand not just when they're ready to take a bite, but also to know what they're doing. Like I said before, and I'm not going to talk about this in this talk, feeding and eating is a social process. There's a delicate dance by which you eat and feed. As an experiment for yourself, and I have some data that backs this up, when you're eating socially with other people, our data suggests that you spend about 30% of your time with the food in your fork on your side, waiting to put that food in your mouth because you're just not ready. You're either talking or you're listening to somebody talk, and you're just not ready to shove that food into your mouth, right? And again, like, if you want to play a cruel joke on someone, just as their fork starts going towards their mouth, just look at them with interest, and that fork will almost always drop back to its waiting position. And that's because we just don't want people to see us sort of shoveling food into our mouth. So having robots that are not just waiting to see when you're not talking, when your mouth is open, but actually understanding the social context is actually quite important and relevant. And of course, interface design and shared autonomy. Like what does it mean for this robot to work with you? How do you design interfaces such that they can work for all kinds of different input interfaces? It might be a sip and puff, it might be a head-mounted joystick, it might be a foot-mounted joystick. All of these different interfaces demand different levels of interactivity between the robot and the human. Even basic questions like, should this robot talk to you while it's feeding you or not? Is it weird that a robot arm talks to you? Is it not, right? And again, it's all incredibly contextual, but also incredibly important. And like I mentioned before, social dining is actually a really interesting and open problem that we haven't actually looked at too much. It's not just about one person eating with a robot, but really about multiple people eating together, not just the social dance of it, but also should the robot pass the salt to your friend? Or should it be focusing exclusively on just feeding you, right? And all of these things are actually quite important and are important for the user to feel like they're part of the same social dynamic as the other able-bodied users who are sitting at the table, right? Like that's what we want to be at. So I want to talk about one very, very specific thing, which is around tactile perception. One thing I want to also say is that as humans, we fumble around a lot, right? And if you watch this video, this is actually some studies that we ran. You can watch that the person tries to pick up the banana, fails at it, and then picks it up and then feeds it. And this happens over and over again, right? Like here we have 1 kilohertz control loop that we're using to track the 6-axis forces and torques that are this is an ATI nanosensor. It's the world's most expensive fork that we built. And we wanted to track the haptic interactions between a human and the fork and the food while they were picking up a food. And you notice here that it's actually incredibly subtle and incredibly challenging and important, right? The failure modes are important and the successes are also important. Another interesting factoid about bananas is that it really breaks all the geometry-based grass planning algorithms that you might have. Like if you look at like DexNet or DexNet 2.0, the standard way they figure out where to pick up the object is you try to find a flat planar surface and you find its surface normal and you approach along the surface normal. This actually works terribly poorly for bananas because if you step the banana vertically, it's just flop out as you lift. And so you actually need to understand that the physical properties of the banana force you to actually go sideways so that you can counteract gravity as you're lifting up. So again, feeding is one of those interesting problems where you are changing the physical properties of the object as you're manipulating it. You're stabbing it, you're cutting it, you're twirling it. And so you need to post hoc rationalize about the consequences of the actions that you're doing before you start messing around with it, because some of these might be irreversible. And I think what's really interesting here is that byte acquisition is contextual and tactile, right? Like both of those words are, again, very important. It really depends on the context at which you're manipulating it, whether you're picking up a hard item or a soft item or something with a hard skin like a grape or something with a very, very soft skin. The force profile that you're using to interact with this object is very, very different, right? So if you just think about like a spring damper system or some linear controller in task space, it is almost always not going to work because the interaction between the fork and the item is complicated and nonlinear and potentially even stateful, right? And so again, this is some work that we've done on being able to learn some of these policies such that we can even acquire bytes with high degree of success without destroying them. To be able to do all of this, we actually had to invent some new sensors, and all of these are completely open sourced in terms of hardware as well as software. So initially we started off with this sort of rat's nest of cables and cameras. The Kinova Jayco arm is particularly annoying for cabling. because it has continuous rotation. So no matter how much sort of cable tension you release, it is always going to entangle itself. It's just a fact of life. And at some point I got super annoyed with it, and it's like, okay, let's just go build a wireless perception module. This actually uses some very off-the-shelf devices, right? We have an Intel RealSense camera. Currently we use the D415, but you could plug and play any of these RealSense cameras. And inside it has an Intel Jewel, which is a sort of a low power compute from Intel. The nice thing about the Jewel is that you can stick Ubuntu on it. You can run like regular ROS on it, so you don't have to do crazy things. And it also has Wi-Fi and broadcast imagery as well as data over TCP/IP. And we also built, we only have like really two wires, one that connects to the RealSense and the other one that actually connects to a gel side based tactile sensor that we developed. So this is sort of, we took the gel side and turned it, actually, this is much more similar to the gel slim than to the gel side, where we were trying to make it fit the form factor of the fingers such that we could actually stick it as end of arm tool. And so that's sort of what it looks like. It does multimodal detection. We use the camera, the eye in hand system for detecting food, as well as for visual surveying with the faces. And then we use the force sensing that comes from the gel side sensing to really close the loop on perception and action. So here's actually a pretty cool example. You watch this, you can notice when the skin of the grape was peeled. That's the first force bump that you see. And the second force bump that you see is when it actually picks it up. And we're doing a apples to apples comparison between what we call our finger vision sensor and the 6-axis force torque sensor that's already there. Now, using that, you can try to close the loop on sensing. And one of the really nice things about the gel side based sensor is that you can not only close the loop effectively in being able to pick up these items, but you can also measure the weight of something that you've picked up. And that's actually kind of cool, because after you pick it up, if you release your fingers slightly, if you loosen your fingers, then you can measure the deformation of the sensor to be able to tell the weight of what you picked up. So initially you squeeze really tight and you lift it, and then as you loosen your fingers, the item drops imperceptibly, and that drop actually tells you what the weight of the object is that you picked up to some level. To a level enough to be able to tell whether you picked up an item or dropped it. And this is, as you can imagine, incredibly challenging for food items that can be arbitrarily light. Right? Like it's hard to tell, it's hard to put a force threshold on a banana piece. And so this sensing was actually really, really useful for us for error correction as well. And I think likewise, the key insight behind our perception algorithm is to really classify identity and regress strategy, right? Both of those, again, are really important because you need to know the identity, to some level of what you're picking up. Because if you know it's a banana, then you know that you need to skewer it sideways. Even though it's RGB and potentially depth can be the same, the actual strategy can be very different based on the identity that you classify, right? And again, like asparagus is a really, really good example. I came to the United States having never eaten asparagus in my life in India. And it was the worst thing in the world to slice with a knife, because you have to slice it very, very gently, right? Like you think that you have to just hammer away at the asparagus and cut as hard as possible, but that just squishes the asparagus. It doesn't slice it. And so you have to really sort of go very, very lightly with your fingers with the asparagus. And obviously, without knowing the identity that it is an asparagus, you would not know what the control strategy is going to be able to pick it up. So a big drawback of this particular work, and this is actually really open work, is that we only sort of know the control strategies of the things that we know how to pick up, right? Like I showed you this beautiful picture of classify identity, regress strategy. But what if you were like little Sid and had never seen asparagus before? Like I would have incorrectly classified it as something else that I knew how to manipulate, and I would have failed. And so obviously this doesn't solve all of those problems. So we're actually working on some active learning algorithms that are able to learn from, we have a couple of papers now on active learning, they can learn from failures such that they can know, okay, I completely obliterated this asparagus as I tried to slice it. I should probably choose a different strategy. So this is the big drawback of this particular work, that as you see it, is that it's fixed in space and time, right? You can only manipulate the things that you know how to manipulate. So I think, this is sort of the baseline of like, think of the left side as like a DexNet-like approach, which tries to find the normal of the thing that you want to pick and just go ahead and pick it. And again, you can see here how the orientation matters, the type of the food item that you're picking matters, and also thinking very carefully about how you're going to fail or succeed also matters quite significantly. This one's particularly interesting because we are able to grasp the boiled egg at the intersection of the yolk and the white, and not just right at the yolk. Because obviously, as a grown-up adult, you know that if you pick it up right at the yolk, it'll sort of crush the yolk, and you'll only get that out. So that was kind of cool. But these are all essentially like learned policies for picking up food. So I want to pause here because of course I could go on forever about several different things, but I hope I gave you at least a couple of vignettes into why this problem is interesting and challenging, and also about how a lot of my work is on being able to look at these really interesting phenomena that are happening out in the real world. That's why I love HRI, because there's so many interesting phenomena, and try to put some math around it such that we can turn those into algorithms that can be deployed on our robots. We're still really, really far away from being able to build systems that can even have some good coverage over all of these challenges for robotics. But one of the things that's really interesting is that we're starting to understand at least what some of these problems are, right? And just like, I've started playing a lot more tennis now. And when you reach a particular level at tennis, you feel happy that you've accomplished something, but you also realize, oh, now I know what the problems at the next level are, because I'm like halfway competent at doing something. Now I need to learn that, like the kick serve. And so I think every layer that we get to only reveals the next layer that's even more harder and more challenging. But at the very least, we're able to get to some layer whereby we actually ran this demo at NeurEPS all day, all night to our users. This is some of the stuff that Tapo did. And we were able to just actually take the system out to Montreal and have it running and do reasonably well at being able to feed people. So, that's definitely a testament to the state of the system. And I think I want to come back to this video of our users because in the end, it's for these people that we're building these systems. And it's really important for us to think about the effectiveness of these systems to our users. And this is actually, so again, some of Tapo's work, where our intended care recipients acknowledge that this is an interesting and challenging problem, but are also excited about the potential of what we can do with this system. And again, you can see the word independence come up over and over again, because again, it is very empowering, even at the state at which the system is in, to be able to have a plate of food in front of you and be able to eat by yourself. And I think we're a long way away from being able to fully solve this problem, but we're excited about the trajectory that we're taking. Of course, I'd encourage you to go to the website. We have a website, robotfeeding.io, and take a look at some of our papers, which is always fun. But more importantly, I do want you to take a look at some of our open data sets. We have our data set of using the world's most expensive fork to capture mocap and 6-axis force torque. I think we have like 37 or so hours of data of people picking up food, mostly synchronized video and force torque data, as well as mocap data. And that's super interesting and exciting for us. And so I think these data sets are all available on the Harvard Dataverse, so I encourage you all to take a look at them. And of course, the GelSight Mini, which is what we call our tactile sensor, the hardware is completely open, as well as the software. There's a GitHub repo for that, and the wireless perception module. So they're all a few $100s to put together and build. And of course, obviously, if you if you build better versions of these, do let us know and we'll just use them. We're super excited to be able to participate in this ecosystem. So I want to close. I think I put up this question earlier of how do we build AI that can empower those in need of care. It's a question that I've been asking myself quite a bit. I think we, as roboticists and as AI people, we tend to build robots that can make able-bodied people more lazy. And I think it's really important for us to think about how we can build robots that can actually empower those who truly need care. I wish, and I'm excited about all the people who are working on it, and I wish more would also join in. Thank you.
Thank you, Sid. Thank you. Let me applaud on behalf of everybody present here. Thanks again for the excellent talk. It's just every time it's just so fascinating to see you give like a 10,000 foot view of the problem, and it's just it's super interesting, and I'm always learning. It's awesome. So we already have around 3 questions on the chat. So let me just start from the first. So Michelle asks basically, so issues of feeding robots have been around since early 1990s, with the first robot being Magpie from UK and low-cost options of Neater Eater. Adding in ML is interesting. Any thoughts about affordability issues?
Very good point. I also want to acknowledge a lot of that early work and work from way before. I think we were equally inspired by all of that work and continue to be so. I think that the affordability is always an interesting and open challenge. My own strategy around that was to use an existing robot that was in people's homes. So in Canada and in parts of Europe, the Kinova Geco arm is approved for use by the medical, by the government, right? So it is subsidized. And my thought on it was that instead of building another piece of hardware that would have to go through the entire sort of rigorous process, I wanted to take an existing robot and demonstrate ability for that existing robot that was beyond what it was already capable of doing. Of course, I completely agree that we have to add this wireless module, which is about $200 or so. But I think that's been my take on it, is that instead of creating more artifacts in the home that are single use, it would be interesting to create potentially a single artifact that could be multiple use. Now, I think the other challenge is around people with different abilities. Of course, we are far away from building a product, and just getting a piece of food in somebody's mouth is actually also just part of the feeding process, right? Like you saw even with my kids, there's a lot of error correction, error detection, error recovery that goes on, some of which our robots can do as well. But I think we're still far away from having a system that can completely feed somebody with their assistance.
Great. The next question is from Daniel. So Daniel says, you mentioned robots grasping food, such as bananas, using DexNet. I'm curious about your thoughts on peeling bananas in addition to grasping them. What would your proposed robotic approach look like?
I don't know. I think Daniel should work on that because I would use that. Actually, at a higher level, again, I completely agree that everything that we've looked at until now has been about skewering, right? Like picking up like a bite full of food. Of course, we've looked at mashed potatoes and we've looked at a few other, you unleash undergrads on a problem and they come up with different ways in which you can make a mess with different kinds of food. But I do completely agree that, some of these tasks might be fundamentally bimanual also. But I wanna point out to one thing, right? Like, I think that the assistive community has built a lot of affordances that can help people, potentially even with a single arm, potentially people with low abilities. The very simple, like the sort of like the stick mats or the plates with barriers on the side, and various other implements that I think we should certainly be using. But yeah, I think even twirling spaghetti, things like that are still interesting and open. But I am inspired by, you just go to YouTube and watch videos of people with an arm, or people with with high levels of disability, with motor disability, be able to do these incredible tasks with very, very simple affordances added onto their devices. So I think that's been really inspiring to me.
Awesome. Yeah, Daniel says he'll work on it. Michelle also has a follow-up question on, like, most of the work that you have shown here uses forks. So have you done work with spoons or knives?
Yes. So we do have some work that we're doing right now, as well as have done in the past, on being able to scoop. And I think scooping is actually really interesting for two reasons. One is, of course, again, like, what is the state space of mashed potatoes is an interesting problem. Actually, about 30 years ago, maybe, there's a whole bunch of work in the construction robotics industry on using diggers to scoop dirt and move it from place to place. And they had actually built like complex, like, fluid mechanical models of how piles of dirt move as you're lifting them. And I think so things like that are certainly of interest to us. The other really interesting thing about scooping and also about manipulating with forks is, and this is one of my favorite problems, like, I eat Indian food, and Indian food, I often eat Indian food. Let me restate that. And Indian food is fascinating because you have to combine different components of the food, like a little bit of curry A, a little bit of curry B, a little bit of yogurt, a little bit of rice, and sort of mix it together for every single bite. And honestly, like, the joy of Indian food is that you're constantly performing sort of gradient descent on the proportions of all of these items that you want to use. And it's your last bite that's almost always the perfect bite, because you figure out, all right, like, this is how much of these things I need to put together. But I think the meta point being, sometimes food is not just picking one thing up and sticking it in your mouth, but really about combining different pieces of food into one sort of mouthful so that you can get the right mouth feel as you're eating it. And again, doing something like that, even with a fork or a knife, is interesting, right? Like, even when you're skewering salad, for example, you might skewer some greens, but then you might also skewer a tomato because you like the way the greens and the tomatoes interact with each other in your mouth. And so being able to do sort of multi-bite skewering so that you can get the right mouthfeel is also interesting.
Thanks, Sid. This is probably the final question in the interest of time. So Gabriel asks, you presented bite acquisition as an autonomous process, but also insisted on the essential aspect of empowerment for the users. Any feedback from the trade-off between autonomous and shared control bite acquisition for users capable of continuous 2D/3D control?
Yeah, I think that's a really interesting problem, and something that we worked on quite a bit too, which is, you can think of the bite acquisition algorithms that we have as providing you with an ability to pick up a bite of food. And we worked on a bunch of different ways by which we can empower people to participate in that ability. So we've used gaze trackers, for example, for the users to look at some part of their plate. And then we use that to capture a region of interest and then pick up a bite full of food from that region of interest. We've also used voice or other interfaces by which people can say, like, hey, I want tomatoes, or hey, I want carrots, or hey, I want something. I think the 2D interaction is also really interesting, because you can think of the AI as almost providing a snap function to your control, right? You can sort of coarsely move your two-dimensional cursor to a position where you might want it, and the AI can use that as an initial guess for what the right bite should be. So it provides you with this sort of snapping or refinement function. I think there's an interesting question also about the signaling of bite transfer. Like, should that be a button that you press? You know, for some of our users, we just asked them to open their mouths whenever they were ready. And because we were doing full face tracking, our AI was able to sort of tell when it should feed them. So yes, I 100% agree. I think that you can think of these as building blocks on top of which to build whatever interfaces and whatever systems you want. Like, I want to be very clear on that, which is, I'm not an advocate of full autonomy for two reasons. One is empowerment, like you rightly pointed out. But the other is also, I just want to deploy these as fast as possible. And we are actually in an environment where the user actually wants this task to succeed, right? You're not dealing with an antagonistic user. You're dealing with a user who's also largely cooperative in the success of this task. So being able to bootstrap that and being able to exploit that is actually quite valuable without overburdening them.
Thank you so much, Sid. So I guess if people have more questions, feel free to put them in the chat. But let's again thank Sid for the excellent talk. And Zachary, over to you to introduce our next speaker.
Yes, so thank you again, Sid. So our next speaker, it's my pleasure to introduce Professor Pieter Abbeel, who I recently got to start working with a little over a year ago from the perspective of manipulation of deformable materials. And so Pieter is the director of the Berkeley Robot Learning Lab and co-director of the Berkeley Artificial Intelligence or Bayer Lab. And his group's research has helped push the frontiers of deep reinforcement learning, deep imitation learning, deep unsupervised learning, transfer learning, meta learning, and learning to learn, as well as studying the influence of AI on society. He received his PhD at Stanford and has received many awards and honors since, including the PCASE NSF Career, ONR Young Investigator Program, DARPA Young Faculty Award, and TR35. So with that, Pieter, I'll hand it over to you.
Thanks, Zachary. Can you hear me okay?
Yes, we can.
Now let's see if you can see my screen now.
Yep.
Okay, great. Yeah, well, I heard Sid say his tennis game is getting better. So Sid, looking forward to taking that to the test next time we get to meet. But now back to the workshop program. So what I'm interested in is a bit, I guess, complementary what Sid was looking at. I like to see how far we can go with autonomy and how far I can push this. And I think at the core, what we'll need is reinforcement learning, systems that continue to learn from their own trial and error, so we don't have to teach them every single thing through demonstrations or labeling and so forth. Sorry, there's a little bit of background noise right now. The trash pickup is happening right now in front of our house, but it sounds like it's going away. So, but what are the challenges in RL? I would say there's two main challenges. One is that the sample complexity is pretty high. Even for simple things like the game of Pong, it can take 40 days to learn to play the game. And for a game like Go, to almost 5 million games to, yeah, a few more. Can you hear me okay, by the way? Because I'm hearing nothing but trash pickup truck right now. Okay, so Zoom has great noise cancellation. So the amount of samples you need to learn is high, even for games, let alone if you're going to move this to the real world. And then the other thing, which ties very close to what Sid was talking about actually, is that you want to be able to personalize what the system does in a convenient way. And today, the way you personalize is by designing a reward function, but that's very error prone. So an example you see here on the bottom right is a boat that's just going around in circles. Well, that's not the intent of the game, but the way the reward was designed, you get a higher score for going in circles in the harbor than to race the actual race. And so can we get to more intuitive interfaces than reward design? So there's two main topics I'm going to cover then: representation learning for RL, which I think will be key to making it more efficient, and human in the loop reinforcement learning. So starting with representation learning. This is kind of the status of the field about a year and a half ago. These are learning curves, so higher is better, and the faster you go up, the better. The horizontal axis is number of training steps in the environment. So what you see here is in blue, the learning curve, if you have access to the underlying state of the world. In green, the learning curve, if all you have access to is the visual input of how you are perceiving the world as a robot. And we see that the green learning curve is a lot slower than the blue learning curve. Two versions of the green, but difference doesn't matter too much. And so what it shows is that as of a year and a half ago, learning from underlying state is much, much faster than learning from pixels. But should it be? Ultimately, the pixels have all the information. It's just that it's not smart enough to extract the information, but the information is there. So can we bridge this gap? Because if we can, that's actually really helpful for real world learning, where typically we don't have instrumentation to extract the state readily available, or it'd be very expensive when we do. This, of course, might remind many of you of the Jan LeCun cake story, where essentially the NeurIPS opening keynote in 2016, he said, hey, RL is just a cherry on the cake because there's not a lot of signal in the reward. It's very sporadic. What we really need to do, where all the volume is in the cake, is the body of the cake, and that is self-supervised or unsupervised learning. Because learning from data just available without any human labeling effort, well, there's pretty much infinite data of that type. And then the icing on the cake is where people are willing to label. And so the question here is, can we bring this to reinforcement learning? Can we bring this best kind of self-supervised learning into reinforcement learning and make it a lot more effective? The best self-supervised learning is SimClear or SimClear variance. What does it do? So here, horizontal axis is the number of parameters in the network. Vertical axis is performance on ImageNet. So higher is better. What we see with the SimClear trend here, as you get a larger network, it performs better and better. And this is an unsupervised method that only gets to train a linear classifier on top of features that were learned unsupervised. And in fact, if it's large enough, the network, then just a linear classifier on top of it is enough to match supervised learning performance. Okay, what's under the hood? The main idea is contrastive learning. So you just download images. Now, here are 2 images you might download, maybe from taking pictures in a warehouse. Then, of course, you want to avoid having to annotate because that's expensive. So how can we still learn something from these images? Well, each of these images gets duplicated, but not in an identical way. So for the top one, we have a grayscale version and a mirrored version. And for the bottom one, we also have a grayscale version and a cropped version. Then for each of those 4 transformed images, the neural network will process them. And this will generate an embedding. So now we have 4 embedding vectors encoding hopefully something about what's in those images. But of course, before you train the network, it's probably not going to be that meaningful. So how do we train it? The embedding vectors that come from the same original should attract. The embedding vectors coming from different originals should repel. That's the objective. We optimize, anybody optimize running SimClear or MoCo or related contrastive learning approaches. Okay, so that's what you do in image recognition to pre-train from unsupervised data. In reinforcement learning, we can do something similar. We have a replay buffer where we have the data we have collected so far. We can take out a sequence of frames from the replay buffer. Why a sequence of frames? Because for robotics, velocities matter. And so a single frame doesn't give you much about velocity, but if you have a stack of a couple of frames, then you also have velocity information there. Then that stack of frames gets fed into the encoder part of the neural network, which on the top processing pipeline goes on to the actor and the critic as part of the reinforcement learning, but at the bottom goes to contrastive learning, where duplicates get generated and get contrasted against others from the replay buffer. So that's the whole idea. It's fairly straightforward, but it turns out very powerful. So what you see here is learning curves in gray with direct access to state, in red with only access to image observations of the environment. And this is in DeepMind control suite. So these are robots doing running or pushing or reaching or hopping. And what we see here is that in almost all of them, the red curve is as good or almost as good as the gray curve, which means that the gap has been bridged between learning from state and learning from images, thanks to the contrastive learning additional loss that we add to the training. Here's a comparison with past approaches. So we have here in gray, the top line everywhere, again, learning directly from state with soft actor critic. Then we have in red our approach, which also uses soft actor critic, but learns from images as input and uses contrastive loss. And then the other colors are prior works trying to solve image-based reinforcement learning, but not being nearly as efficient. Similar thing happens for Atari, Curl, Rainbow. Here we do the contrastive learning on top of Rainbow, which is a Q-learning approach. And we see that it outperforms prior work. This is the Atari 100K benchmark, which is for testing fast learning, and also it's faster to run your experiments because you only get 100K frames of interaction with the environment. Simple comes in second, which is a model-based approach, which often is thought of as should be more sample efficient. But actually, as you see, it actually is not. Q-learning with contrastive, the Curl Rainbow approach, is the most effective. Then you could ask the question, what if in the training of the neural network, we do not backpropagate the reinforcement learning loss into the encoder? We keep it restricted to the encoder only being trained from the contrastive loss, and then the reinforcement learning heads can be trained with reinforcement learning loss, but not the encoder. The comparison is red versus green. We see green is not as good. It's good to have that reinforcement learning loss backpropagating through the encoder, but actually very often it's close, suggesting that very often you could possibly pre-train the representation from maybe data you pre-collected in some other way, and then only train the reinforcement learning head afterwards quite effectively. Now, we actually then took this to a real robot. So here's the complete setup. With a real robot, you don't really want to start from scratch because it takes a long time. So we start from a few demonstrations. Then we run unsupervised representation learning on the data from the demonstrations. And then we do reinforcement learning with data augmentations while also keeping the original demonstrations in the replay buffer. And in total, it'll take about 30 minutes to run these experiments. 10 minutes for demonstrations, and then the remainder, essentially, the robot does everything on its own. So the human is involved in step 1, but doesn't have to do anything for step 2 or 3. Here are some results. So here the task is move. It's, well, demonstrations. On the left, then a first success happens after 40 episodes of trying. Optimal policy arrives at around 80 episodes, and we get about 26 out of 30 success of moving the object onto the red target. Similar for pull. Again, around 5 episodes now, it has a first success. After 45 has the policy it converges onto, which is 28 out of 30 success. So overall, it learned 6 diverse tasks with sparse reward entirely from pixels within an hour, using the same hyperparameters across all of them. Many of them have 100% success rate, though move and pull, the ones I showed, have a slightly lower percentage success rate. And the optimal policy arrives within half hour most of the time, sometimes even after 15 minutes. Okay, so that's one way to speed up reinforcement learning. It's to essentially learn representations through a contrastive loss. But ultimately under the hood, you might still want something else. And this is something that's been investigated in parallel, and I'm not sure which one will be the most important in the long run. But often you might want more compact representations. For example, key points, rather than a dense neural network output of what you process from images. For example, if you look at a human skeleton, if you track 17 or 18 coordinates, you kind of have the whole geometry of the current configuration of the human body. And so then, at least in this case, for this kind of skeleton, and that might be better as a representation to learn from and to control than a more dense representation. Envision's been a lot of work on key points, by the way, but not a lot of work on doing it in 3D, which of course is really important for robotics. So here are things that have been done in computer vision. You ask somebody to annotate enough data, and then at some point your neural network learns to extract those key points, and that actually works really well. But ideally you do this unsupervised, so you can cover a wider range of objects and situations rather than what we're willing to annotate. And 3D annotation is usually fairly impractical, so hopefully it's unsupervised, plus it would extract 3D rather than 2D. Why might this work? The intuition is that a fully convolutional architecture preserves spatial affinity, but then we add a key point bottleneck to the neural network. And by adding that bottleneck and then expecting a reconstruction after that, if the key points are very sparse and all it has is those key point coordinates, it better be the correct coordinates, otherwise the reconstruction is going to fail drastically. So that's how we set it up. In come images, in this case from different viewpoints. This one's done in simulation, but you could also set up multiple cameras in the real world. They get processed by the neural network. The neural network predicts, essentially outputs heat maps of regions of interest, then outputs coordinates, UV coordinates that are 2D, turns out with a depth prediction, a monocular depth prediction into 3D coordinates, then averages those 3D coordinates across all predictions to get a single set of 3D coordinates, put those back out to the reconstruction part of the network, and then the reconstructions happen. And so if those 3D coordinates are correct, it should reconstruct quite successfully. If not, it would be very hard to reconstruct. And so that's why, even though it's unsupervised, we can expect this to recover 3D coordinates of interesting points on the robot. In addition, we also do cropping, which is very common in computer vision. By cropping your images, you take some information away, which makes the neural network work harder to process things, and that's a good thing for its generalization capabilities. We looked at MetaWorld, which is a standard manipulation benchmark in simulated robotics, has 50 or 45 different tasks. One thing to keep in mind here, that this was designed for running from state space, is how the benchmark was designed, not from images, but we're going to do this from images, which get turned into key points and then in turn execute on the task. And it actually works really, really well. The green curve is with the unsupervised key point learner and reinforcement learning on top of that. The other learning curves are prior state-of-the-art of vision-based reinforcement learning, including what I just presented, curl, RAD, which is quite similar, and then in red, just a standard RL approach without any representation learning. We also looked at this in the context of deformable object manipulation, and this is of course something, Zachary, we're doing in the assistive gym that you have been one of the key developers of, and that we're very happy to be working with. And so what you see on the right here is a video of the learn policy in action. In the middle, you see the learning curves. And you see that the key point-based approach outperforms prior vision-based RL approaches significantly. And we also see that it actually gets the scarf around the head without exerting unnecessary force or choking anybody. You see here just the end effector control that's being learned. In principle, of course, you'd want a whole robot attached to that. But this is what we've been doing here for now. Now, so far we looked at representation learning for RL, and I think it's becoming a lot more effective. There's more work to be done, but I think it's becoming more and more realistic to run this even in real world, especially if initialized with demonstrations or initialized with simulated learning. But of course, going back to what this workshop is about, and in many other ways, is not just efficient learning to do the right things, but also giving the human a say in what happens. Standard RL doesn't give much of a say, except through the reward function. So something I've gotten really excited about in the last year is human in the loop RL. So typically RL, you have decisions, there are consequences, which consist of observations and rewards, and then this process repeats, but the problem, of course, is that these rewards are hard to design. For example, here's a reward that looks pretty reasonable. The further forward in the X direction, the better. Minimizing squared torques at the joints and keeping the center of gravity close to the 1.3 meters height. That all seems great. But then the running you get is not very natural looking running. And so this might not be what you want. So now you have to go tweak that reward function. Now imagine individuals having robots and they all have to go tweak reward functions for their own preference. It's going to be very, very hard. Imagine doing it for more difficult things like cooking. It's going to be really hard to design your reward function for cooking. In fact, Sid in the previous session alluded to many, many aspects of even just how you want to put the food in your mouth has so many reward aspects to it. And then, of course, there's the boat racing canonical example where it was a game where it seemed like what can go wrong in designing the reward function or the score in a game. And even there, things can go completely wrong, even though it's maybe a little less high stakes, but it's still illustrative of how hard it is to get this right. So what's an alternative solution? This is the typical RL learning loop. And let's assume we like RL. I mean, obviously that's a debate we can have. I think RL is only getting better over time. And even if you're not happy with it yet today, you might be happy with it in the future. Let's assume we want to keep that approach. How do we get rid of the reward and still learn something meaningful? Well, we then somehow want to put the human directly in the learning process. And in fact, the original reward formulation, even though it's not what we usually do in RL, talks about, it can be humans just saying good job, bad job. It doesn't talk about somebody writing a function in code that has to be used for learning, even though that's of course more convenient for benchmarking. But there's no reason you couldn't put a human in the loop. So, but now exactly how do you put the human in the loop in the most effective way? If the human has to give rewards directly, that's very hard. How do you score something? Effectively back to square one. It might not be a function, but you're still doing the same job of specifying point values of that function, which remains hard. Now, there's been some work on something called preference-based learning, which we're building upon, which I think is really promising. So the idea here is that the human just has to look at two trajectories at a time and decide which one is better, which one is worse. No quantification required, just which one's better, which one's worse, or you can say it's a tie, that's fine too. So this way, the human will have the ability to interactively guide agents according to the progress they're making. A better trajectory will be the better one compared to one that is not as much progressed yet. It can allow humans to teach harder tasks where it's hard to specify the reward, and it can avoid reward exploitation, which is where you specify the wrong reward and you get the robot that is super optimized for the wrong thing, which is, of course, in some sense, the worst of all that you can encounter. So how does it work? Step one, collect samples via interactions with the environment. Step two, collect human preferences by looking at pairs of trajectories. Now, when the human scores those trajectories, which one's better, which one's worse, what do? They just choose. But what then happens for the algorithm is it gets turned into a reward function, so we can run reinforcement learning again against this learned reward function from human preferences. How do we learn it? We essentially just train a classifier. You can think of a neural network as processing current state in action and predicting what the corresponding reward is. That neural network gets trained such that the sum of rewards along the winning trajectory is higher than the sum of rewards along the losing trajectory. But we don't just have an inequality constraint there. We train it as a classifier saying that the exponentiated sum of rewards along the winning trajectory, that's the numerator, and then the denominator will be the sum of both, the winner and the loser's exponentiated sum of rewards. And if this fraction is close to 1, then it means the winning trajectory has much higher reward than the losing one, and that's what we want, and that's how we train it as a classifier. Then we use that learned reward and we optimize the policy. Then of course, that doesn't mean we're set. We then have to go back around, collect more trajectories, collect new human preferences, and repeat. Why are we not done in one pass? Because initially the robot would just do fairly random things. And so getting preferences on that will be informative about maybe how you do the beginnings of something, but say nothing about how you do the later part. Another thing we do is pre-training. So the idea here is that if you just start RL from scratch, the motions you get shown on the left are pretty, well, essentially random walk-like motions. And if you get a bunch of those, it's hard to say which one's better, which one's worse. If you run unsupervised pre-training, which essentially tries to generate a range of interesting behaviors, even though it doesn't know which ones are more interesting or less interesting, it's just trying to find diversity, then it's much easier for a human to distinguish those and decide which ones they prefer over which other ones. Okay, so can this work? Here we show that a human can teach a cart pole to swing counterclockwise or clockwise. These are two separate teaching sessions showing that the human has control and in just 40 queries to the human and less than 5 minutes of time can teach spinning in one direction or the other. Here, human has taught in 200 queries, less than 30 minutes, which leg to lift. So 2 different runs, 2 different outcomes intentionally, showing the human control over the outcome. Can also teach backflips, which is a very classical example in this space, where the idea is, well, with a backflip, it's very hard to specify a reward function of what it even means to do a backflip. But with human preference learning, it's actually possible to teach it in less than an hour time. Can we avoid reward exploitation? Remember the running that wasn't so great? Here's a 2D version of that. Here it's dragging its leg with the standard DeepMind control suite reward function. With human preferences, we get actual running. It also is more efficient than prior works. I don't want to maybe get into too much detail, but the main differences in what we did was we made human preferences learning, one, off policy, which makes it significantly more efficient. 2, we made it take advantage of active pre-training. And 3, we included representation learning into it. And so the combination of all of this makes it a lot more effective. So in summary, I think reinforcement learning, while it still has some major downsides today in terms of sample complexity and the amount of control you have over the outcome, I think there are some really good paths forward to address those. For the first one, sample complexity, representation learning will be key, which means essentially having auxiliary losses related to, for example, could be a contrastive loss, which is what's often used in vision to do feature learning, or it could be 3D key point learning in an unsupervised way. Not sure which one will be most effective in the long term, but both seem very viable routes, and both are much more effective than not using such auxiliary losses. And for the other one, human-in-the-loop reinforcement learning, we showed it can actually be quite effective at teaching new skills where the human can really control what the skill is that's being learned. And by the way, for the latter, it's also worth mentioning that this human does not need to be a reinforcement learning expert. It just needs to be somebody who essentially can understand what it means for a robot to have made progress towards completing a task. So if you have any kind of understanding of how you might, evaluate a human making progress as you teach them, then the same kind of input by saying which directory is better than which other one could be used here. And that's it for me. Thank you.
Thank you, Peter. Thank you. So we have, I see one potentially one question in the chat currently. So I'll read that off. And if anyone else has other questions, feel free to throw them in the chat, or you can open up your mic. But so the first one is from Michelle here, in which she asked, and I believe she was referring to right after when you're presenting curl, you're looking at the key point method. And she was asking, can the key points deal with obstruction in the image, right? So if some of these, let's say 18 key points are blocked from the camera, how does that come into play?
The short answer is yes, but I mean, it doesn't work perfectly. I mean, there's room for progress, but essentially very often a bunch of the key points will be invisible from various camera inputs. And so, but because in this case, I should probably clarify this. In this case, we're always working either with this ant robot, or we're working with the robot that's putting the scarf on, or with these specific environments. So it's good to clarify that our train and test environment are matched up, right? And so it can actually learn at training time that when it sees a certain viewpoint onto this robot, what is going to be on the other side. Now, of course, if it's a detail of where exactly the foot is of a leg that you're not seeing, it's not going to get it super precisely, but it can still make an educated guess because it will be used in the averaging here. Now, there's something a little subtle in the averaging, which is that actually it can also output a variance here. And so if you're more uncertain, you can have a higher variance. And so you wouldn't contribute as much to that particular key point. So it's okay to have a higher variance, but it does try to make a prediction nevertheless for each of the key points in this while it's training.
Great. Any other questions from audience members that we have here? Oh, another one came in. So for Human in the Loop RL, this is by Jo. I'm sorry if I'm mispronouncing your name here. So Jo, for the Human in the Loop RL, do you incorporate some sort of curriculum to the learning process in order to learn long-term tasks, such as if the task were a long-term task, like say baking a cake, could you fraction the task? I suspect that means chop it up to make the dynamic evaluation of clips viable.
Yeah, it's a really good question. It's actually something we're dealing with right now as we're transitioning to longer horizon tasks. You're right. If somebody is baking a cake and you're supposed to compare them, taking the ingredients out of the cupboard versus putting the cake into the oven, it's hard to compare those two very different skills and say this one was better than that one. So yeah, the things we're looking at now are essentially also looking at timestamps and to compare clips of trajectories rather than the entire trajectory and have the timestamps with them. And then you would compare things from roughly the same timestamp. And then it becomes possible again, and you get kind of what you're alluding to here. But there's another thing in your question here that I think is really interesting, which is that one of the reasons RL is really hard is because if the reward is sparse, it's actually not so much an issue of being hard to specify. A sparse reward is usually easy to specify. Success or failure is quite easy to specify. It's the fact that you just don't learn against such a sparse reward. And so having the human in the loop for these longer horizon tasks, I think will really help, because it's very hard to shape a reward function to kind of shape it to give you a reward every time you make progress towards this longer horizon task without having some pitfalls where it somehow gets very excited about some early stages and keeps doing them. But with a human in the loop, I think we'll be able to somehow enable humans to more easily teach, because humans will be able to naturally provide a curriculum. Because humans might early on be pretty excited about just a little bit of progress and say that was better than this other one, which was quite bad. But then later on, you need to make more progress to be a winner in those comparisons. And I think that'll be very natural for humans to do that comparison, but much harder to program a reward function for. So natural curriculum is one of the big hopes that might come out of this.
Thank you. I have kind of a follow-up on this slide as well. Oh, well, before then, it sounds like we've got another question. I'll let the audience ask first. Do you consider the force, this is by Allah, do you consider the forces associated with the motion of the robot in the presented work even implicitly? So do you consider the forces even implicitly, and if so, how? If not, what are your thoughts on adding in forces?
Yeah, it's a really good question. There are some slides that were removed in the interest of time that actually hit upon this a bit. So specifically for the curl, the contrastive unsupervised representation learning with RL, if you dive deeper into where the vision-based learning with curl is not yet matched up with the state-based learning, well, it turns out when you dive deeper, it's where the images don't contain enough information to do as well. So the way we investigated this is we said, okay, there's the underlying true state of the world. We have access to that because it's a simulator. And that's what the standard RL runs from, state-based RL. And let's see if for our trajectories, we can learn a regressor from vision input and then output the underlying state. And where we succeed with the curl approach to match the state-based learning, that regressor is also very successful. Where there's still a gap is also where that supervised learning regressor, and supervised learning is well understood, there should be no challenges there. If it doesn't succeed once you make the network large enough, and it doesn't even succeed on the training data, when you make the network large enough, as a struggle succeeding there, then it means that the information just isn't there. And so we found that to be the case. And this is likely because of the contact forces that we're not able to predict, that for some tasks, we can't do as well as with access to underlying state. Now, of course, if it were a real robot, maybe you wouldn't do just vision-based, you would put some contact sensors into the feet or into the hands. But in the simulator, those contact sensors are, well, they're present, but we wanted to see how well vision-based can fare, and that is really the missing piece. I would say in about 10% of the environments, that was the case. This is a mix of running and manipulation environments.
Awesome. Well, thank you, Peter. I can always ask questions afterwards, so no need there. Any others from the audience before we move over to the next one? All right. Well, thank you again, Peter. It's been a joy having you join us and share all of this work with us.
Well, thanks so much for joining. And yeah, if anybody has any more questions, don't hesitate to send me an email. Thank you.
So thank you, Peter. And with that, we will move over to our last talk before a break afterwards. And I think Tapo can do the introduction there.
Thanks, Zachary. Thanks, Peter. So yeah, I'm very excited to welcome Aaron here to give a talk on Hello Robot in this workshop. Dr. Aaron Edsinger is the CEO and co-founder of Hello Robot. Aaron received his PhD from MIT CSAIL and has had a passion for building robots and robot companies. Aaron has founded 4 companies focused on commercializing human collaborative robots. 2 of these companies, Mecha Robotics and Redwood Robotics, were acquired by Google, after which Aaron was the director of robotics at Google. Today, we are excited for Aaron to share with us a bit about Hello Robot. Aaron, over to you.
Great. Thank you, Tapo, and thank you to the organizing committee for inviting Hello Robot to join. It's been a great workshop so far. Let me just share my screen. And okay, I just want to make sure we can all see that. Great. Okay, so today I'm going to tell you a little bit about a robot named Stretch, which is what we've been developing at Hello Robot. And you can see Stretch here with Henry Evans, and we'll tell you a little bit about the work we're doing with him later in the talk. What I want to cover is, first off, just the notion of inclusive design and how we got to this robot Stretch, our focus on community and building a community around the robot, and then some of the great work that's been happening with the robot to date. So inclusive design really kind of goes to the origin story of the robot. It comes out of the healthcare robotics lab at Georgia Tech, led by Professor Charlie Kemp. And in over a decade of research there, he found that mobile cobots, so that is a mobile robot with an arm that is safe to be around, he found that mobile cobots can really provide meaningful assistance, right, in tasks like feeding, shaving, putting on garments. And these are all things that people found value in. And I think there was also a realization that these robots weren't quite ready for the real world. They're in laboratories. They're hard to deploy in field. And so that was sort of the inspiration behind Hello Robot originally. Charlie in his laboratory built a cool prototype that I saw while I was at Google. And 2017, we decided to build a company around that prototype. 3.5 years later, we launched. So it turns out to be a lot of work and a lot of hard engineering to go from laboratory to product. We launched back in July with Stretch. And what we really set out to do with Stretch was to find a happy medium between robots that were small and toy-like and not necessarily very capable, and robots that were very capable, but also often very large, heavy, and complex. And so with Stretch, we worked really hard to make it affordable, compact, lightweight, human-centric, and capable. And 2 features that I think are very, very relevant here. The sense of portability with Stretch was really a focus early on. And we saw with Professor Laurel Riek's talk earlier, some images of emergency rooms and just how chaotic and cluttered they are. And you can imagine a large robot there, if say the batteries ran out and you weren't able to move it out of the way, how disastrous that could be. So really the ability just to pick it up and move it around was one of the design imperatives from early on. And also capability. For us, it was very important to make a robot that could reach the places in human workspaces, human environments in the home that matter to people. And for assistive tasks, that includes reaching to the ground, reaching to the back of a countertop. So we really took these design imperatives early on into consideration. And let me just play a video. These are some highlights from our launch video. It's about a minute long. I'll let that go here. Cool, so that's stretch. And let's get out of that. There we go. And finally, one last point around inclusive design I wanted to bring forward is that our founding advisory team included at the very beginning Henry and Jane Evans from Robots for Humanity, Vincent Duro, who's at Google. And aside from providing kind of great business guidance, they've also really helped inform the product and make sure that it met the needs both of the disabled community as well as the able-bodied community. And so really in the design of the product, we've really had them in the conversation from the beginning. Now on to community. So really for us, community and building a community around this robot is our top priority. Internally, we like to say that our North Star is to build robots that improve life for everyone. And we know that this is a longer term goal to get robots and the great technology that's in laboratories today out into the world. We also recognize that we just can't do it alone. We need everyone to sort of share, collaborate, combine forces to get there. And so we're really excited to build this future together where mobile cobots are sort of providing assistance for people who are in need. We recently had our first community event where we had over 60 researchers, engineers from academia, institutions, industrial, and not just in the assistive space, but also people who are doing service robots and industrial robots. But really what we're seeing is a vibrant community emerging where people are sharing their work and sharing results. And we're very excited to see that emerge. We believe very much in open development. So we have all of our code is open source. So you can go on GitHub today and see our commits and see what's going on inside of the company and with our customers. We have a tool share where people can share things for accessible technology, for example, the code, the CAD, the URDFs, all that you can find online. And finally, we have a forum where people are very actively sharing ideas, finding issues, trading notes, that type of thing. So it's very much part of the company and how we view ourselves in our community engagement. And since this is a workshop around learning, I wanted to make sure I mentioned that we are actively investing in supporting the machine learning community. We have some high profile researchers that are already working with Stretch and building software stacks with it. One thing to highlight is that it comes with a very well calibrated URDF, which might seem like a technical detail, but what that means is the point cloud from the camera matches very well to its body. And so if you're doing sim to real type of learning, that's really a huge enabler. And often, students can spend months trying to get a good calibration to work. We did that hard work for you all so that you can get to the more fun part of machine learning. Stretch is in the assistive gym, which hats off to Zachary Erickson for leading development on that. And finally, this summer, we have some product features coming out that I think the machine learning community will find exciting. We're moving to Python 3, we're moving to ROS Noetic. And one thing we heard multiple times from that community is they would like a more dexterous wrist to explore some learning policies. So we're coming out very soon with a new wrist that will enable some pretty awesome capabilities such as door opening, as you can see here. Cool. Okay, so finally, let me talk a little bit about some of the great work that's happening with Stretch. We have a project this summer with a occupational therapy doctoral student, Vi Nguyen, from Pacific University. And through her, this collaboration has emerged, and it involves Professor Maya Chakmak at University of Washington, Tapomayukh Bhattacharjee at Cornell, Professor Wendy Rogers at UIUC, and then of course the Hello Robot team. And what we're doing is we're putting Stretch in the home of Henry and Jane Evans. And over the summer, we're going to see what can it really do, and where is it valuable, where is it useful, what are the pain points, and really get kind of a long, relatively long-term study over the summer to understand the capabilities. So we're very excited. We just kicked off this work. A little bit about that team. So Wendy Rogers' group at UIUC are really focused on the human factors side of it, and how accessible is this technology. Her focus is primarily older adults. And looking at, can you teleoperate it effectively, hands-on or eyes on or eyes off? What is the out-of-box experience? Can an older adult set this up? Things about kind of the accessibility of the technology and really thinking about the community that it was designed for. With Professor Maya Chakmak's group, they developed this great teleoperation interface built on top of the open software that we've provided, and have been doing studies about how effective is it when you do remote operation of it? What types of tasks are achievable? How long does it take to do different parts of the task? I think this is work that's in process of being published. And they developed this interface, they call it Forky. Here's a little video playing of Forky. But what it lets you do is to drive the robot around through a web browser. And the video, you can see a little bit of that. This is the interface that Henry Evans will be using in this project this summer. They're actively modifying it for him, and part of the plan over the summer is to rapidly iterate the interface, the tools that the robot is using, and sort of land in a whole new part of the design space, hopefully by the end of the summer, based on this closed loop feedback with Henry. So we just had our first deployment of Stretch into Henry's home on Thursday. And for us, this is a big milestone. It's been almost 3.5 years in the making, working with Henry, talking about this robot, planning around it. And we finally got it into his home just a few days ago. So on the right there, you see V, you see Henry and Jane, you see William, Henry's caregiver, and Elliston Franks from Hello Robot. And we're very excited to see what this team comes up with this summer. One thing, a couple kind of points to highlight. On the left is a tool that V created. And what's exciting about this to us is, she's not a roboticist. She comes out of the occupational therapy field, where they have a different set of tools in the toolbox. And so this is kind of an assemblage of things that she thought would be useful, and you find on Amazon, or things that she's used in her practice, but really brings a different perspective to building tools for robots. And it'll be exciting to see what else she comes up with over the summer. On the right, you can see Henry using this Forky interface to drive the robot arm to wipe his chin. And of course, these are very early, since we just spent one day in his home so far. Here's a couple of videos from that first exploration. So here, Henry is using the interface. You can see he's using his left thumb to control a mouse to drive Stretch to pick up a towel. And here you can see a multi-use tool that V developed. So here he can control the robot to wipe his face. And then it can pivot around and bring a brush over to his head to scratch his head, which is something that he likes to do, to be able to itch a scratch. So, one day in, these are very early sort of explorations, but we're excited to see where the summer takes us. So with that, I will hit pause and take any questions you might have.
Thank you, Aaron. Great talk. It's nice to see Stretch being used in real scenarios. One thing I forgot to mention is that Hello Robot has been kind enough to sponsor a $1,000 monetary award for the best contributed presentation in this workshop. So thanks again to Hello Robot for this. Do we have any questions for Aaron or the Hello Robot team from the audience? while people think, I do have something that I wanted to ask Aaron. And so, Aaron, it's exciting to see that there's a community building up around Stretch to be able to use Stretch for different tasks. And I was wondering, from this initial deployment, what have you learned from the customers in terms of like what worked and what are the things that need to be changed? For example, I was very excited to see this new development on a dexterous wrist, and also moving to Python 3, Rosnoitic, and things like that. Is there anything else that you have learned from this initial deployment for Stretch?
Yeah, well, we've learned a lot, and that's the beauty of getting out there and sharing your work is you get feedback. One thing that we've always thought was important for Stretch is that it's easy to deploy, right? I can literally put it in the back of my Prius and drive it around. And so we're starting to see customers push on that, especially as the pandemic is easing up. And with that becomes, there's issues around charging, right? So now we're developing a charging station, right? There's, just a lot of practicalities around fielding robots. And I think that's sort of one bit of feedback and we're trying to invest in, is to support our community to actually get the robot out in the world and out of the laboratory. We're very excited to see that happen. So we are doing things like that. And again, another emphasis for us is to really support the machine learning community with the tools that they need to quickly integrate. So we've been investing in simulation. We've been investing in things like the wrist, et cetera.
Awesome. Thanks, Aaron. I do see a question in the chat. So Michelle is asking, are you exploring the use of Stretch by caregivers to control the robot, also used with cognitive issues?
Yeah, absolutely. So actually with Henry and Jane, Jane is Henry's primary caregiver, and we are over the summer going to explore her use of it. And she already did teleoperate it, and to do the direct teleoperation, it's, if you're a gamer, you can kind of figure it out pretty quickly, but for someone who hasn't played games, it's a little more challenging. So that's one thing we'll be looking at over the summer is how can it assist her and care and relieve her burden of care. That's something we're very excited about. So hopefully by the end of the summer, we can say more about that.
Michelle also has a follow-up question on how are you assessing formally usability?
Yes, well, I'd say that's out of my expertise, but I will say that Professor Wendy Rogers and her group have done a great job so far looking at usability, doing a very sort of data-driven approach to usability. With this project, I have to let the researchers speak to their work probably.
V is in the audience, by the way, and she's really the leader of this effort, and it has a lot of putting a lot of effort from the OT perspective on assessment, and so look, there she is.
Hello.
V, would you like to take the question?
Sure. Yeah, I'm gonna read.
So Michelle's question, V, is about assessing usability with Stretch.
Yeah, no, I think that's a great question. So part of, in addition to knowing we're having Henry use it with the web interface, I'm focusing also on that caregiver experience for Jane. And in my field, we believe functional performance for activities or activity of daily living are applicable for both the user and their caregiver. So our thought is, I'm going to ask her interview questions, for example. A lot of the caregiver assessments out there, outcome measures, I think aren't really made for this type of industry. A lot of it just talks about burden, and she may not feel those certain things. So I'm working on ways to create interview questions. I'm asking her about what do you think Stretch can do for you? She's aware of that it can actually be automated to clean the floor with the Swiffer. And so she got really excited about that. She's like, that would be fantastic if it could clean my floor, because it would just free up so much of her time to be able to do her daily activities. So those are some things I'm still exploring, but that's definitely something that I'm going to do in my project, addressing the caregiver role and how do robots best support them to do their daily activities as well, while allowing individuals like Henry to achieve independence in his. I hope that answered your question, but it's all being developed, and I finished my school in August, so there will be a complete manuscript all about it. So then I will definitely share that with everyone.
Thanks, V. There's a follow-up question, Aaron. A brief by Joao. Again, I'm hoping I'm pronouncing your name correctly. If not, please feel free to correct me. So the question is about a brief inquiry on safety. Is Stretch a cobot? And do you have any comments on efforts to reduce video latency during remote teleoperation?
Sure. Well, Stretch is a research platform, right? So it's not safety certified in the sense that maybe an industrial robot arm is. Standards for safety are very different in the industrial space, of course. But we view Stretch as having a lot of safety features because it was designed to be low mass, low inertia, and have contact sensitivity. So it can, didn't show video, but if it makes contact with somebody, it'll stop. It can sense that detection. And so really through good design and good design intent, we believe we're in a very good part of the safety space, but as a research platform, we haven't gone the next step yet in terms of a certified safety, but we do consider it a cobot, and that is meant to be collaboratively working around people. With respect to video latency, I'd say that's probably something out of my domain of expertise. It's not something we've been tackling internally in the company just yet.
Well, I can say, by the way, the open source code that we released that Professor Chakmak's lab has done such a great job on. By the way, I usually have my academic hat on. For this one moment, I have the Hello Robot hat on. It's using WebRTC. So it's actually basically the robot and the operator are basically teleconferencing with one another using web standards. And WebRTC is remarkably good in terms of low latency.
Thanks, Aaron, Charlie, and V for answering all the questions. In the interest of time, let's end this session now so that we can have like a 5-minute break before our next speaker. Karen, and I see Karen here.
It is a great pleasure for me to introduce our next speaker, Dr. Karen Liu, who's an associate professor in the computer science department at Stanford University. Now, I've been working with Karen pretty much my entire PhD, so I know her very well. I've had an absolute joy working with her. So I'm very excited for everyone else to learn about the research that she's been doing, both her and her students. So prior to joining Stanford, she was a faculty member at the School of Interactive Computing at Georgia Tech and received her PhD from the University of Washington. And her research interests lie in both computer graphics and robotics, including physics-based animation, computer animation, optimal control, reinforcement learning, and computational biomechanics. She's also received several awards, including the Career Alfred Sloan Fellowship, TR35, and the Significant New Researcher Award at ICRA. So with that, I'd be happy to hand it over to you, Karen. The stage is yours.
Thanks, Zachary. Let me first start with sharing my screen. Okay. Do you guys see the screen?
Yep.
All right, great. Well, thanks for the introduction. It's definitely a pleasure working with you as well. In fact, a lot of things I'm going to talk about today is through collaboration with Zachary and Charlie Camp. All right, so today I'm going to talk about the role of physics simulation for assisted robotics. And by physics simulation, I mean simulating the entire world, which I realize is a little bit broader than what I described in my abstract, but this is what I'm going to talk about today. Physics simulation has always been a good friend to scientists and engineers, but its importance has been drastically elevated in recent years due to the rise of deep learning. It all starts with this desire to build AI-enabled robots that operate in a dynamic and unstructured environment and interact with humans, of course. But acquiring robot training data requires careful instrumentation in physical experiments, which can be challenging and risky to the robots and experimenters. And for many physical tasks interacting with humans, the sheer quantity of training data needed for a learning algorithm is just not possible to acquire in the real world. On the other hand, physics simulation can provide a safe and inexpensive virtual playground for robots to acquire physical skills and even learn from making mistakes. Simulation also allow engineers to rapid prototype different design of robots, and various virtual humans and environments can be easily created in simulation, so the robot can just gain experience by interacting with a wider range of scenarios. And finally, simulation can easily scale up to produce training data as much as needed at a low cost. But there's a problem. Control, policy, learn entirely in simulation can fail when deployed on the real hardware. This is a challenge known as the sim-to-real gap. And most of the robotics researchers attempt to cross the sim-to-real gap by innovating better control policy for the robot. And we wonder if we can achieve the same goal by innovating better simulation techniques. And speaking of a better simulation techniques, we know who we should be talking to, right? Computer animation researchers can produce ultra-realistic visualization for physical phenomena, such as this plate of soba noodles swimming in way too much oyster sauce, like my mom would say. Oops, sorry, is it still playing? Oh, good. Still playing, the camera, the video? Okay, good. So but the simulation today can't really predict particular scene in the real world, such as this particular robot manipulating this particular pot to make this particular pasta sauce, because we don't know how to build an accurate model for complex interplay of multiple physical regimes in the real world at the level we can simulate it. And likewise, we can simulate the virtual humans perform complex motor skills that looks very compelling. But when it comes to predict the movements of a particular person interacting with the real world, we don't have a clue whether our simulators in any way reflecting reality. And this example was even more challenging than the soba noodle because we need to simulate both the mechanics of a human body and its control. Simply put, the simulation tool today is not very effective. On one hand, we have a lot of models that can create some phenomena, but they are not good for predicting a specific real-world environment. On the other hand, we can collect a lot of data from the real world and perhaps build a data-driven model, but it's not going to generalize to the extent our physics model can. So what is the principal methodology to integrate data with physics models? Ideally, we would love to have a customizable physics engine that only takes a small amount of the real world data from the environment of interest. And then we use this physics engine to train policy that can cross the sim-to-real gap. So what's this physics engine? Well, at the heart of the simulation is an ordinary differential equations, but how do we utilize this physics engine given this framework to how do we utilize data given this physics simulator? An obvious place we can inject the influence of the data is this simulation parameter mu. This could be any parameters involving this in the simulation, such as the geometry of the agent or the friction coefficient of the surface in the environment. And one common way to do that is called system identification. We can extend the system, we can execute a system in the real world to collect the data, and then we can optimize the parameter mu to fit the data. This works well if you only have a small amount of data to parameters to identify. On the other hand, recent advances in machine learning open the possibility of using a large amount of measured data to replace physics model with data-driven models. But they perform poorly when operating outside of the distribution of training data, which is very likely to happen for a dynamic system executing for a long period of time with external perturbations. So between these two extreme approaches, there should exist many other ways to integrate data with a model such that they can be truly complementary instead of overriding each other's strengths. So to this end, we need to consider other components in the physics engine, such as contact handling that compute the contact forces and boundary constraints that enforce the range of motion and the actuation capability of the robots. So now our simulation framework looks much more complex. In fact, we typically end up solving in DAE rather than just in ODE. But this also means that there might be a lot more opportunities to learn from data. So today I will mainly talk about the two components, contact handling and stay in action boundaries. But let me first shamelessly make an advertisement on one of our papers that works on making model parameters more learnable. My student Yifeng will talk about how he creates a hybrid simulator and train it like an RL agent using adversarial learning on Tuesday at the humanoids and animal noise session. All right, his work augmented a classical physics simulator with learnable state action dependent parameters. Now, what about other components? First, I'm going to talk about learning opportunities in stay and action boundaries. The need to make the stay and action boundary learnable becomes more apparent when we bring in another layer of complexity into the problem of sim to real. That is, how do we transfer a policy that physically interacts with the person from the simulated world to the real world? For example, if we are training a healthcare robot that assists the person to put on clothes, how can we make sure that the policy trained on the virtual human will work on the real person? And directly deploying the RL policy, which is the one you see on the right, on the real person is just not a wise thing to do. So we need a better simulator for human so that a robot trained to assist the virtual human in simulation has a better chance to cross the sim to real gap. Such a human simulator should realistically reflect the person's range of emotion and the dynamic capabilities. And the naive way to define the range of emotion is to simply set some arbitrary upper and lower bounds on every single degrees of freedom of the human model. But the real range of the human emotion looks a lot more complicated than the simulated one with the box constraints. And the second challenge is that the range of the angles vary depending on the position of the other joints. For example, I can bend my elbows almost 180 degrees if my arm's in front of my torso, but the range of motion of my elbow is largely limited if I put my arms behind my torso. So with these two observations, we redefine the upper and lower bounds as a function of a joint configuration Q. However, a more clean representation is using an implicit equation. So we define a function D to represent the boundary of a human range of motion. So how do we learn such a function, right? Luckily, Michael Black's group at MPI has created a very comprehensive database of human poses, among many other great things they did. So this database provides the training samples we need to learn the function D. And once this is state-dependent boundaries condition D is learned, we need to enforce it in the physics simulation process to ensure that the next state we integrate to is still within the boundary, right? So this can be done by solving the constraint for satisfying these conditions. And the fact that D is a neural networks makes computing this gradient Jacobian very efficient. So let's look at some results. Here we simulate two completely passive human agents under gravity. The one on the right has the standard box constraints on the joints, and the one on the left uses our learned joint limits. So without any active internal control forces, the joint limits alone already gives the character a little bit more human-like behavior. We can also utilize these gradients of the neural network to solve inverse kinematics problem, where solutions are confined in the set of valid human poses. And in addition, we observed that our joint limits constraints can mitigate the issue of self-collision because many of the self-penetrating poses are not presented in the database to which we learn our function D from. So now we know how to model humans' range of motion better. What about the dynamic capability of a human? Specifically, what are the joint torque limits that reflects realistic capability of a human's musculoskeletal system? It turned out that using conventional box constraints to enforce joint torque limits is also a really bad idea. Here's a motivating example. If I'm defending myself against someone bigger than me, one effective strategy is to put my opponent's arm behind his back because anyone in that configuration can barely exert any torque. So this leads to our first observation that joint torque limits should be state dependent. Another fact about our muscular system is that each of our muscles spans multiple joints, and there are multiple muscles exerting torques around the same joint. So this leads to our second observation that torque limits also depends on the current torque at other joints. So we start out with a conventional box constraints for joint torques, but with our first observation, we know the torque limit should instead be a function of the joint states. And by second observation, we know that torque also depends on each other. So therefore, we model torque limits as an implicit function of Q, dQ, and tau. Those are the states and control variables. Our hope is that this function can incorporate muscle capabilities, but only use information available in the joint torque space. So we define C being -1 if there exists a valid muscle activation pattern such that it could produce the torque at the current pose. And we define C to be 1 otherwise. So in order to evaluate C, we basically need to solve a feasibility problem. We can relax the problem to an optimization problem, but still this makes evaluating C very costly, especially when evaluating it in the inner loop of an optimal control problem. So perhaps we can build a model to approximate this optimization process, and this will allow us to quickly figure out whether a proposed joint torque is human realizable or not. But how do we collect training data to train such a model? Turns out there is this wonderful set of the muscle modeling simulation tools called OpenSim, which with OpenSim, we can solve the optimization problem using anatomically accurate human muscle models. So we utilize OpenSim to provide 1 million optimization instances as training data, uniformly distributing the joint space so we're not biased towards a specific task. We could generate as many training data as we need, since offline simulation is essentially free. So this learned joint torque balance can now be directly used in the optimal control problems. We can replace the constraint torque limits with our task agnostic state dependent torque limits function C. And this function is represented as a neural network, which means we can calculate gradients very efficiently. In addition, we can also replace the box joint limits with the state dependent joint limits learned from the real human poses, which I just talked about. And together we have a human simulator learned from biomechanically correct model and the real world data. So let's look at some example. In this task, the agents try to optimize the motion to jump as high as possible. And using conventional joint motors, shown on the right, the green character, you can see that it could jump higher. But it turned out that this green character hyperflexed its ankle, so it has a longer distance to accelerate before leaving the ground. However, this is impossible to achieve because the real human cannot apply large torque in this hyperflexed pose. So our model correctly prevents the optimizer from exploiting the simplicity of the model without the need to simulate muscles and tendons. We also compare our method to motion generated using complex muscle model, basically using OpenSim to do that. And our motion is qualitatively similar. But our torque space method takes 50% less computation time, even in this very simple 2D example. In our other reinforcement learning examples, the performance gain is much more significant. So we have added more learning opportunities in our physics engine by representing the state and action boundaries using 2 neural networks and learning their parameters from biomechanical data and the real human data. Now, we still have one problem here. A learnable physics engine is useless if we don't know how to train the parameter efficiently. We could always use some stochastic gradient-free optimizer, but they do not scale well when the number of learnable parameters is large. It would be really great if the entire simulation cycle is differentiable, so we have the flexibility to learn any part of the physics engine efficiently. It turned out that most of the physics engine is differentiable, and the only component that is not naively differentiable is the contact handling. And so the question is, how do we make it differentiable too? So contact handling essentially is a process to find the contact force Fc and the relative velocity of the contact point at the next time step, the Vt+1, such that they satisfy the equations that enforce contact dynamics along with the dynamic equations. So this system of equations is called linear complementarity program, LCP. And turn out that we can write down the next velocity as a linear function of a contact force with a matrix A and a vector B defined by other terms in the physical equations. So now we can have a concise description of LCP. It's a mapping from input A and B to output FC, which is the contact force solution. If we embedded LCP as a layer in the neural network, the forward pass will be just computing the contact force that satisfies the LCP. And our goal is to be able to compute the gradient of this layer, which is the gradient of contact force at the solution with respect to input matrix A and vector B. Computer gradients of the LCP is not easy, but there are a lot of really cool math development in the recent years, which could be very helpful. So from the prior work, we learned how to compute the gradients of a quadratic program through its KKT conditions. And if you look at our LCP, it looks just like a KKT conditions for some QP, right? So we can directly use the same machinery to get the gradients. But treating LCP as a generic KKT system requires solving a very large LP, which is not ideal. So we noticed that this generic approach completely ignores the unique structures of our problem due to the contact physics. If we try to exploit our knowledge in physics, we can develop better algorithms to compute the gradients for LCP. So we know each contact points can be in one of the following three states, according to the LCP: the clamping mode, in which the objects will remain in contact in the next time step; separating mode, in which the objects will move apart from each other in the next time step; and the tight mode, which in which both relative velocity and contact forces are zero. And there are other modes related to frictional contacts in the tangential direction. They can be all folded into LCP format, but we're not including there here in this talk due to the time constraint. If no contact points are tied, LCP is actually strictly differentiable and gradients can be analytically computed. So let's exclude the tied case for now. And we can group the contact points into the clamping set and separating set and rewrite LCP as follows. It seems like we're making the problem worse because now we have more gradient terms to consider. But we know that the contact point for separating contact point is, the contact force for separating contact point is zero. And the relative velocity for the clamping contact point is also zero. These conditions allow us to cancel off many terms in our equations. So now LCP can reduce to just these three linear equations. And we can then reason about each gradient term and found out that most of the terms are zero. So for example, this gradient term measures how solution FC changes, which with a change in the submatrix ASC. And the relevant equation of this gradient term is the third one here in red. So according to this equation, a value FC should map to a positive value on the y-axis. Now, if we perturb ASC a little, we change the slope of the equation. And since the solution AFC holds strictly in this inequality constraint, there's some non-zero room to wiggle the slope without violating the inequality. This means that, sorry, let me just go back here a little bit. This means that the same FC can still hold true, can still satisfy this inequality. We don't need to change that. Therefore, the gradient is zero. The only gradient term that we will actually have to calculate because they're non-zero are these two terms shown in red. So in practice, we could calculate these two gradients using this analytical form and turn out that we still have to calculate, or still have to invert this matrix ACC. But this matrix ACC is just a submatrix in this large KKT system. So inverting this case, this much smaller matrix is much more desirable. And finally, we need to talk about the tie case. In fact, the tie case is the only reason the LCP is not naively differentiable. To see that, we can write down the linear relation of a tie contact point and plot out the relation in 2D. So the current solution must lie in the origin because both velocity and the contact force are 0. As we add an infinitesimally small positive value to b tilde, we see that the current solution does not hold anymore, and we need a positive velocity to balance the equation. This means that the contact will switch from tie to the separating mode. On the other hand, if we add an infinitesimally small negative value to b tilde, the contact in this case will immediately switch to clamping mode. And the gradient for the clamping and separating case are both valid subgradients for the tied contact points. So which means during the optimization, you can actually just choose, arbitrarily choose one. And in practice, encountering tied contact is quite rare because there's always numerical approximation in our calculation. So the takeaway here is that given a solution, the LCP contact handling is almost always naively differentiable. With this differentiable contact handling procedure, we now have a feature complete and very fast differentiable physics engine. Here are some results of solving optimal control problem using gradient-based optimizer. All the examples we present here require contact states to change, and this type of a problem is very difficult to solve using gradient-based optimization methods in the past. We also open source our differentiable physics engine, so anyone can just pip install it and play with it. There's a lot of a physics engine out there being used by a lot of people already, so we don't really want to create a new physics engine just for its differentiability. So instead, we make an existing fully functional physics engine, Dart, differentiable, without modifying its constraint handling and without sacrificing the speed. And finally, we can make our learnable physics framework completely differentiable, which allows every parameter in this physics engine to be efficiently learned from data. So I don't know how much time I have, but in the last few minutes, I'm going to switch gear just to talk about some current progress of our work on transfer policy that physically interacts with a person from the simulation world to the real world. When developing a robot aware of a human in the scene, the simulation can play a crucial role, both in terms of perception and control. So let's first talk about the human-aware robot sensing. A large body of past work in robotics and computer vision always focus on vision perception. But there are many other modalities of perception playing critical roles in human-robot interaction. For example, human caregivers heavily rely on haptic sensing to provide physics assistance. So can we teach a robot to understand how a person feels from the limited sensing capability it has? So in this project, this is by a project collaboration with Charlie and Zachary. In this project, we want to be able to estimate what human feels from the force applied at any effectors of the robots when dressing a person. So on the right, you're seeing the simulation of the person's arm and what the robot thinks the force is being applied on the humans in real time. And this type of a haptic perception is really important for application like dressing because occlusion can happen all the time. And specifically, we learn an estimator model that estimates the current force map from the history of force torque sensors and at any factor of the robot. And all the training data is from from the cloud simulators. And to test our estimator, we command the robot and effector to follow a random trajectories. On the left, you see the pressures on the arm predicted by our estimator. And on the right, you see the ground truth obtained through the cloud simulator. Basically, all robots knows are these three vectors here and apply it at its hand. And from there, the robot needs to be able to imagine the pressure forces applied on the human's arm. Another project, it's also collaboration with Charlie's lab. We are interested in estimating 3D pose when the person is resting on bed under blankets. The 3D human pose and shape estimation for for sleeping or for someone lying on the bed is really important, and it can have an implication in a lot of healthcare applications such as sleep studies and remote patients monitoring, SOAR management. But line of sight perception, like a camera, is complicated because of the occlusion So one idea is to use pressure sensing maps. In this project, we introduce a data-driven method to infer 3D pose from a pressure image recorded by pressure mattress pad. But collecting this type of training data is not easy. So alternatively, we could use simulation data to train the model. We modeled this pressure sensing pad and underlying mattress as collection of the particles and carefully identify the coefficient of the simulator based on the readings from the real pressure sensing pads. And we use our customized physics simulator to synthesize pressure images and create a large set of label training data. And the simulation process is essentially free and allows us to cover a wide distribution of the body types. And here we show that the model trained with the synthetic pressure images, but tested it with the real pressure images produced by real people lying on the mattress. And our model is able to predict the 3D models and body shapes reasonably well. So robot perception is crucial, but at the end of the day, what matters is whether we can develop a robot policy that takes advantage of those rich input perception and make it the best possible decision. Since the human and robots need to learn to collaborate with each other to achieve the task, we take a co-optimization approach to simultaneously train control policy for the robots and for the human. And the action robot and humans produce will be tested simultaneously in this shared environment. And one nice thing about training policy in simulation is that we can train with a variety of environments in parallel. If we think the human is a source of variation in the environment, this means we can train a policy against a wide range of a population simultaneously. And the robot will be trained to robustly serve not just one particular human model, but this continuous range of humans who all attempt to do their best to achieve the task within their capabilities. So ultimately, we are co-training an adapted policy for the human and a robust policy for the robot by applying domain randomization on the adapted human model. Here we visualize the learned robot policy interacting with a range of the different humans' behaviors. Compared to the normal humans, a human with a weaker arm changes the actions of the robots. It's subtle, but you can see that the robot ended up doing more for the human when it's dressed as a weaker human. And similarly, when the human has less precise and more noisy movements or limited range of motion, the same robot policy is still able to achieve the task. So after training a policy in a simulation, we have successfully developed a RL trained policy on a real robot, PR2, dressing another robot, which follows the virtual humans policy. So this robot-robot interaction scenario is clearly an intermediate step towards serving the real humans. So eventually we want to be able to deploy the RL policy on robots. Currently, we have also achieved assistive dressing on real user with disability using a model predicted control style policy. And here are more examples of apply our MPC controllers along with haptic sensing on users with disability. We also introduced a capacitive sensor, which I didn't have the time to include in this talk. And beyond dressing, we expanded the simulation environments to train robots for other activities of daily living, such as drinking, bathing, limb manipulation, and feeding. And we developed an open source software called Assistive Gym, which is designed to provide training environments for physics, human robot interaction, and robotics assistance. And hopefully this open source can facilitate more follow-on research in this very exciting domain of assistive robotics. So with that, I would like to pass the mic back to Zachary and maybe take questions some other time.
Yes, well, thank you, Karen.
Sure, thank you
very much. Applause from the audience. I'll applaud for the audience. Yeah, if you have time for a few questions, we can have a few at the moment. Do you have time for a few questions? If so, we can see if the audience has any questions for you. I, of course, have some as well. Get started. So I'll ask one just to kind of get us started here. So at the kind of beginning, you were talking about sim to real and closing the sim to real gap. And I was wondering if you've, and then you were talking about right after that, these human models, right? Looking at building human models in simulation that are better models for human joint torques and joint limits. And so I was wondering if you looked at closing the gap from that, looking at bringing these types of human models back into the real world, either by training a robot based off of those models and then transferring that model to the real world, or directly taking those models into a realistic, more realistic scenario.
Yeah, so the right, so I guess let me see if I can summarize your question real quickly. You're talking about actually how to utilize these models we build for sim to real, right? How in terms of the progress of sim to real, how do they, what roles do they play? I mean, they are tools, right? We're building simulators, so we're in the business of making tools. So it's really up to a lot of robotics to think about ways to use them. So you can use it for IK, right? Something very fundamental. You can improve your trajectory optimization, right? Because now you have a better constraints. You can improve your reinforcement learning because now you define an action space that looks more like a human rather than just some, random arbitrarily set, action space. And we in terms of our own work, we use that for the, so for example, like the robot human co-optimization, that project, we use that model, the joint limits, the more human-like joint limits as the base to simulate human motion. Yeah, so you can just basically use them to generate more plausible poses. Oh yeah, the Henry's work too, right? The one that used to generate 3D poses as a training data for the for estimating the 3D pose and the body shapes.
No, it definitely makes sense. Thank you. Tools for the research community. Any questions from the audience members? Feel free to unmic yourself if you'd like, or type in the chat. I'm happy to read them. I've got another, I think it's a quick question for you, Karen, which is, so Nimble Physics, the new differentiable physics simulator, does that support soft bodies? Or do you have any thoughts about that as well?
Yeah, it does not currently, but I think it's probably not too difficult to do that. I'm just gonna put myself out there and then worry about being attacked later. I think the hardest thing is, to handling constraints properly with rigid body contacts. And if it's your soft body comes with all different kinds of problems and issues and challenges, but getting gradients through that is not one of them.
I have a question, I guess.
Charlie, hey.
Hi, good to see you. I really enjoyed that. That was excellent. Yeah, this is a little random, but I mean, you're in two different worlds. I mean, you've been in the computer graphics community and you're also very much in the robotics community. And I guess I have this naive perception that movies and computer games have driven a lot of developments in the physics simulation world. And I'm kind of curious, for something like Nimble, what do you see as the future in terms of things driving forward the physics simulations? Is robotics one of those? Is machine learning? And how do you see that playing out? And curious.
Yeah, I think the applications from like the conventional applications on the graphics side will always be there. We will always want a better, more like faster, more realistic physics engines that we could use to create beautiful imagery. But there is just such a wonderful uncharted territory though for a physics engine to play a role in robotics has started already, but then there's an in-body AI, right? Computer vision people start thinking and moving in that direction. They're all rushing into building this physical, like interactable and photorealistic worlds to train robots interactions. So physics is definitely going to be it plays differentiating roles in there. No pun intended. So I think And to me, I feel like the most exciting application is not RL. A lot of people think learning, because, RL needs so many samples to train anything. You can only do it in simulation. But I feel like this is a kind of transient needs. Eventually RL would be better, and physics engine might be better as well. So it would be great that physics engine can play that role while RL still requires to be done in simulation only. To me, the most exciting thing in the future is using physics engine as an online predictor for the robots, right? So you're really using it as an NPC fashion, but it's blazingly fast that you can do it. So you can predict the future, and you can do it very quickly to update your model as well, because it's differentiable.
That was great. Thank you. Very cool.
Thank you so much, Karen. So with that, we'll move over to the next speaker. So again, thank you, Karen, a round of applause.
Thank you.
And it's over to you, Tapo, to introduce our next speaker.
Thanks, Zachary, and thanks, Karen. I think that that's a really very exciting vision to have, using physics simulation online to be able to predict things. I mean, that's exciting. So it's my great pleasure to introduce our next speaker, Jeremy. Dr. Jeremy Marvel is a research scientist and project leader at the U.S. National Institute of Standards and Technology, or NIST in short. Dr. Marvel received his PhD in computer engineering from Case Western Reserve University. His research interests include intelligent and adaptive solutions for robot applications, including human-robot and robot-robot collaborations. He currently leads a team of scientists and engineers in metrology efforts at NIST towards the performance evaluation of human-robot teams. Jeremy, it's over to you. Looking forward to your talk.
Awesome. Thank you, Tapo. Can you hear me okay? And can you see the screen okay?
All good. Yeah.
Excellent. I am jealous of your animated background, by the way.
It's just the default background. But yeah, I love my background. Yes. I wish I was there. Wishful thinking.
So thank you again. Again, my name is Jeremy Marvel, research scientist at the National Institute of Standards and Technology. Basically, what I'm here to talk about today is what we as a community need to do in order to move toward test methods and metrics that can be widely and consistently applied to caregiver research or caregiver robotics research. Hello, computer. There we go. So for those of you who are not aware of what NIST is, I know many of you are. Here's a very quick overview of what NIST is. So we are actually part of the US Department of Commerce. So I am a Fed. Our mission is to promote US innovation and industrial competitiveness. And we do this by advancing measurement science, standards, and technology, mostly in order to enhance economic security and improve the overall quality of life. Many of these statistics that you see here are actually pre-COVID. Right now, we are actually still in phase 1 of reopening. We've been that way since last June, so almost a year now. We are at about 20% of capacity, so it makes human-robot interaction research quite difficult when you can't have people in your facilities with the robots. Again, I am a federal employee, so I actually do have to give this disclaimer. There may be things in here, technologies or various name brands that are mentioned. I don't mean to say that these are the best. I don't mean to say that these are the worst. I use these only as illustrations. I am also required by law to be dry and boring and to cite at least one standard. That is a requirement for NIST. So anything that resembles humor is purely the figment of your own deranged minds. When we're talking about metrology, what do we actually mean? Many of the cases, what we do at NIST are going to be industry-driven performance requirements. So things that industry identifies as being something that's important to them. And we're not necessarily talking about just like manufacturing kind of industry, but we're talking about service robotics, medical robotics, caregiver robotics, military robotics. All of these have stakeholders that have specific requirements. And it is our responsibility to try to capture these as best we can and to develop the metrology that actually captures all of these different interest points along a different spectrum of performance. So these pass-fail kind of tests that you see, we don't really like those. We want to be able to say, where on this spectrum do you actually fall? And what can we actually gather from this information? So not only do you have an idea as to whether or not your systems are performing as expected, but you can also identify the sources of potential failure, or in some cases also predict failure coming up. So the prognostics and health monitoring of your robotic systems. Ideally, we want our test methods to be design agnostic. So not something that is specifically for a given system or robot is not as helpful to the broader research community or even to the market as something that is more agnostic to the technologies being investigated. So you'll often see in the industrial realm test methods and metrics for performance of industrial robots that do not take into account the actual design, the number of degrees of freedom, the design characteristics, the capabilities of the robots, but more along the lines of, here we're going to test the repeatability and accuracy of the end effector as it goes into Euclidean or Euler, Cartesian. I can talk. It's been a day. Cartesian space. And similarly, what we want to do is then take these industry requirements and then kind of push them back out into the research community, saying that these are very real problems that need to be solved, and basically show that there are opportunities out there that can actually be used to influence and to drive technology forward, and that there's a very real industry need that if you can meet that need, you can actually make a lot of money. So what does that mean in terms of HRI? There are whole numbers of different kinds of factors that you can look at in terms of HRI metrology. These are just some of them. Many of these are actually quite common, like safety and situation awareness, effort and trust. But at the same time, there's also things that may not necessarily be as kind of front and center in your mind when you're working on any kind of human-robot interaction or interface. And that could be along the lines of, well, how easy is it to program? How accurate does it do its task? What is the impact on the human? What is the impact on the robot? What is the impact overall on the team itself? So there's any number of different metrics that you could be looking at. And it's it's frightening, it can be. So to quote Thomas Dolby, I don't want to necessarily blind you with the science. So what I want to do is actually kind of reduce it down to what we actually care about within the caregiver HRI community. Obviously, safety is going to be there. Effort, we're talking about physical and mental effort in order to be able to use the robots, either as the recipient of the caregiving or as the operator who is actually setting up the robots to do the work. These robots are intended to do any number of different tasks, and so they have to be able to do them to some degree of proficiency. And that could be food preparation, it could be setting reminders or calling on emergency services if there's an accident. Same thing with mobility assistance and other things. You also have this big issue of acceptance or trust. And this is, again, not necessarily just on the part of the person using the robot, because obviously if they don't trust the robot, they're not going to use it. But also people who are going to be investing in these kinds of technologies need to have trust that the robots are going to do what they're expected to do, that they're going to be safe when they're supposed to be safe, that they're not going to do something that they're not supposed to do. And especially when you're thinking in terms of some potentially really dangerous again, potentially, applications where you may actually have robots that are carrying blades or needles or medicine. And so if a robot is supposed to give you a certain amount of medicine and too little is not going to be effective and too much can be fatal, you have to have faith and trust in that robot system to be able to do that task without incurring negative repercussions. So okay, so we got the metrics right here. So everything is solved, right? Unfortunately, not so much. There are multiple problems with this. For instance, actually asking the very simple question, what makes a caretaker robot suitable for its task? I don't know if anybody can actually answer that. In many cases, it's going to be a custom built or purpose-driven design, which is good. But what happens if they want to start expanding beyond that? Do they necessarily have that background research on the design front or even on the programming front to be able to handle all situations, the uncertainty of the squishy humans, that kind of thing? Same thing, how do you assure the performance of what is effectively going to be a black box? Right now in the research community, we value open source. And this is wonderful, so we can actually see what's going on, we can improve on it, we can identify potential hazards. But once it actually goes out onto market, you no longer have access to the underlying source code. And as a result, you have to be able to assess and assure something that you have absolutely no control over beyond what is given to you in that user manual. Again, what is the metric for intuition? So a lot of people are talking about intuitive HRI. As soon as anybody can tell me how to measure intuition, I guarantee you there's going to be a lot of money associated with that, because you will have officially solved one of the biggest driving problems of industrial robots, because everybody claims to have an intuitive interface, most of which consist of a single button. It's like, oh yeah, that's not intuitive. Anyway. And when it comes to the metrics themselves, there's many different ways of measuring, quote unquote, the same thing. In some cases, you've got multiple terms for an identical kind of aspect. Or you may have a single term that consists of multiple things, like learnability. Depending on who you're talking to, if you're talking to an educator, if you're talking to a computer scientist who's doing AI and machine learning, if you're talking about people who do interface design and human-focused design of systems, learnability means different things and is measured in different ways. Many of these metrics may be incompatible, and many of the measurements that you take are not going to be transferable, which is always an issue, because now you're doing all this measurement, you're doing all this research, you're putting it out there, and nobody can use it. On the flip side, we often see problems within the published work where metrics are often going to be cherry-picked in order to highlight the benefits or the capabilities of these new systems that are coming out. It's not to say that cherry picking measurements is bad, but it doesn't really give you a good sense as to how your system compares with other systems that are similar, or even maybe even previous iterations of the exact same system. And many times you don't want to necessarily report on the failures or limitations of your systems, because obviously that means that there's something wrong with your research and that you're never going to graduate. Nobody wants that. But it is going to be something that's going to be necessary if you want to solve the problems and move forward. And many cases, what you're actually looking at is a larger community who keep running into the same problems over and over again, banging their heads on the walls, not realizing that other people have also had the same issues. And this is one of the reasons why we as a community, again, need to be very, not necessarily tight-knit, but we need to be open with one another. And this is one of the things that workshops like this actually are wonderful for, because it helps us kind of, I don't want to say just complain, but it allows us to share common experiences of failure. The cult of the new is also a big problem that we run into, where everything has to be constantly improving, constantly new, shiny, new this, new that. And nobody ever bothers to go back and look at the older systems again, see if they're actually still applicable, or if there's anything that can be learned from these older technologies that maybe has been lost somewhere along the line. And as a result of this, we get this kind of publisher perish kind of mindset, especially in conferences and journals, where we often just kind of find ourselves kind of sandboxing ourselves into little nooks and crannies and say, this is my little domain within the bigger kingdom. And as a result, nobody's really looking at necessarily the exact same thing as everybody else, because it's like, well, that's Frank's domain, that's Bob's domain. I don't want to encroach on that, especially if Frank and Bob happen to also be at your institution. So these are problems. So kind of go at a little bit higher level here. It's like the pie in the sky kind of look. Why do we care? Ultimately, what we want to do is bridge this gap between pure theory and pure application. We often see that the ways of measuring the performance of robotic systems or even technology in general are going to be different for the research community as they are for the market community. It's not to say that the market community doesn't care about the research community or that the research community doesn't necessarily care about the market community. It's just that it's not something that is broadly acceptable or in many cases also broadly encouraged. And so this is one of the things that NIST is really good at, where we just kind of sit in between academia and industry and say, hey, I've got this guy that you should meet over here because he's looking at a problem that just might meet your challenges. And the problem that we've run into, especially with regards to kind of getting stuff out of the research realm and into actual application, is that especially within the caregiver robotics, there's really not much of an outside force pushing that technology transfer. So in many cases, you may see some technologies such as flight simulators, in some cases even autonomous driving or autonomous navigation, being pushed from the research realm into actual application by means of like military contracts or military funding. Same thing with mechanisms by which you can actually assess the maturity of these technologies. So here in the United States, we have technology readiness levels that are applied to the various technologies within, say, warfighting and space exploration. We don't really have that in other domains. The closest we can get is kind of like manufacturing readiness levels, but it's not necessarily looking at the technology, it's just looking how easy it is to actually produce something in the tens of thousands, which is useful, but not very helpful in terms of the research itself. There are, of course, a number of challenges that we're going to face in order to kind of get to this point where that bridging between research and the market is a little bit smoother. We have to convince the community as a whole to actually move forward, consisting with reference to these metrics. We also have to recognize that there is a broad diversity of application domains and robot designs, that many of the metrics that are coming out right now and being published on may not necessarily be as applicable as we would really like. And as a result, when you look at the larger HRI community, caregiving robotics is pretty small. Many researchers are interested in things like therapy for speech or social interactions. Some cases, they're looking at it from an industrial safety perspective or even education. And the metrics that you use on those may have analogs in caregiving. And similarly, caregiving HRI may have analogs in other domains. But you have to keep in mind that this is one community in a much larger world community. Similarly, we have issues with replicability and reproducibility in HRI. Again, because of those squishy humans getting in the way, it's really difficult to actually reproduce certain studies. And one of the things that we at NIST are very interested in is the use of digital twin, and another way of saying simulations, in order to capture and model the uncertainty of working with people and actually producing quality data sets that can be broadly applied. Similarly, once you kind of get out of that initial like new and shiny phase of the research, you need to actually start working on the verification and validation of not only your metrics and your systems, but also the way in which you actually do your evaluation. And so having a custom built set of test methods is not necessarily the best way of saying, oh yeah, this is validated because it worked with our system for which these metrics were designed. Similarly, because real people are being interfaced or interacted with by these robots, we have to keep in mind that these interactions and impacts, both physical and metaphorical, have real consequences. In some cases, it could reduce the amount of trust that people may have in the systems. It could lead to injury. And these are always going to be a bit of a challenge that we have to overcome. It's not to say that we should let this keep us frozen where we're at and prevent any future technology developments or evolution, but it's something to be aware of. Another thing to keep in mind is that many robotic startups fail, particularly with the social robotics. This is not to say that all are going to fail. In many cases, they're not going to. The more successful ones are going to get absorbed, as we've seen with, say, Redwood or similar technologies. There are very few positive examples for which we can actually say, yes, this is actually a good caregiver robot that has entered the marketplace, at least in the United States. Overseas, particularly in the Asian nations, like Korea, for instance, with their aging population, surface and personal care robots are actually taking off. And we see a lot of new data coming out of these kinds of interactions. I hate to say that the elderly population is being used as guinea pigs, but effectively that's what's happening. And similarly, cultural differences may mean that the solutions that we come up with are somewhat regionalized. In the United States South, they may be a little less likely to trust robotics than, say, in major metropolitan areas like New York City or Los Angeles. Similarly, the people, how they respond to robots in the United States is going to be different from how they respond to robots in Australia or China or Japan. And some people are more open to robotics. Some people are a little bit more leery of robotics. So a lot of negative, but there are multiple opportunities that we actually have here. Again, caregiver and service robotic research is a rapidly growing and evolving field, mostly because of the necessary needs that we see worldwide. So we've got a rapidly aging population. We've got declining birth rates globally, which means that there's fewer younger people to help take care of the old aging populations. As a result of the pandemic, we've seen a lot of social isolation and impacts of disease on on society and how people actually can kind of live on their own, if it's even possible. And because we are actually constantly moving around, and with our global economy, it's not common as well, it's not as common as it used to be, where you'd be born into a community, you'd grow up in that community, and you would die within that community. You move around, and that means that your sons and daughters aren't necessarily going to be around when you enter that aged population demographic. And so it means that somebody has to take care of you, and it may not necessarily be in your best interest to be taken care of by a human hand and foot. In some cases, you could actually be independent. And that's actually one of the ultimate goals, one could argue, of caregiver robotics, is that independence. And there is greater acceptance of robotics in general. So in my household, for instance, we have 2 robotic vacuum cleaners. Household chores, everybody's interested in all kinds of automation. So you've got your Siris, you've got your Alexas, you've got your Google Homes. These things are being brought more and more into our households, and we're becoming more and more accepting of them. Similarly, society as a whole is becoming more accepting of robotics, because as a result of numerous global catastrophes, be it disease or tsunamis, earthquakes, you name it, we're seeing that benefit of robotics being applied in especially kind of a reactionary kind of perspective, where you may not necessarily have people who can go in and do the work safely. Industry has been a huge driver of robotic research, and we're seeing that robots in general are entering different industries. So medicine, healthcare, you name it, it's starting to enter. And of course, government is very, very interested in robotics. Hence the reason why I'm here. But it's not just NIST who's interested in this. You've got the military side, you have commerce, you have State Department, you have everybody, travel, you name it. Everybody is becoming more and more interested in robotics and automation. So that kind of then leads us into standards. And pay no attention to this particular slide. This is here mostly just to scare you and intimidate you about what the standards landscape looks like for industrial robots. And this does not take into account the medical robots, the service robots, you name it. This is just so many different factors that can be standardized. And so that's one of the good things, and also one of the bad things about standards is that there's just so darn many of them. And choosing which ones to actually follow or to improve can be a bit of a challenge. So for those of you who have not had the displeasure of working with standards, let me just give you a very, very quick overview of what they're like. Standards provide specifications. So mechanisms by which you can compare different like products, quantities, technologies, you name it. They're there to provide some level of security, either like cybersecurity or buyer security, consumer security, that kind of thing. Safety, huge factor. This is actually one of the biggest driving factors within industrial robotics in general. Consistency in assessment. So ASTM is developing a huge suite of different standards that's all looking at test methods and metrics for evaluating robotic technologies. Similarly, that allows you then to be able to look at compatibility between systems, similar to like 802.11 series of standards and industry requirements. And similarly, providing a mechanism by which you can assess who's going to be liable. So if your little robot dog, which you've put into your grandfather's house, accidentally kills your grandfather, who's going to be responsible for that? Is it going to be you for putting it there? Is it going to be your grandfather for not paying attention? Is it going to be the dog? It's a robot. I don't know if it can be held accountable. Or is it going to be the manufacturer of that dog? Another thing to keep in mind is that standards are voluntary, except when they're not. There's only two mechanisms by which a standard will not be voluntary. One is that if it is adopted by a regulatory board or body, similar to OSHA, or somebody who is looking at electrical safety, saying you have to have this mark in order for it to be sold in our markets. The other is whenever it's part of a legal contract. So now you're legally bound to follow that particular standard. Now, the question is, are standards the way to go? Probably not. At this point in time, standards may actually be more limiting than enabling. And we really need to see more consistency in the field. And I hate to say this, probably broader applicability and more robots actually in the field before standards may actually be beneficial. Otherwise, what you end up facing is the potential to stunt technology development and growth. So what can we ultimately take away from this? We need consistent metrics for consistent measurements for prototyping systems, benchmarking, proving functionality, blah, blah, blah. But this is not going to happen overnight because we're actually looking at developing and building a community, actually reaching out across the way and kind of finding people who have similar problems as to ours and trying to find common solutions, uniting the clans, as it were. Similarly, verification and validation has to happen. So not only do your systems have to be verified and validated, but your test methods and your metrics have to be validated. And while the community within the research body is working on this, industry is going to keep plowing ahead. So the Amazons and the Googles are going to be putting out their own technologies into the households, regardless of what the community says is actually probably for the best. And so regardless of what the research body says, there's going to be that potential that, especially with newer startups that are going to be developing over the next couple of years, there may be an amount of catch up saying once you actually have all of these robots in-house and taking care of or looking after your loved ones, now you need to start applying the research that was done independently in the universities and in the research consortia. And this kind of goes back to the earlier comment about need more robots in industry first or out there in the field first. And that may actually be a good way of doing this in order to get some of that data that you can use in your test methods and metrics is to watch Google kill more people. Take their medicine and eat it, because that's what robots eat. And then being able to actually take that information, learn from it, digest it, and hopefully get in front of people losing faith in robotics again, and then actually making forward progress as we move along. And just want to make sure I'm not horribly running late. So that's what I had to say. I could actually go on for multiple hours on any of these topics, and I have actually gone over these multiple hours in the past. If you have any questions, feel free to reach out to me. At this point in time, email is probably the best way of getting in touch with me, just because I'm hardly allowed in my office ever, because I'd much rather be in my lab anyway. So thank you all so very much for your attention, and I look forward to any of your questions.
Thank you, Jeremy, for this very thought-provoking talk. Are there any questions from the audience?
I can start off with one. Jeremy.
Yeah. Go for it.
So kind of at the end, you were talking about, from your perspective, right now is not the time for standards in a lot of robotics, in a lot of robotics contexts. When do you think is the right time for standards, if at all, to come into focus?
A very good question. Usually we at NIST try to meter the standards development according to the actual industry drive. So if there's not necessarily a market for certain things, we don't say, let's try to get ahead of that and try to create a market, because that always means that you may be a little bit preemptive and putting out requirements or test methods that may not necessarily be representative of the technologies that are going to be going out. And so this is somewhat related to where is this current state of the art in terms of caregiver robotics, or even in many cases, the underlying learning mechanisms that go into the caregiver robotics. Is that technology reaching a state of maturity that it's actually going to be breaking out pretty soon into the market and being consumed at a fairly reasonable rate?
Awesome. Any other questions? Let me ask something, Jeremy. That's actually a follow-up to Zachary's question.
Sure.
So, given that I know that there is an ongoing effort on creating a study group on deciding on basically coming up with metrics for HRI in general, not just caregiving robots, but HRI in general. Probably you think that for HRI at least, the effort, this is probably the right time to start thinking about these metrics or standardizations. So then my question is, do you think there are any common intersections between HRI in general and caregiving robots that we can reuse some of these metrics developed for HRI for in this application of caregiving, or does caregiving robot application impose some specific constraints that we cannot generalize those metrics?
I think that there are many metrics that are generalizable to the whole of the HRI field of research that are highly applicable in caregiver HRI. So let me go back to this one right here, for instance. Safety is a huge thing. One of the issues that has come up within this study group through IEEE for HRI metrics and standards has been the concept of the human subject study. And in many cases, people are recreating studies without actually knowing it, but again, calling things differently, or maybe looking at it from a slightly different perspective, or misappropriating or misapplying statistics because you've got the whole lies, damned lies, and statistics. So it's very easy to abuse statistics. And it's also very easy to misunderstand statistics. And so if you actually apply it consistently and do so in a way that the community agrees is going to be beneficial, then this is something that you can actually leverage for standardization, especially if you've got new researchers just entering the field who maybe have never done a human subject study, and maybe who wants to have some mechanism by which they can actually learn or at least base their studies off of. A standard in that regard would actually be highly beneficial.
Awesome. Thanks, Jeremy. Are there any other questions? If not, then I would like to thank Jeremy, our speaker, again with a round of applause. And over to you, Zachary, to introduce our next speaker and our final speaker for the day.
Absolutely. I always have to spend so much time finding Zoom windows once it exits the presentation mode. All right, so this will be our final speaker, presenter, invited speaker for the workshop here for today. So I'm happy to introduce Dr. Michelle Johnson, who's an associate professor of physical medicine and rehabilitation at the University of Pennsylvania, where she directs the rehabilitation robotics lab. She received her PhD from Stanford University in mechanical engineering, and today her research is primarily in the area of robot-mediated rehabilitation, and her lab uses robotics, rehabilitation, and neuroscience techniques to translate research into development of assistive and therapeutic rehabilitation robots. So with that, Michelle, I'm happy to hand it over to you.
We can see your slides, but not hear you.
Do you need to see me or?
Oh, no, I mean, that's up to you. Of course, we'd love to see you.
I know, it's like,
it's great to see you. Yeah.
Right. Hey, guys, last but not least, hopefully. So thank you guys for having me. I'm going to probably give a little bit different perspective, but I think the things that I'll talk about echo some of the things that I've heard, which has been really great and exciting in this workshop. Looks like I'm not advancing. Oh, so just to give some context, I'm going to talk about essentially the experience between therapists and patients, and studying that experience within the context of stroke therapy. And for those who may not be familiar with stroke, usually that results from an infarct in the brain. Either it's a hemorrhagic or ischemic. It often results then in hemiparesis or hemiplegia, which then affects both the upper and the lower limb. One of the most popular activities that are done in terms of caring for stroke survivors is task-oriented therapy, where we're using different tasks, self-care skills, ADLs, et cetera, to support the recovery of function, either for mobility or for upper extremity use. Just to note that stroke survivors will not just have physical issues, but they'll also have cognitive and emotional issues as well. So I think in terms of like looking forward in time, and we're not that far from the 2030, we now need to start quoting 2060 data. We have the expectation that there'll be 10.8 million older adults living with disability due to stroke. So when we think about that, our goal is to maximize their independence and get them going again. And so there are a variety of typical stroke rehab strategies. Like I said, I'm going to focus mainly on the task-specific ones, but there are lots of players involved: occupational therapists, physical therapists. In the occupational therapy world, we're working with real activities, trying to move joints, do sensory facilitation. And one of the challenges is this typically takes 60 to 90 minutes daily if we're in the inpatient setting, or if we're in the outpatient setting, we're talking about 3 times a week, 45 to 60 minutes for 6 or more weeks. And oftentimes it's done in segments. You might do like 10 sessions or 12 sessions, and then there's a break, and then additional sessions. Now, in the United States, we're fortunate to have a little bit more therapists per population, 3.62, but we know that in many, many countries, and even in ours, there is a growing shortage of people who are able to take care of this growing population of stroke. So everyone's been talking about this gap in care. And essentially, we're all on this talk because we believe that technology can clearly bridge this gap in care. And the 2 types of technologies that we've been focusing on is the idea for therapy robots. And when I talk about therapy robots, I'm very specific in thinking about robots that their goal is to automate and deliver either autonomously or semi-autonomously some aspect of the therapy that either is a physical therapy domain, an occupational therapy domain, a speech therapy domain, et cetera. And that one key aspect of these robots are in terms of assessment of the level of disability and some type of remediation of impairment through a variety of activities. For most common, it's repetitive movements, intense passive, assistive, active force impact training, etc. And then another piece is their effectiveness is governed by their actual ability to reduce the impairment that we see. And many of the robots that we're talking about in terms of the cost factor, we'll see mainly in clinics and in the supervised settings. And then when we talk about assistive robots or humanoid type systems, those are the ones that we're talking about in terms of how are they operating within this settings. And then when we say socially assistive robots are those that have both an assistive robot paradigm as well as a therapeutic robot paradigm. When my lab has been really trying to go back to basics in terms of thinking about and observing human-human and therapist-patient interactions to try to inform maybe what we've already been doing in this space and maybe going forward in the future. So clearly, we've been looking at, how are people moving? And that, of course, leads us to then being able to capture kinematics, how the forces of the interaction, and leads us to trying to then model haptic interaction. And then I think the part that we don't do well, and we've talked a little bit about this in this talk with a variety of different presentations, is the behavior and trying to understand the intent and the role of the behavior in driving the action of the robot. And I think I want to kind of focus on this aspect as well in this particular talk. And the study that we did, it was a very small pilot study, but it was in huge collaboration with our clinical therapy partners. And we were looking at intent, and we defined that as understanding cues, verbal activity, and the behaviors that therapists were, and the roles that they were involved in. How we did it was we actually started with a series of videos that are often actually used to train occupational therapists. And we were talking a little bit about where do we get data from. There are lots of videos out there that are actually used to train clinicians, and these are one set of them. And they specifically focus on the upper extremity in this particular case. And so what we tried to do was we looked at the videos, and we actually looked in concert. So one aspect is, why didn't we use ML? We wanted actually, first of all, in this particular case, partner with the OT, and we wanted to grade, and from their perspective, what are we looking at when we watch these videos? What are they doing as they interact and support the stroke survivor in these videos. This is another example of the video here. I'm not sure if it's playing. Oops. This one did not put, hold on a second. Some reason the video is not playing. Anyway, in this video was an example of a sweeping activity that the patient was doing. And this is a higher level functioning patient, which had a little bit more ability to do this action. And so the therapist's relationship to the patient will change as a result of the level of function. Oh, so maybe it was a little bit later. So you can see that this patient can be left on his own at points in time to do the sweeping activity by himself. So one of the things in collaboration with our occupational therapists is that when we're thinking about humanoid robots and social assistive robots, we're often layering on a behavior-based paradigm. So I wanted to think about that paradigm in terms of what a stimulus and response, and in thinking about the behavior that the therapist was doing or the behavior that the patient was doing, and how did what type of inputs triggered physically and verbally triggered the change to the behavior, what was the therapist doing inside this behavior, and then what might have been the actions that resulted. So we developed a set of cues, and this was primarily developed by our occupational therapist partners. So what types of specific things do you think the therapists normally do? This is just a subset: reaching, gripping, moving, lifting, helping transport, helping to stabilize the patient, helping to guide the patient, helping to direct them to particular activities through touch and manipulation. And then in terms of verbally, what types of things are they normally doing? They're trying to express from the therapist standpoint, usually providing support, motivation, asking the patient to do a particular thing, often maybe even commanding, do this, do that, stating, here's the description, here's the parameters of what I want you to do. Oftentimes verbally, they're correcting, they're maybe also stopping and preventing a particular action. But these cues are often from the patient perspective, what might be triggering is the patient is not reaching, it's not gripping, they're not coordinating, they're not moving, they're not doing something that the therapist, would like them to do. They're not able to stabilize the cup, they're not able to stabilize their hands. And then from a verbal point of view, the patient might be asking for support, might be complaining, might be disagreeing, might be expressing pain, those types of things. What are they doing that might be triggering also changes in behavior, as well as a change in activity? What the three types of roles and behaviors that we wanted to focus on, and we realized that we thought about this as a dyad. So when the therapist is in a demonstration mode, the patient is often observing, and this is a classic case, a case that we typically see. So we think about this as a dyad because they're co-acting together. When something triggers the therapist out of that mode into an observer mode, now the therapist is observing the patient who's performing, and again they're co-acting together, and then something may trigger the group out of this particular mode, and now the therapist becomes the helper and the patient the performer with help, with assistance. And what we intuit was that these things could be triggered back and forth. So you could trigger from the helper to observer to demonstrator, or from demonstrator to helper, etc. So in trying to capture, looking at those videos that we used as a pilot group, we used NVTA, and we actually got the clinicians to do the coding because in terms of training them with the definition, the classic process that you go through, qualitative coding, which is definitely intense. And this is where, in fact, we just got a small grant to take this to the ML stage and to try to begin to code or recognize some of these roles automatically. But anyway, in this particular offering, our occupational therapist providers, they did all the coding after we trained everyone in what they would be looking for to code. And then this is an example of what they might have been doing when they were looking at the video. For example, recognizing that there are two actors, the therapist and the client, which is the patient. And then recognizing in time what is going on as we see them in time. So they may then say, okay, the video starts out with a demonstration and it occurred for a specific length of time. And then something occurred, an administrative cue, say, for example, the task ended, and then that caused the therapist to move to the role of observer. And at the same time, the client, the patient, is in the observer role while the therapist was demonstrating. And then when they switched, there was a collaborative switch, and the patient went to performing. Then something occurred. What was that cue? They coded that cue that then moved them into the next role and triggering back and forth. So this is kind of an example of what we anticipated the video would look like as we went through the interaction sequence. We then basically pulled all the videos together and looked at then how patients, what were the frequencies of these roles, what occurred, the duration and time of these particular roles, and when did the cues occur? Did they occur? What happened to trigger you from demonstrator to observer? Or while in the demonstrator role, what were the therapists doing? What were the patients doing? So from a quick results standpoint, we saw that all of the six roles were represented. In terms of the dyads, the three dyads were represented. Now, what we saw was the therapist performance dyad with assistance was actually the most frequent one that we observed. Then the observer performer, the therapist being the observer, the patient being the performer, was the second most frequent. And the third was the demonstrator observer. We actually think, and I'm jumping to kind of a little bit of the conclusion here, that the reason why there might have been a little bit less demonstrator observer activity happening is because most of the videos kind of cut to a little bit of demonstrator, and then there was then the beginning of the activity or the therapy session. But we surmise that if you actually collected videos, raw videos, you would have gotten more of the demonstrator observer activity, because oftentimes that is the beginning of the therapy session. We also then coded and captured percent and frequency of the physical and verbal cues. And I'm going to go through these a little bit, just each role, each behavior, so that you kind of get a sense of the big picture. We did this for what are the cues. We saw the biggest cues were does not reach, does not grip, and does not lift. These were often the time where the patient spent the most time and had the higher frequencies. And from the perspective of the therapist, we saw physically a lot of lifting activity, stabilizing activity. And we, of course, everything occurred, but we saw those as the most, took a lot more time in terms of frequency. In terms of verbal cues, a lot of describing, explaining, and stating was what we saw in terms of the patient. And then from the therapist aspect, we saw a lot of supporting activity, encouragement, asking questions, and telling the patient what they needed to be doing. So we also coded about what happened that took a patient from observer to performer, et cetera. And I'm going to just jump in piece by piece to give you a little bit of a good background. And what I hope is that you take away from this a little bit of kind of like an insight into what is happening in these therapy patient environments. So out of the 10 cues that the therapist, we coded for the therapist, we saw the reaching, lifting, and stabilizing cues were the ones that were most frequently used and most frequently caused a role change. We saw reaching, lifting, stabilizing, and these had 36, 24, and 41%. And the cue stabilizing was used when the patients required physical support to perform the task. And so you can imagine patients that are lower functioning would require more physical support. So in fact, maybe the helper role would be more significant if the patients were lower functioning. In terms of verbal cues, we saw really 50 supporting, expressing being the most often used one. And the 78% of the time, the patient was describing, explaining, and stating. The patient's verbal requests or physical inability to perform an action completely correctly or accurately often led the therapist to switch into the helper role. And some of this is intuitive and some of this we kind of know, but I think it was for us very interesting to confirm some of our theories, but also to quantify that as well. So for example, in the demonstrator role, here we see the therapist spent a lot of time providing instructions. They were often in this role seen describing the task to be done. They often provided verbal and physical instructions for how to perform the task. And oftentimes this role was specifically ended when the task was finished, when they finished demonstrating the task. And oftentimes the cues that you saw happening, the role is them reaching out or explaining something. And this is just a video, it's not going again, where you see you see a little bit of transitioning, but demonstrating, then leaving them to perform, and then demonstrating again. So of course, when we think about what's out there, we have been working in this specific space, and others, even from some of the videos that we saw in this workshop, that people have been working in this space of demonstration. And there's a ton of robots that we've developed, humanoid and social assistive robots, that have actually been in this demonstrator role. So clearly this is a role that roboticists and folks have been developing robots that can provide those types of activity as well. What was interesting, and we didn't quite do this, is to go back and look at robots that were predominantly out there that were demonstrated robots, and did they actually kind of embody many of the things that the therapist was doing during that time. So one of the things that we said, well, based on what we observed, maybe these are some guidelines that could be taken home. That in the demonstrator robots, they should be performing the set of tasks and exercises for the patient. And what we also notice is that able to reach in, grip, stabilize, guide, and manipulate whenever is needed, and that clear instructions and directions to the patient was actually critical for this robot to be successful, and being able to communicate in some way to clarify actions, I think was very important. And I think in a couple of the workshop talks, we saw this in action, and learning autonomously tasks. And then I think something that we don't often see in the robots that we develop is them transitioning to the role. And I think I was really excited to see the talk today where this was occurring, that transitioning from the demonstrator to the helper to the observer role. And I actually feel like that's actually a finding that we saw, in that most of our robots were not doing that. The transitions from demonstrator role seem to occur and often happened at the discretion of the therapist. And what we saw was the demonstrator to observer role really was often triggered by the therapist attempting to express and clarify the activity. And then the demonstrator to helper role was often when the therapist observed something that was not happening and they wanted to clarify and directly move the patient into doing the activity. And I think oftentimes this happened when the patient was already low functioning. So there was no opportunity for the patient to totally practice the task by themselves. In terms of the observer role, what we actually also saw was that you often saw the therapist monitoring the activity. They are looking at the user's performance, looking at how they completed the task, and they're often doing it without direct contact. This is where I think it gets complicated because oftentimes the tasks that are being performed are quite complex. And I think it was mentioned in maybe Dr. I think in Brenna's talk about how do you break down these complex tasks? How do you allow the robot to be able to see and understand what is happening? I think many of the talks echoed that. Helps in terms of like what we also saw, and I think this was interesting, was this role often led to a helper role whenever the therapist saw something, and they often moved in and stabilized the patient. And it was hard to code this role because they were observing, and then often with a light touch, a hit on the back or a push on the hand, they moved quickly from observer to helper and then back. And so this was often the physical cues that we saw in this particular role. Clearly in this role, there was a lot of encouragement, a lot of explaining, a lot of state, good job, and those types of things that I think robotics, we often have been doing already. From the patient's perspective, what we saw that the patient often triggered this role. The patient going into performer's role or triggered coming out of this role when they didn't do something, does not lift cues, or needed or asked for more explanation from the therapist. We also, the patient often triggered the therapist to move to the helper mode with, we saw a lot of does not lift, does not coordinate, does not reach. And what we also saw was whenever they were unable to perform the particular action, that's when the therapist moved in, either with a light touch stabilizing to help to manipulate, to transport the arm, etc. This is an old picture that was from Dr. Matarich's lab that I really like, where this is one of the really early activities of using a robot to observe and to telemonitor and to react using sensors to the patient as they complete the task. And this is a classic example of the observer role occurring, not demonstrator, excuse me, but the observer role occurring that robots are able to do. Some of the guidelines that we thought would be worth mentioning is that I think it's important that in this role, the monitoring of the body and the limbs, and this is not an easy task, and I think that was alluded to earlier, because it's like, where do you look and how, especially if you're looking at the upper extremity, being focused in the upper extremity, if you're looking at the lower limbs, being focused at the lower limb, if you're doing bilateral task, it becomes even that much more complicated. And what's fascinating about the therapist and the human, the therapist and the patient, the therapist is taking it all in, and that's really challenging, is they're looking at the human body as a whole and trying to absorb all these pieces at the same time in respect to the tasks. They're also simultaneously assessing the level of performance with respect to some performance criteria that is known a priori. They're also adapting their behavior according to the level of function that the patient has. And they're doing a lot of reaching, gripping, lifting, stabilizing, supporting the movement along with these verbal cues. and along with supporting the learning of these new tasks. So a robot observer needs to be able to do that. And I think what we also found in these human-human interaction, transitions are occurring all the time. And especially observer to helper was a very, very common transition. We saw at transitions from observer to demonstrator, that often happened, I thought, when there was a confusion, when the therapist thought that the patient might have been confused about the task or wanted to demonstrate another way of doing the task and an easier way of doing the task, or to correct the way the person was doing the task. Observer to helper, I saw that more frequently. I think this happened the most often. And ironically, I think this is the one that doesn't happen as much, and many times the observer to helper was involved a touch, involved a stabilizing, involved some type of physical activity, and it could often involve non-physical contact, but I saw a lot of also very physical contacts occurring as well. Lots of reaching, lots of lifting, lots of kind of getting in there and cueing as well. So in the helper role, we observed oftentimes it occurred when the patient was having a particular difficulty. We often saw that the therapist was using the observing role to collect the information about the level of function, their motor and cognitive impairment of the patient. And then they often were guided by a priori knowledge of who this patient was and what they were doing. They often reached in to directly touch the patient's limb, lift their arm, stabilize their limb. And I would say most of the forces that we observed in these particular 8 tasks were light touch or very guiding forces. And that echoes something that Dr. Lee had mentioned about the role of light touch in stabilizing movement. And I think we saw that here. Physical cues, we saw a lot of physical cues occurring in helper role. I would say that for this population and for the group that we looked at, the helper role, like we said, was the largest, was the most frequently used role. And while that was occurring, lots of supporting, stating, commanding, requesting, asking occurring there. From the patient perspective, the things that we saw that triggered the patient was not lifting, not gripping, and explaining and desiring more information. So, of course, we've been doing, at least my team have been kind of focused primarily on building robots that are in this helper role for stroke survivors. But one of the things with these robots is that they're often permanently connected to the patient, and they're not kind of providing, say, like being able to move away from the patient if necessary. But I think one of the things that I think is the parallel of what this helper role is that we've been using our control laws to assist as needed, so that even though the robot might be physically connected to the patient, there are times when the robot is acting as a passive actor or acting as an active agent in supporting and assisting or resisting the patient. So I think in this case, we see evidence of this in what we've already been doing as well. It's I think the part that I notice is in more of these complex activity, our robots are not able to do the most complex activity. And in terms of the things that we observed, the type of helping behaviors that we observed, the reaching, the gripping, the lifting, the stabilizing, we've built robots that do aspects of these, and in many of these complex ADL tasks, we're not able to kind of put it all together. I would say these were some of the other things that we noted: assessing the user performance, providing the physical and verbal feedback, and again, being able to transition from observer to demonstrator. The transitions we saw to helper, oftentimes from helper to demonstrator, we saw reaching, moving, stabilizing, and manipulating were often the reasons why therapists would switch. Correspondingly, we saw does not grip and does not lift as the reasons why the patient triggered the switch. Helper to observer, often when the patient kind of helped and then wanted to see if the person got it. And so they would demonstrate and then step back and observe, and then, you know, maybe reach in, stabilize again, and then help observe. And then we also saw, in terms from the patient's perspective, we didn't see any physical cues that would that caused the helper to observer activity, but we saw a lot more verbal cues here. So from a summary, I would say if we're ideally trying to create a robot therapy assistant or a robot therapist, that we've been actually attempting and successfully attempting some of the things that we observed during this particular pilot study. We have helper robots, we have demonstrator and observer robots. What I think we don't have as much of is the robots that are fluidly transitioning from contact to non-contact with patients, from moving through all the three patient coacting dyads that we observed. My team started to kind of think about a little bit about that with the Baxter robot, and kind of from observer to helper with a light touch and contact, and kind of what would that look like. And I think, again, what we observe is we often think that a lot of forces might be needed to be able to do that, but sometimes the force might be just a light touch, or might be a guiding touch that we need to do in order to kind of get our robots doing more of this transitioning activity. Of course, the limitations in every study, we didn't have as many videos as we want, which is why we're kind of trying to do this. Our next phase is to collect a lot of videos from our colleagues and do this with trying to see if ML activities can do this. We saw that task complexity and patient motor function, I would say it would definitely change the percentage of role we observed and time spent in each role. I suppose that if we have a group of very high functioning patients, we're going to see more time in the observer role and in the demonstrator role, and less in the helper role, versus patients that are more severely impaired, you're going to spend more time in the helper role. And so I think this might be something that the robot needs to kind of understand in order to appropriately provide assistance. I definitely think ethics and real-time implementation is something that probably needs to be thought about, and we thought about it in this way. It's like, what's the scenario when we think about robots and therapists and robots assisting therapists? The scenario that most therapists fear is a totally everyone just thinking this is the best strategy, where the robot fully replaces the therapist. And it's, for me, this is the strategy that I think does work sometimes. However, it needs to be still done where the therapist is in charge of programming or helping or demonstrating or teaching the robot. Ethically, a lot of therapists will often tell me, well, here's my fears. And I think there are lots of people doing research on the ethics of having fully autonomous systems versus shared autonomy, et cetera. But the idea of being impersonal, or not being very safe, not being as good as the therapist, not being versatile enough, expensive, things like that, I think are oftentimes the barriers to possible acceptance of scenario one. But I feel like there is an opportunity here for implementing a scenario one when we work through some of these issues with the therapist. clearly the robot sharing the space and with the therapist is, I think, what many of us talk about as possibly the ideal, where some activities are offloaded onto the robot and others are offloaded, are retained by the therapist. And ideally, I think when we talk about this, and when I talk about with my clinical partners, this type of scenario is what they prefer. However, they do not mind having some scenario one activity occurring for select tasks. One of the things that we've been working on, and one of my students have been looking at, is how do we perform affordably social assistive robots, both when the robot is co-located and then when the robot is remote. And thinking of these perspectives that we've been just discussing, how do you do that when the clinician and the patients are in the same room together? That's one thing. And then how do you do it when now the robot is actually not the clinician is not located in the same space? So actually my student has been looking at this particular activity, and he's going to be presenting a little bit of the work that he's doing. I believe that's Wednesday, in terms of the design of a system that will be more on the demonstrator observer role, but kind of like also thinking about these roles in terms of remote, a remote delivery of them. I'm going to stop and say thanks to the people, of course, who support and make this work possible, and to the funders, and I'll stop there. Hopefully I didn't go too far.
Wonderful. Thank you, Michelle. Thank you for sharing. So we have just enough time for one question or so. If anyone has a question from the audience.
So yeah, maybe I'll ask a question, Michelle. So thanks again for the great talk. It's very educational. Michelle, I was wondering if you had seen any temporal effects in terms of, like, when switching between diets. Like, for example, over long term, did you see that the helper role went down or something like that? Like, were there any temporal effects that you saw in switching between these different transitions between these different diets?
So I think because these were one session videos, I think temporal effects would not come into play as much, but I would expect that if you had a series of videos where you were watching what was happening at the beginning to what happens towards the end, say of a 12-session series where someone was improving, that we should see temporal effects and we should see changes. And you could argue that you could use these roles and their frequencies as a marker for effectiveness of what the therapist is doing, and maybe even a marker for gaining independence if you're moving from having primarily been more in the helper role, and then later you're moving more in where the therapist is spending more time demonstrating, observing. You want that to occur. And the temporal effects will mainly happen, I think, when this is looked at over time. You may not see this temporal effect in one session, because it takes more than one session often for people to gain competency and improve therapeutically.
Thank you.
Good question.
Go for it, Charlie.
Yeah, so very cool work. Thank you. Thank you very much. One thing I was wondering about was, now that you sort of have this gold standard coders with clinicians, is it possible for naive coders to do a comparable job? Do you think that's a possibility? And how much inter-coder agreement was there, with the gold standard clinicians? Because it would be cool if you could scale it up, but
So we actually, it's funny, my OT colleague trained her students, and we trained 2 students separately. And then we looked at ICC to look at their, once they got trained, they did it separately, and then came back with agreement
talked a little bit about the definition and went separate and then coded again. And we had over 95% agreement. And I think it's possible to, it's just a little bit labor intensive. I to do the video coding was a bear. And in fact, that's one reason why our next step is, can this be done using machine learning, using some type of leveraging of ML to recognize these roles and these cues. And actually, that's what we're actually tackling right now, because if it can be done, that would increase the the utility of this to kind of analyze more complex scenes between therapists and patients.
Thank you.
Thank you, Michelle. So at this point, I think we'll do a quick wrap up here and move into the final topic for today, which will be our panel discussion on the grand challenges. Again, for everyone who's here, thanks for sticking around with us. I know it's definitely getting a little bit late now at this point, so thank you for sticking with us. I know we've been getting several messages from our colleagues, both in Europe and in Asia, where it's getting very late for them, but they've been asking if recordings will be live so that they can watch them afterwards. So we're recording this, we'll post it online, so all of them will be able to watch these last few talks. And so with that, I'll leave it to Tapo to get us started in the last panel discussion.
Thank you, Zachary. And again, I echo the same message. Thanks for staying so late with us. But yeah, I hope this to be a very exciting session, as was before. So this panel, this panel is basically themed towards grand challenges in robotic caregiving, right? And thank you so much to our panelists, Karen, Jeremy, Michelle, and Aaron. But also for the audience, feel free to jump in anytime if you have any comments or to the questions and everything. So I guess I'll start with, given the theme of the panel, I guess I'll start with the most obvious question, right? That I've been thinking about all the time is, what do you see as the core challenges of facing caregiving, robotic caregiving in general, and also especially learning for caregiving robots? Feel free to jump in, any of you, like at any time. Yeah.
I think there's still so many. One perspective is terms of dealing well with decreasing and changing the impairment, the persons who, so let's back up. There are lots of different types of elders, and there's the able-bodied, the frail elder, and then the increasingly disabled elder. And I think oftentimes we target one level. And but if we're going to be realistic, there often, I think the challenge is is the increased versatility. Even in my talk, is just to see the versatility in that interaction between the therapist and the patient. And I think the versatility is what we don't do well. The flexibility is what we don't do sufficiently well. And I think that's the grand challenge, is how do we get robots transitioning easily and dealing with the complexity that's really and truly what's going on in the caregiving world.
Well, I can comment. I have more of a I guess applied perspective, in that we're trying to get robots out of the lab and into homes. For me, it's really about, how do you make the technology not frustrating, to make it a delight to work with. If we're ever going to really have the impact that we all hope for, people have to accept the technology and want it in their lives. And even for relatively simple devices, very large companies don't always succeed, right? And we have very complex technology. We have a wide diverse range of people with different needs and in terms of the interfaces that they would require, the types of assistance they need. And then you also have to deal with safety in a way that you wouldn't have to ever do with an Alexa, for example. And so, you know, for me, it's how do we lower that frustration, right? And in there's a lot of hard technical problems about learning, understanding intent. There's design problems around intuition. I think Jeremy had mentioned, you know, just making it a single button doesn't make it intuitive, right? And so there's hard design problems. And then there's just the human factors and how do you encourage someone who may not work with technology, may not want it in their life, to use these devices and accept them. And I think, you know, to me, it's just how do you make a great product out of all of this great work that's been going on.
And I think from my perspective, I'm going to kind of echo both of them and also kind of put on my NIST hat here, is that high quality, diverse data for training, something that is not necessarily going to introduce any unintentional bias against one group or another, but also being able to be broadly representative of large swaths of the population, because many cases you're looking at gathering data that's very regional. And if you're lucky, you can actually coordinate and collaborate with others in either other parts of the country or even other countries. And I think getting that corpus of knowledge is going to be required in order to kind of bridge some of the, like, it'd be nice if we could, to here's how we do it kind of technology shifts.
Yeah. And just to kind of follow up on that, so even if we're able to collect lots of data from lots of different kind of contexts related to caregiving, how should we evaluate progress in the field, right? What metrics are important for us to be looking at in terms of evaluating progress?
Acceptance is a good metric. When you actually have more interest, especially in, say, caregiver organizations or hospitals looking to start acquiring and actively deploying these kinds of technologies, I'd say that's a very good indicator that your technology is maturing to a state of acceptance. Beyond that, it largely comes down to, can you actually convince the general populace that you are making good progress? And some of that will be actually providing useful, not necessarily data, but proof that things are working. And this goes beyond just the flashy demo. I like flashy demos as much as the next person. But whenever I see a flashy demo, I say, okay, can I see a data sheet where you've done this particular experiment 500 times, and that you get similar responses with different people, and that you actually have a good performance rate that actually meets the needs. And it could be a matter of, well, what is the applied force as you're helping the person lift that glass? Is this something that could result in a hematoma for people who have blood conditions? Is it something that maybe is appropriate for certain healthy or semi-healthy populations, as opposed to the more frail and possibly needing?
Yeah, I also think another grand challenge, and I think the Hello robot is one of the examples of a robot trying to address that, is just affordability. You know, that's one of the things that I've been really thinking about, is thinking through carrying robots that are not just limited to high income settings. And, you know, thinking about stroke, and that majority of it is occurring in developing spaces and outside of high income settings, but they're not there because they're too expensive. So I think carrying, you know, there's a lot of issues, of course, both even urban to rural and things like that. But I think that's a big challenge too, is how do you, like Aaron said, move it not out of the lab, move the robot out the lab, into the community, but even into the like the poorer communities. And I think that's another grand challenge is how do we realistically do that? Because you know, our systems are not really serving the majority of people who need them.
You know, I can add just with respect to affordability, it was definitely an imperative for us at the start. And, you know, in practice, we're selling it for actually more than we had hoped. You know, we had a much more aggressive target, but this is sort of the way the game goes, especially when you're trying to grow a company and be low volume at the same time. But we do, even where we're at, we see that as a big enabler, just in the range of even researchers that have access to the technology now. And, you know, I'd mentioned portability before. Just the fact that it's easy to transport, put into a home makes a big difference, where you can put it into rural communities and do experiments there now. It's much more feasible. And we do think actually sort of remote caregiving through a device like this has a lot of potential in places that are underserved by sort of staff to nursing, stuff like that. So.
I do want to point out like something that I feel like I think this affordability is a very crucial point, but I feel like to actually, I see a lot of hope. Like when I started my PhD, I was working with robots that were like, you know, PR2 or mecha robots, like they were like $400,000, $200,000. And now we have like, for example, stretch robot, which is like, you know, $17,000, $18,000. So I do see advancements in sensors, actuators, robots in general, where things are becoming cheaper. Yes, it's still probably not affordable by one person, maybe shared in an assisted living facility or something. But I do want to point out that, you know, I feel like this is where I think we need to go beyond our circle and bring in policymakers and everybody into the thing, into the entire circle to be able to make this happen. Like, for example, when I was talking with Kinova, I don't know if John is here or not. Kinova had mentioned to me that they're one of their biggest customer base is in Netherlands, and one of the reasons was that this wheelchair-mounted robots was like fully it was fully covered by insurance there, and so it became, you know, affordable. So, and that's where I feel like we need to have mechanisms in place where we need to bring in other people outside the industry, even the policymakers, together to actually drive this towards in real homes. Anyway, continuing this thread about, you know, translating technologies from labs to real homes. I would love to know a little bit more about, you know, what do you think are the key gaps between academic research in these assistive robotics, like whether it's social assistive robotics or physically assistive robotics, and the real world scenarios? Like what are the key gaps that you see, and how can we overcome them?
You want me to pull up that slide again? So in many cases, pure theoretical research is looking at different problems than what industry is looking at. So you mentioned the affordability. That's a huge problem. And there's many instances where we see the commoditization of technology driving down costs, like in the case of, say, 3D printers, or even the democratization of technology, as we saw with the Microsoft Kinect about 10 years ago, where $3,000 was your entry level point for 3D sensing, and all of a sudden you've got it down to 150, just one fell swoop. And being able to recognize what is actually important to industry and the users is ultimately what's going to be necessary for getting the stuff out of the research lab into the household or into the hospital laboratory. In other cases, you may actually be looking at an instance where you've got a great technology that is ready to go. It's just missing that killer app. Good example of this, augmented reality and virtual reality. It's just waiting for that one thing that people can't live without to actually be able to drive it into the consumer market, because the price is right, the technology is right, everybody is ready to go. It's just, there's really no reason to go out and buy it.
I was going to add, you know, we've taken a path which hasn't been looking at sort of policy and insurance and sort of systemic things that would have to be dealt with in the US to do something that might be done in the EU, which would be fantastic if our government would do that, but we're not holding our breath either. So, you know, one path that, you know, the way we think about things is also coming at this through the consumer route, where if you make a technology that's broadly accepted, it can then be adopted and co-opted into assistive applications. And in doing that, you get the sort of maturity of technology and the sort of that level of execution that's required for someone to accept it into their life. And it's sort of a balancing act. You know, we're thinking more about a multi-purpose robot that you could imagine having a broader consumer appeal, but there's also very specialized devices that it'd be much harder to go that route on. But, you know, I like the example of the Apple Watch as a fall detection device, because I bought that for my mother, but not the contraption I could have gotten at Best Buy that was a dedicated device for that. So I think, you know, there is a balancing act between depending too much on policy and insurance and all that to do the right thing, and finding strategies to get products in the market that just find through their own natural organic growth.
And I also think I agree with that. And I don't know, I'm on a Fulbright right now. And one of the Fulbright goal was I'm working in Botswana. And the idea was to kind of really think through the global health and the affordable robot issue, rehab robotic issue by being on the ground in a place that, you know, these issues are even starkly, you know, in your face. And something that I've discovered there that I think was quite informative was the idea that somehow we have to figure out how to leverage the local talent and materials, et cetera. So for example, we have our TheraDrive haptic robot that we brought over. So we brought over 2 robots and the platform, et cetera. And then the local engineering school were like, can you build this version of it there? And what was interesting was the labor cost was just amazingly different. Like, okay, so $1 US was equal to 10 pula. And so equipment, like things that, you know, people's labor was a lot cheaper. And so all of a sudden, something that was costing us what, 5,000 in material and, you know, and maybe a little bit more in labor was now hitting the threshold where it could be done for half that price, and labor was really like cheap, dirt cheap. So, but the skill was there. Lots of cool engineers, lots of really smart folks that know what they're doing. And what I also think was really, they're used to engineering, you know, creatively with affordable issues in mind. So, I don't know. My point is that maybe in terms of fostering more collaborative activities with people within these spaces who are counterparts, who are able to help us think through how to be innovative within the constraint of resources. Just a thought, but at least I've been discovering that with being in Botswana and hearing, and I'm like, oh wow, I didn't even realize you could do. Oh okay. So that's been very I think a part of our grand challenge is, if we want to do more and reach out more, just like we need to collaborate with the clinicians, the people in the community, the people who were actually trying to put the robots in their hands. I think we also need to collaborate with globally as well in order to make this work beyond the high income countries.
That is a very, very good point. How do you envision setting up these kind of collaborations globally? I think that's one of the big questions I've been thinking about.
So I've been actually, so it's a great question, Zachary, because I've been, I don't know if I've been single-handedly doing it, but not really. I won't give myself that much credit, but I have been who are interested. In fact, one plug for IEEE ROS is that they're trying to, there's a call out for mentors who are interested in mentoring our counterparts in developing countries and who are interested in robotics. And so they want people who are interested in becoming a member to form these collaborations with colleagues in these countries so that we can begin to work together. And I've formed many of those collaborations in Nigeria, in Ghana, in Mexico, in Costa Rica, in Jamaica. And it starts really with identifying, one, a local engineer, and two, their clinical partner. And then I've been able to then begin to understand the needs of the ground. So basically you form your counterpart there, and there, I can talk more offline, Zachary, if you're interested in knowing that. And I've also actually started this webinar that is focused on bringing people from developing and, engineers and clinicians together and to talk about these issues. And then that also tries to get people interested in collaborating together. But Ross is trying to also do that by asking for this mentor initiative. But I think that's something that I found. The engineers are there. We just need to make the connection, and then they're willing to collaborate and work with us. But I can connect you to people who are definitely willing to work on these particular topics.
That is great. We will be in touch.
Okay.
So I guess another thing that came up almost in everybody, all of your comments, like Jeremy, Aaron, yourself, Michelle, and other talks as well, is one of the gaps is because is due to the lack of stakeholder inclusion. And while we all individually researchers, we are really, there is more and more I would say awareness about this. And people are trying to do this, but I was wondering, are there any mechanisms that you know of, or are there any ideas that you have that we can set up a mechanism in which people from these different research labs across different universities have a way to have access to these stakeholders? And when I say stakeholders, it's not just the care recipients, the end users themselves, but also caregivers and experts like occupational therapists and everything, so that they are we get their information, their feedback throughout the design process of our technology.
So I kind of hate to say this, but you're going to have to go out to them rather than expecting them to come out to you. Most people in industry do not attend academic conferences. They occasionally go out to some of the more popular ones like ICRA or IROS in order to get a better feel of where the research is going in terms of trends. But beyond that, they don't really pay that close attention to the technical details of the talks. They're just more looking at trend analysis. And it's mostly because they've got a business to run. They have to get work done. And these week-long conferences cost a lot of money, not just to attend, but also in terms of lost wages, lost labor, lost productivity. There's a lot of patients that could be seen in a week. And you've got a person just dedicating themselves to a robotics conference. And it's tough sell.
But I would say that there are conferences where we can, like you said, go to them, but they are eager because they already go to them. So for example, a conference that is actually a good one that engineers should go to, I think, is ACRM.
Okay.
Is ACRM is the American Congress for Rehab Medicine, and they publish the Archives of Physical Medicine and Rehab, which is also engineers also publish in there. ACRM is an interesting conference because it's already, they have straight up clinicians who attend, but they also have a lot of research clinicians who attend, and they also have some engineers who attend. I think that's one conference that I think can be more multidisciplinary. Another one that I think Rehab Week, like the ICRA, they're trying to connect with the RESNA. So RESNA, the Rehab Engineering Society in North America, that conference has both engineers and a lot of clinicians. So I think what we have to do is not only go to ROS, but also those more multidisciplinary conferences where you find both the research therapists, the research, the physiatrists as well will also attend often these, as well as as engineers or rehab engineers, not they may not be hardcore in terms of robotics, but they are interested in these topics, and you can put in an abstract. It's actually often easier to get an abstract in because they often only ask for the abstract and it's not a paper. So they after only ask for 300 words or like a very short thing versus, Ross. But I think that's what we need to do. And ironically, the past president of RESNA is a good friend of mine, Roger Smith. And Roger Smith is actually has an engineering degree, an industrial engineering degree, and he's also PhD in he has an OT, he's an OT as well. And what's cool about Roger is he gave a talk at the AOTA, the OT major conference that all the OTs go to. And one of his talks was that OTs need to work more with engineers. And that was actually a part of his plenary talk. And I was like, whoa, that's pretty cool. But anyway, there is an awareness, but I think we also have to go where they are too. We may not necessarily go to AOATA, which is their main conference, but we could go to the ACRMs and the ones that are already interdisciplinary, and the RESNA.
And, I may not directly answer this question, but I'll circle around it a bit, I guess. So, we have this collaboration with VWin and Henry Evans and a couple of other labs this summer and that came up organically in a sense. I believe V reached out to Henry and the whole thing sort of spun up, right? But part of the reason it was able to get traction was all the parties kind of had the bandwidth, capacity, and interest in pursuing this project. And I think, one thing we've seen with our robot is because it's more accessible and affordable, it's a lot easier just to say, sure, let's try that, right? And we have, so we can do lots of trials. We've got some high school students hacking on it. We have a college student who wants to buy one just to play with on the summer, So I think if you set yourself up, I'm speaking from the business side, as an organization that can accommodate these experiments and the cost of experimentation is low, there's a lot of interested parties out there who would love to sort of get in the mix, either on the OT side, the engineering side, or business development, all of that. So I think from our perspective, it's finding those collaborators who have that ambition, that passion, and then being organized in a way to hop on an opportunity when it appears.
Great, Zachary. I guess do you have any last questions or any questions from the audience? If not, then I guess it's let's thank the panelists again. It was very, as I mentioned, like very educational, very thought-provoking, and also this automatically leads to things to think about. That's what this workshop is for, right? And so thanks again to everybody for taking the time and talking about these very impactful and important problems and approaches to be able to solve them. So with that, we'll go to the last part, like the final part of our workshop, very short thing, which is about workshop closing and awards. And I would hand over to Zachary for that.
Right, so this is just the last, it'll probably take less than 5 minutes, just kind of closing out the workshop, just a recap of some of the things we've talked about so far, and an award ceremony just for a moment. So again, thank you all for joining us here for the ICRA 2021 workshop, Learning for Caregiving Robots. It's been a joy having you with us and having talks from so many experts from around the world talking about their different perspectives and ideas and thoughts and research on this topics. I've learned a lot. I suspect many of the other organizers and attendees have learned equally as much. So thank you again for everyone who's been participating, attending, and asking questions. Again, thank you to our sponsors, Hello Robot. Also, so we've got a workshop webpage and a Slack space, which we talked about at the beginning of this talk. This entire recording, workshop recording, will get posted live on the workshop webpage on YouTube, and that'll be linked in Slack. So everyone who's in Slack will be alerted about it once it's available, hopefully in a couple days. So again, thank you to everyone who's joined us here today. And we'll move over to the next slide, the awards ceremony.
Yes,
well, gave it away, but go for it.
It's a drum. That's fine, Zachary. But yeah, it's a drum roll moment. So our best, the award for best contributed workshop presentation goes to Affordance Aware Handovers with Human Arm Mobility Constraints by Paola, Maru, Eric, Ronald, Catherine, and Maya. So big round of applause for them. Looks like, fortunately, I mean, Paola is in UK time, so it's very, very late, or I guess early evening there. So there's like no one here to actually accept the award live. But I would like to thank our sponsors, Hello Robot, again, for sponsoring $1,000 monetary award for this. And I have no doubts that the authors will really appreciate this. Thanks again to Hello Robot, Aaron, and the entire Hello Robot team. Unfortunately, there is no live award ceremony because the authors are not there. But yeah, it was thank you again for the support. Moving to the next slide. So just to wrap up, basically, we would just going forward, just want to say that we will post all the slides. It should be slides, not sides, and the recordings, especially the panel discussion recordings, on our website sometime after the workshop. So for people who could not attend, they would be able to access it. We'll keep the Slack workspace active. So if you haven't joined it yet, I guess you would only get the Zoom link after you join. So probably you all are there. And I would encourage all of you to use that Slack workspace to discuss relevant topics, find all these different collaboration opportunities that we just talked about during the entire day. And we'd also love to collect feedback on this workshop, just so that we know what you liked about this and what you thought we could improve in the next versions, which basically brings to my last point, which is we'd like to also brainstorm with all of you about what the next edition of this workshop should be. We want to continue this effort, and so please join us if you're interested, and let's chat more in Slack, and feel free to contact Zachary or me in this email address, and would love to have you on board for this. Thank you again.